Hello, can you hear me, Radu? Everything
Yes.
is clear? Okay, good. Because I was testing and my internet connection right now is a bit
Hello. Okay.
yeah. But I can see the screen and everything high resolution. I'm good.
Pay attention that you need to present some work.
Yes. Don't worry. I will find a solution now.
Okay. Furkan, are you there? Everything is fine?
Yes. Hey, good morning. Thank you very much.
Okay, perfect. So I will add the participants and then start the streaming on the internet.
Yeah, we'll start the streaming.
Okay. So if it's possible, one of you to accept the participants once you are appearing there. Okay. Hello. Good morning, everyone. Welcome to the fourth Advances in Image Manipulation workshop and associated challenges. This time we have a virtual workshop in conjunction with the European Conference on Computer Vision that is on site at Tel Aviv 2022. Okay, perhaps it's better to wait a couple more minutes for those that are a bit late to connect. So meanwhile, I can point out that the schedule and the details are posted on the webpage of the workshop. The link is there, but probably you can find it easily. The European Conference on Computer Vision platform, but also on the internet if you are looking for our Advances in Image Manipulation workshop. Okay. So this workshop okay, maybe we should start. So I'm repeating myself also for the newcomers. Good morning, everybody. I'm Radu Timofte, one of the organizers of the fourth edition of Advances in Image Manipulation workshop and associated challenges. This is a virtual workshop organized in conjunction with the European Conference on Computer Vision. And this is the opening or introductory talk of this workshop. We have a long day ahead with many talks, and I'll give a brief overview of what you can expect in this workshop. So first and very important piece of information is that on the AIM 2022 webpage, you can find all the updates, the specific details of the talks, and the schedule of this workshop. As typically happens for this kind of workshops, some changes in the schedule are possible, and also some delays, like a couple of minutes, 5-10 minutes, from one talk to another planned scheduled talk. So I invite you, especially the authors of papers, to be connected in your respective session of the workshop, and be there and wait for your allocated time slot to have your paper presentation. And before your allocated time slot, to contact me directly in the chat room and mention your paper ID and your availability for giving the talk, or if you prefer me to play your pre-recording for you, if you submitted one. Okay, so this Advances in Image Manipulation workshop was mainly organized by Andrei Ignatov from ETH Zurich and the AI Witch Labs, Rene Young from ETH Zurich, Marcos P. Conde from University of Würzburg, and Furkan Kinley from Boğaziçi University, and myself. If alongside us, there were many other people involved in the organization and support. Many thanks are going to the program committee members that helped with assuring the quality of the accepted papers, and also with advices and suggestions. Here is the workshop in numbers. This is the 4th edition. Typically, our workshop is organized in conjunction with the European Conference on Computer Vision and International Conference on Computer Vision. We had 76 program committee members. Many thanks are going to them, and 280 reviews, 45 accepted papers. All these accepted papers will have oral presentations. The presentations are typically short, less than 4 minutes. There are 5 minutes for most of the papers allocated in this program today. We have 8 associated challenges, and in our challenges, we got more than 1,000 registered participants. We have a good amount of award certificates for the top teams that participated in the challenges, 6 invited talks, and 9 sponsors. So many thanks are going to our sponsors, and here are enumerated: MediaTek, Reality Labs, Meta Reality Labs, Huawei, Synaptics, Oppo, Raspberry Pi, University of Würzburg, AI Witch Labs, and Computer Vision Lab from ETH Zurich. So many thanks are going to them. They are giving us the budget and also for the prizes awards. Okay, so in this workshop, we had also co-organized challenges. These co-organized challenges were with the mobile AI workshop that took place in conjunction with the CVPR, Computer Vision and Pattern Recognition Conference this year. So we have real-time image resolution, real-time video resolution, single image depth estimation, learned smartphone ISP, real-time rendering realistic bokeh. All these 5 challenges were organized with the mobile AI workshop and finalized in time for this Advances in Image Manipulation workshop at the European Conference on Computer Vision. Then we had a challenge on compressed input image for video resolution, and a challenge on a reversed ISP image signal processor using data from 2 different cameras, and a challenge on Instagram filter removal. In total, we had 10 competitions. 9 of them were hosted on Codalab platform, and we got more than 1,000 participants registered in these 10 competitions, with more than 100 teams that competed in the final test phase, submitted solutions and fact sheets. Okay, so a key aspect of the associated challenges is the reproducibility. So the winners are checked for reproducibility, and all the ranked teams were asked to submit both sources and fact sheets. And we are promoting more and more real-world scenarios so that the developed solutions to become easily adopted and implemented for real-world applications. So we have award certificates for the top ranking teams in our 2022 challenges, and given the budget that is still some cases to be confirmed, we'll provide money or product prizes for the top winners and sometimes for the following teams according to their performance in the challenges. The teams will be contacted by email. The certificates will be posted on our webpage somewhere today. Most likely we'll make the certificates available. Okay, I will not go through the certificates because there are quite a number of them, and virtually it's less appealing than in an in-person award ceremony. So I will just leave this to the participants to check their own certificate, and to the challenge organizers to emphasize and reveal the top leading teams in each challenge. So many congrats to those top ranked teams, and also to all the participants in the AIM 2022 associated challenges. So we have 45 accepted papers. And these accepted papers, all of them will be presented, oral presentation today. We have 8 oral sessions. Each of these oral sessions starts with a challenge report paper and continues with challenge papers or papers related in topic. Okay, so we have the first oral session will be on bouquet effect rendering challenge and editing in gowns. And then we'll continue with the efficient depth estimation challenge, enhancement and learning papers, learned ISP challenge and high dynamic range papers, reversed ISP challenge and related challenge papers, efficient super resolution challenge, image super resolution restoration and blurring, efficient video SR challenge, light field angular super resolution, video deblurring, compressed image and video super resolution challenge, Instagram filter removal challenge, and photosynthesis. Okay, so also, besides the 45 accepted papers in this workshop, we have 6 invited talks from outstanding scientists, researchers, and they will discuss about top current research trends and techniques, okay, that are the state of the art nowadays. Okay, so here I'm mentioning Sabine Sundstruck, Professor Sabine Sundstruck from EPFL. She will discuss about uncovering local semantics in CNNs and GANs. Then Professor Björn Omer from University of Munich will discuss about the stable diffusion plus democratizing visual synthesis. Then Professor Felix Heide from Princeton University and AlgoLux, and we'll discuss about the differentiable camera, designing cameras to detect the invisible. Then we have Dr. Pratul Srinivasan, and he will discuss from Google Research, and will discuss about neural inverse rendering. Then we have Dr. Bo Zhu from Meta Reality Labs. We'll discuss about practical considerations on device for on-device denoising, and Professor Gordon Wettstein. He will discuss about efficient neural scene representation, rendering, and generation. So again, I'm listing the sponsors of our workshop and challenges: MediaTek, Reality Labs, Huawei, Synaptics, Oppo, Raspberry Pi, University of Würzburg, AI Witch Labs, and Computer Vision Lab from ETH Zurich. So we are planning new trends in image restoration enhancement workshop and mobile AI workshop at CVPR 2023, and you could expect new and interesting associated challenges on diverse topics such as quality assessment or quality mapping, super resolution, high dynamic range, deblurring, dehazing, restoration task, night photography, and viewpoint synthesis. And like usual, we can expect like a schedule that involves a couple of months of development in the challenge, 1 week of testing, and then a couple of weeks for the preparation of challenge papers and submission. So before starting the talks in this workshop, I want to advertise some open positions for PhDs and postdocs on diverse topics like restoration enhancement manipulation, computational photography, learned compression image and video understanding, learning paradigms, augmented and mixed reality, edge inference, and mobile AI. So these positions are available under my supervision at the University of Würzburg. So without further ado, I will now open the floor for the bouquet challenge. So Andrei, are you ready?
Yes, I'm here.
Okay, so Andrei will share his slides and present the realistic bouquet effect rendering for mobile GPUs.
You need to enable screen sharing.
Okay. Okay, I made you co-host. Sorry.
Okay, good. Hello, everyone. My name is Andrei Ignatov, and we'll start with the first mobile AI challenge on realistic bokeh effect rendering. Bokeh effect is a popular artistic effect used to highlight the main object of interest by blurring all out of focus regions, and unfortunately mobile cameras cannot render this effect naturally due to physical limitations, and therefore usually one uses computational based and deep learning based approaches for producing a strong bokeh effect on mobile photos. In this competition, the participants were asked to solve exactly this task, to render natural bokeh with deep learning, and moreover, the final solution should be quite efficient, so it should demonstrate good performance on mobile GPUs, and it should be able to process HD resolution images directly on mobile devices. The participants were provided with the EBB dataset consisting of 5,000 aligned shallow and wide depth of field images captured with Canon 7D DSLR camera. And the solutions submitted by participants, the performance of the solutions was measured using the following metrics: using PSNR score for estimating fidelity, results of the model's structural similarity index, SSAM score that was used as a proxy for perceptual score, mean opinion score computed in the user study, and the runtime of all submitted models was evaluated on the Kirin 9000 chipset with a powerful 24-core Mali GPU. And on the Kirin 9000 platform, the runtime was measured when processing 1024 times 1024 pixel images. In this challenge, we had two tracks. In the first track, the final score was estimated based on PSNR and runtime results. And in the second track, the final score was estimated only based on the mean opinion score. Nevertheless, in both tracks, the participants had to submit their flight models. Therefore, all solutions were evaluated together in the first and second track. To design efficient solutions and to optimize their models, the participants were provided with a benchmark application that allows to load and run custom TensorFlow Lite models on any hardware. And since in this challenge we used the Flight GPU delegate, the runtime of the models on participants' devices was proportional to the runtime of the target platform. This slide summarizes the results obtained in this challenge. In the first track, the best result was obtained by team Antin-CV. They designed a very, very shallow architecture of size of less than 60 kilobytes. And not surprisingly, the runtime of this model was very good. So it required less than 30 milliseconds to process one HD resolution image on the Kirin 9000 chipset. The second best result was achieved by team NSI, and their solution was just a bit slower, and nevertheless it still required less than 100 milliseconds to do the processing on mobile GPU, but its visual results were substantially better. In the second challenge track, the best numerical and fidelity results were achieved by team Joute Vision. The mean opinion score of this solution was 3.8, and it significantly surpassed all other solutions submitted in this challenge. Nevertheless, it was still falling behind slightly. It was still falling slightly behind the baseline BiNet architecture. So the first team challenge winner, Antin-CV, used a very shallow unit-based model. So we remember that the size of this model is less than 60 kilobytes, and this was achieved by using only three different levels, three different scales in the unit architecture, and heavily reducing the number of filters in this model. So the architecture of this model was heavily optimized for mobile GPU-based inference. And the model itself was trained to maximize the PSNR loss function directly. So, and nevertheless, this allowed this team to achieve quite good PSNR scores and quite low runtime results. The second solution in the first track proposed by team NSI was also using a unit-based model, but in this case, the architecture was significantly heavier. So it was processing images at 5 different scales, And this model was actively used on skip connections that significantly boost visual and numerical results. And the model was trained to minimize combination of the L1, MSSM, ResNet50, and color histogram loss functions. As was already mentioned, the best visual and numerical results were achieved by Team Jute Vision. The solution from this team was based on the BGGAN architecture that was using two consequent unit architectures. The first unit model is very basic, while the second one contains additional spatial attention and channel attention blocks. And the entire architecture was trained to minimize combination of L1 SSAM and perceptual perceptual and of course adversarial loss functions, as this is an adversarial based architecture, and it used to discriminators that learned different aspects related specific to our bokeh effect rendering task. And the description of all the submissions proposed in this challenge is provided in the challenge paper, so you can find them by visiting this link. So, and that's it from my side. Thank you for your attention, and if there are no questions, then we can probably move to the description of the challenge winners, presentations from challenge winners.
Okay, so are there any questions? If you have questions, please just unmute yourself and just let us know, or you can just use the chat and write down the question. Okay, so if there's no question, then thank you, Andrei. And now let's move to the next talk, a challenge work from this challenge, a challenge participant work. So the authors are here, and we can play presentation, and the authors will be here to take the questions afterwards.
Hello everyone, I'm Mehmet Kerimcan, and I'm pleased to present Adaptive Mask-Based Pyramid Network for Realistic Bokeh Rendering, which is a joint work between Samsung Research UK and CERT-ITI units. Bokeh effect is a fundamental photography technique, where a region of the image is highlighted by blurring out the rest. The in-focus region remains clear, whereas the other parts are blurred, leading to a pleasant effect. Traditionally, the bokeh effect is achieved by focusing the camera on the region and taking the photo with a wide aperture lens. However, this requires cameras with large aperture lenses, which are often expensive. Furthermore, domain expertise might be required to achieve high-quality bokeh effect. ML-based synthetic bokeh rendering is a viable alternative, especially for devices without adequate sensors. However, on-device ML-based methods have their own challenges. We need a performant model with high-resolution, high-fidelity outputs. ML-based methods learn the blur style of the camera used to collect the dataset. We also need an interpretable and an interactive model. A model that implicitly learns the focus area might not be desirable. In our work, we designed a model that tries to meet these requirements. An on-device accurate model with the ability to change the blur style and the focus area. We propose AMPN, Adaptive Mask-Based Pyramid Network for bokeh rendering. Our architecture consists of two blocks: the mask-guided bokeh generator block and the Laplacian pyramid refinement. AMPN takes in the high-resolution input and decomposes it into high-frequency and low-frequency components. Low-resolution components set the MGBG block to produce the focus mask and the low-resolution bokeh image. The low-resolution bokeh image and the higher-frequency content of the LPR block are then progressively refined to generate the final high-resolution result. We first focus on the MGBG block. The MGBG block has one goal: to produce a low-resolution bokeh. A single network is sufficient, but to have an interpretable model that can be guided with any type of mask. We propose a stacked two-network setup with networks G1 and G2. G1 predicts the focus mask, and G2 generates the bokeh image. Both use the same lightweight architecture. G1 is trained in a weakly supervised fashion without any mask ground truths. Note that G1 can be removed with inference when a mask is provided. In G2, we use a dual attention mechanism. The idea is to have a long-distance residual connection from the RGB channels of the input to the output. We plug in attention modules to the residual connection and the output of the G2. We now focus on the LPR block. The LPR block has two functions: to upsample and refine the low-resolution bokeh. First, the low-resolution input, predicted mask, and low-resolution bokeh image are upsampled to the resolution with a higher frequency content and concatenated. This tends to respect the refinement network that generates the refinement mask. This mask is fed to the fine-tuning convolutional bus and multiplied with the lowest higher resolution content to produce the high frequency residual of the first pyramid level. This process is repeated for each level. The resulting residuals are added to low resolution bokeh image that is progressively upsampled to produce the high resolution bokeh result. LPR builds on the existing literature in three key aspects. The mask predicted by G1 is upsampled to guide the refinement process. Dual attention mechanism is used in the refinement network. We use mask blending for spatial guidance, where we directly copy the focus area from the input via residual connections. We train our model on EBB dataset with L1, LPIPs, and SSIM losses. We apply the loss only to the final high resolution bokeh. We evaluate using PSNR, SSIM, and LPIPs metrics on the Val29 LUP4 split. Compared with the existing methods, AMPN is faster and smaller. It produces highly competitive results. It has the best LPIPs and the second best SSIM. We present several key insights about AMPN. The refinement network is the computational bottleneck. LPR on the setup can render bokeh without G2, and all the variants are competitive against alternatives. AMPN setup shown in the first row is the best accuracy performance trade-off. With AMPN, we can adjust the close set. By changing the intensity, the out-of-focus areas in the mask will be simulated with different f-stars. Due to our stack network design, we can learn from bokeh datasets but perform a more generic task: mask condition image blurring. We show images where we use G1 predicted mask, user provided mask, depth, and saliency maps to generate the final bokeh image. To summarize, our model achieves state-of-the-art metrics. It's faster than existing methods, can adjust blur strength, and goes beyond bokeh to perform mask-guided blurring with any type of mask. Thanks for watching our presentation, and feel free to ask questions.
Okay, are there questions? The authors are here. Answer. Okay, meanwhile, I'm asking if the bokeh loss GAN paper, the authors are here or not. The paper ID 356. Okay, so Brian, could you please?
Okay. Yeah, I can share screen.
Yes.
Hello. Hi, I'm Brian Lee, and I will be presenting bokeh loss GAN multi-stage adversarial training for realistic edge-aware bokeh. So this project was part of the bokeh effect rendering challenge for the ECCV, the AIM challenge. So the bokeh effect is an aesthetically pleasing effect that is commonly seen in photography, where you take an image with a shallow depth of field, keeping the in-focus regions sharp, while the out of focus regions remain blurry. This effect is very easily naturally achieved on traditional DSLR cameras due to the large focal length and wide aperture lens of a traditional DSLR camera. This is, however, difficult to replicate on a mobile camera due to hardware limitations of the mobile sensor. We must thus rely on synthetic bokeh rendering on the mobile case. This is difficult, however, because we need to both learn to accurately segment in focus and out of focus regions while learning an accurate bokeh style on the out of focus regions. We thus propose bokeh loss GAN. So the main backbone of the network consists of two modules, a DPT depth module, which predicts a depth map and a 8-layer NAFnet, which has shown to be more computationally efficient than some other architectures. We then concatenate the original all-in-focus input with the depth map, and then we run it through the network to create a bokeh output. This network is, however, trained in 2 stages. The first stage, a pre-training stage, is trained with 3 new bokeh loss functions, which encourages sharpness in the edges and uses the depth map as a grayscale saliency mask. The second stage consists of a refinement module where a GAN-based discriminator is used and to refine the bokeh output and learn an aesthetically pleasing effect. So the 3 bokeh loss functions we introduced consists of a Sobel-based loss function, which sharpens the edges of the in-focus regions. It also consists of an edge difference loss, which tries to replicate the edges of the ground truth images. It also consists of a background blur loss, which tries to smooth the background. In this pre-training stage, we use this combination of these loss functions, and we create a rough bokeh effect that has sharp edges. However, it might be slightly distorted in the background. In the second stage, we use 2 patch GAN-based discriminators with 2 different receptive fields, similar to the idea used in the BG-GAN paper. And we train the module adversarially. Ablation studies have shown that this NAFnet architecture shows some considerable, it saves some considerable computational overhead while keeping the MOS score similar. The loss functions have also shown to greatly improve performance during the training. So this motivated us to include these loss functions as well. Our final results are as shown, and we received a PSNR score of 22.81, an LPEPS of 0.2207, an SSIM of 0.8653, and an MOS of 3.4. So in conclusion, we provide a new monocular bokeh synthesis method using blur cues and a grayscale saliency mask. We introduced 3 new bokeh-specific loss functions for edge sharpening, and we successfully apply the NAFnet architecture to bokeh and show that it can lead to some lower computational overhead. Thank you for listening to this presentation, and I'd be happy to answer any questions.
Radu, you are muted.
Oh, okay, thank you. So if there are questions, just let us know either by writing in the chat or just unmute yourself and ask directly.
Yeah, I do have a question. You mentioned that you are adapting or kind of reusing NAFnet ideas. Can you explain briefly which ideas, which particular blocks from NAFnet? Because it is going to be presented here actually at the ECCV, and I was also interested.
Oh yeah, so so for the main backbone architecture, actually, let me share the slide again. So rather than using just the unit, just using the nonlinear activation instead of just the regular unit, and also lowering the like playing around with the number of math blocks. There's like kind of a diminishing returns that you can see if you increase the NAFnet size too much. So we just include 8 NAF blocks and just changing, going from the linear activations to, the nonlinear activations to the non-linear activation free network. It gives a slightly lower like a slightly lower number of G-flops, which allows for the network to run faster.
Okay, I see. Thank you. Thank you.
Okay, thank you, Brian. For the next talk, we have style adaptive semantic image editing with transformers, and the authors are here, and we'll take the questions after running their pre-recorded talk.
Hello, everyone. Welcome to the presentation of our work, Style Adaptive Semantic Image Editing with Transformers. My name is Rui Gong, a PhD student from Computer Vision Laboratory in ETH. This is a joint work with Edward and Luke. Between our proposed style adaptive semantic image editing problem and the traditional semantic image editing problem. To control the style of the synthesized area, such as the black car in above example. Respectively.
Okay, so apparently there is a problem with the sound. Rui, are you there?
Yeah, hello.
So maybe you could play yourself the
Yeah, I can play
the video.
Myself.
Okay.
Yeah, thanks. Yeah, thanks.
Okay, because I had some issues with playing the sound of the recording. Now Rui will present himself. We cannot hear your sound.
Firstly, sorry, can you hear the sound?
Yes, now yes.
Yeah, to explain the difference between. Hello, everyone. Welcome to the presentation of our work, Style Adaptive Semantic Image Editing with Transformers. My name is Rui Gong, a PhD student from Computer Vision Laboratory in ETH. This is a joint work with Edward and Luke. Firstly, I would like to explain the difference between our proposed style adaptive semantic image editing problem and the traditional semantic image editing problem. In the traditional semantic image editing problem, the masked image and the semantic label map corresponding to the masked area are given, and the aim of the task is to synthesize the masked area to generate the hidden masked image. However, in the semantic image editing problem, there is no control over the style of the synthesized masked area. In order to overcome the problem, we add another style reference image to control the style of the synthesized area, such as the black car in the above example. Thus, the challenge of the style adaptive semantic image editing problem involves synthesizing the masked area according to the semantic label and transferring the style of the reference image to the masked area, which is corresponding to the intra and inter knowledge transfer respectively. In order to resolve the style adaptive semantic image editing problem, we adopt the generative adversarial model training pipeline, and we introduce the intra-image and inter-image multi-head attention modules into the generator, which is abbreviated as IAMA and MRMA respectively. For the intra-image multi-head self-attention module, the query key and value of the transformer layer is from the content image. For the inter-image multi-head self-attention module, the query is from the content image, while the key and value are from the style image. In this way, we transfer the intra and inter-image knowledge to the masked area. Then we show the qualitative experimental results. It is observed that our proposed method can synthesize the content and stylize the masked area according to the reference image. We verify our method on the landscape dataset and on the human face dataset and the street scene dataset. Besides, the quantitative experimental results also show the effectiveness of our method compared to the baselines. At the take-home message, we propose and study the style adaptive semantic image editing problem and realize the intra and inter-image knowledge transfer through the intra and inter-image multi-head self-attention layer.
Yes, and thanks a lot for your attention. And if any questions, I'm here to answer your questions. Yeah.
Okay, are there questions? So if you have questions, just unmute yourself and let us know, or write them down in the chat room. Okay, so if there are no questions, then thank you, Rui.
Yeah, thanks a lot. Thanks a lot.
Okay, let's move on to the next talk. The third times the charm, and the authors are here. I will play the recording, and then for the questions, the authors will take them at the end of the presentation. So.
I'm Yuval, and I'll be presenting a work third times the charm. During the last few years, StyleGAN 2 has become one of the most popular GAN architectures thanks to its amazing performance across many image manipulation tasks. Recently, StyleGAN 3 was released to overcome the texture state phenomenon, which limited StyleGAN 2 for applications such as editing. Doing so, StyleGAN 3 potentially opened the door for new video-based applications. Our main goal of this work is to explore the new generator, understand its capabilities, and compare them to those of StyleGAN 2. Specifically, we focused on two things: latent space editing and GAN inversion. And we asked three central questions. First, do things that work well in StyleGAN 2 also transfer to StyleGAN 3? Second, how do we perform image inversion and editing on unaligned-based images using StyleGAN 3? And lastly, what potential advantages does StyleGAN 3 offer in the world of video editing? So let's begin by talking about image editing. We began by exploring image editing techniques over StyleGAN 3's aligned generators. And by adapting several methods to interface GAN, we observe that the edits are a bit more entangled than with StyleGAN 2, but still work quite nicely. The most direct approach for editing unaligned images with StyleGAN 3 is to simply use the unaligned generators and find semantic directions in latent space as we did before. In general, however, we found the latent space of unaligned generators to be more entangled than those of aligned generators. In StyleGAN 3's architecture, one can apply a user-specified transformation that can control the in-plane rotation and the position of the face in the image canvas. Therefore, to achieve more disentangled edits for unaligned images, we can control the rotation and the translation of a given face image with these user-specified parameters. And this brings us to advantages. First, we only use the aligned generators, so we have the same directions that can be applied for both aligned and unaligned images. And second, we can achieve more disentangled edits. In the paper, we also adapted StyleGAN to work over StyleGAN and found that editing in this space is even more important than StyleGAN 3 than it was in StyleGAN 2. And we now move to a GAN inversion task. A common approach to inverting image with StyleGAN 2 is training an encoder using a fixed generator. By training a similar encoder for the aligned StyleGAN 3 generator, we get comparable results to those of StyleGAN 2. We then asked ourselves how we can extend to inverting unaligned images. One approach is to simply train an encoder for the unaligned generator as you would with the aligned generator. However, we found that doing so is much more difficult due to the variability of the underlying inputs, resulting in many unwanted artifacts. We can therefore take a different approach with artifacts. Given an image, we'll take two crops, a crop with the face in the original position and an aligned crop. Then, by using a landmarks detector, we detect the eyes and the rotation and translation offsets between them. By using these parameters and the user-specified features with the align generator, we can achieve a face with the same position as in the original crop image. Putting this together, we can invert unaligned images by inverting the aligned image and applying the computed parameters as a user-specified transform. This will give us a reconstructed image with the same pose as the input image. And here are some of the inversion results. By inverting the unaligned images, we can now perform various edits over the codes. We now turn to explore the video editing capabilities of StockM. We first need to invert the video. The naive approach would be to invert frame by frame as we did before. However, this gives results that are not accurate enough. We therefore use the PTI fine-tuning approach. Given the latent codes corresponding to the video frames, we fine-tune the generator to achieve near perfect reconstructions of the video. We can then use the fine-tuned generator to invert and reconstruct the original video frames. Now let's edit the video. For example, let's say we want to edit the hair color. But when pasting the face back in the original video, we may come across a problem. Notice that the hair region that was missing from the aligned video frame is unedited, resulting in a non-coherent edit of hair. To solve this, we can expand the field of view with edit. We'll first invert and edit the cropped frame. Then, by adding an offset to the translation parameter, we can shift the generated frame so the entire hair appears in the generated image. So now we have the edited frame and its shifted version. Then we can simply merge the frames in a pixel space. And this gives us a frame with an expanded field of view, which allows us to edit the entire video with an edit that affects the entire region of interest. Thanks for listening.
Okay, so
I'll be happy to answer questions if there are any.
okay, so if there are questions, please just unmute yourself and let us know. Meanwhile, I will just warm up a little bit. So, I'm just curious, is this approach here can be applied on a streamed video in real time on a normal GPU and get the nice rendered outputs?
So I think that apply it in real time is a bit problematic because we rely on the fact that we have several frames to fine tune the generator to be adapted to the specific person. But maybe we can apply it in real time with a warm up, like we can use the frames of the several few seconds for the fine tune of the generator, and then apply it in I think it can be applied in a real time using this approach.
Okay.
With a normal GPU.
Okay, that will be very useful. Okay, are there some other questions? If not, then thank you very much. And
thank you.
Let's move on to the next presentation. We have CNSNet work. The authors provided a pre-recording. I will run it. So if you have questions, write them down in the chat room or unmute yourself at the end of the presentation.
Hello everyone, my name is Qi Hao. I'm a master student of University of Science and Technology of China. In this video, I will present our paper, CNSNet, continuous embedded shadow network for shadow removal. Shadow removal is an outstanding communication method. In a shadow image, we can directly separate it into non-shadow region and shadow region based on the corresponding shadow mask. These features of the shadow region are wrapped, while in shadow-free region, the same measure miserable with processing and building up the texture regions for better performance. However, the potential operation does the trickle network-based methods based on range of certain entities, which not investigate. To address the aforementioned issues, we propose a continuous navigated shadow network for shadow removal. Here is our framework. It comprises 3 components. The green box indicates a soft region mask predictor, which is introduced to measure the correlation between the 2 regions. The orange box is a shadow-oriented adaptive normalization model. It's designed to guarantee the statistical consistency between regions for region-wise restoration. The purple box shows a shadow-aware application method. It neutralizes the soft region mask guided attention for pixel-wise restoration. Shadow-oriented adaptive normalization extract the various shadow region adaptively applying shadow region guidance to shadow mask. Unlike region normalization, this case apply parameters apply the features of shadow the scale and bias of shadow regions and showing orange dotted lines. What features in our network, we expect to develop an orange connection between 2 regions and further design a shadow-aware application in transformer model. Under the guidance of this model constructs the precise connection from the pixels with high correlation in the shadow region pixel by distribution. Second, the reason why we use the soft region mask instead of the hard region mask is mainly because the hard shadow mask separates the 2 regions so absolutely, causing the loss of information transmission and transfer, while the soft mask performs better and showing this frequent. Regulate our network to constrain benchmarks with ISTD, adjusted ISTD, and design things. ISTD is taking place values respectively and respectively. On the tables, observe that our method achieves superior and competitive results than other state-of-the-art methods, maintaining the balance of network impacts. Especially on details. Based on assembly of non-random detection, shadow removal must be and the efficiency of information operation. Design the weakest navigated shadow network in order to avoid auxiliary guidance of shadow masks. Particularly investigate regional information, both visual-wise and pixel-wise ways. Well, that's all. Thank you for your attention.
Okay. Are there questions? Okay, so if there are no questions, then we'll move to the next talk. And we are speaking here about the unifying conditional and unconditional semantic image synthesis with OCOGAN. The authors are here. I will run their pre-recording.
I will present unifying conditional and unconditional image synthesis with OCOGAN, which is a joint work with Stefan from Telecom, Camille and Jacob from Meta. So first of all, unconditional GAN perform very well at synthesizing high-quality images on simple datasets, such as cars, cats, but they perform poorly on complex datasets containing lots of objects, such as ID20K. And on the other hand, you have GANs for semantic image synthesis, which in this case, the generator is conditioned on a semantic map that indicates the position of objects in the image. And these types of GAN they obtain better results than unconditional ones in on complex data set. As an example, on the figure on the right, you have STALGAN2 on the top that synthesizes sample from AD28, while on the bottom right, you have OASIS, the state-of-the-art conditional GANs, also trained on AD20K that synthesize samples from it. So you can see that image are much better quality and with better, with sharper details. So it also allows us for better user control in the conditional case, even though labels are costly. So up to now, the majority of GANs for image synthesis have a specific architecture and training pipeline for a given task, but there could be strong motivations for having a unified hybrid models that can deal with both types of generation. First, it would reduce pool of different models for similar tasks, and also we could leverage the synergy between both tasks in a specific data setting. And this is what we show with OkuGAN, which stands for Optionally Conditional GAN. And it's an end-to-end architecture that can synthesize images both unconditionally and conditional semantic graphs. The generator is made of 3 components, an unconditional and conditional style networks that output styles in the spatial latent space, while there is a shell synthesizer that takes the styles and outputs an image. It's worth noticing that most generator parameters are shared among the 2 tasks in the shared synthesizer. About the training of our model, we adopt an adversarial approach with a shared discriminator and use 2 types of loss: a global binary entropy loss at discriminator and encoder for enabled 1 data, and a per-pixel multi-class entropy loss at discriminator decoder that tries to classify real images according to a true classes, while it classifies synthesized images as fake. About the experiments, we evaluate 3 types of regime: in the limited, full, and full data regime, and also in a partially annotated regime where we use few annotated data in the full size of the unconditional data set. We compare to specialized baseline, unconditional and conditional 1, and also to existing input baselines like PSP and SPGAN. We take 3 data sets: Zscapes, AD20K, and CocoSurf, and we also select random samples from them to create subsets to train the limited data regime. We obtain significant gain in the limited data regime for conditional data, as it benefits from semantic structure of labels, while in the partially annotated regime, conditional generation is boosted thanks to the additional amount of conditional data. Also, we are competitive with specialized baseline in the full data regime. So let's have a look at some qualitatives. So in the limited data regime with Addendor, you have on the left unconditional samples, on the right conditional samples, and OkuGAN generates images of better quality with sharper details. And in the full data regime, we are competitive with Spade and OASIS, which are specialized baseline. So as a takeaway, we proposed OkuGAN, a unified architecture trained in the end-to-end way that obtained competitive results with the specialized baseline and improve our existing input baseline. And our model is also better than unconditional specialized baseline in a limited, partially annotated regime.
Okay, are there questions? The first author is here with us and can take and answer. Otherwise, you can always try to contact by email, and the authors will be more than happy to answer. Okay, the next presentation is the invited talk from Professor Sabine Sundstruck from EPFL. And because we are a little bit behind the schedule, we'll lay.
Hello, everyone. That will be in this presentation. And many thanks also to the organizers for the invitation. The title of my talk is Uncovering Local Semantics in CNNs and GANs. As a quick introduction, as I'm only virtually present, I'm a professor in computer and communication sciences at EPFL in Lausanne, Switzerland, at the shore of gorgeous Lake Geneva, where I lead the Images and Visual Representation Lab, IVRL. At IVRL, our imaging research is at the intersection of algorithms, including machine learning nowadays, human vision modeling, and physics, with the goal of improving the photographic experience of everyone, including one lady here who still doesn't have a camera. Our application domains are thus in computational photography, computer vision, image quality, and image aesthetics. So let's talk about algorithms and specifically deep learning, machine learning. I know this is a virtual presentation and I show up as a little side window next to presentation slides. But if you look over, you see that my hair is about as gray as the box on that slide, which illustrates should actually be black because it illustrates the black box of deep learning models. As many of my generation of researchers in computational imaging and computer vision, I have a love-hate relationship with deep learning. Yes, the performance of many vision tasks has improved tremendously, exponentially, with the advent of these neural networks. And yes, the black box behavior of these mostly deep learning models was and still is extremely provoking for all of us in research who improves clear explanations. So in this talk, I will present our research into explainability and interpretability, of neural network architectures, first CNNs, and then, if time permits, also GANs. It spans a research area of several years and covers the research of two of my PhD students, Edo Collins, who's now Global Research, and Ejan Hoyushkar, who's still in the lab. We are by far, by the way, not the only ones working on this, as it is the holy grail we are all aspiring to. So I'm not claiming to be comprehensive in covering all the research I do. I concentrate on what we do. And yes, before you ask, yes, we are continuing that research also into neural architecture models based on transformers and diffusion models, but we are not quite there yet to present on in a prime time venue such as this one. So, okay, now on a basic level, what are these convolutional neural networks we are using in our image and video processing? On a schematic level, they take an image composed of several matrices representing color, which you can also call a tensor, several matrices stacked on top of each other, and they perform a cascade convolution, as it implies, followed by some pooling operations. So, well, these intermediate tenor representations, we perform the same kind of convolution pooling again. In these intermediate representations, we also have tensors. Also, again, stacked matrices. And that's where our showing actually started. We do know that matrices and tensors can be factorized to reduce dimensionality. We all know this from our linear algebra college courses. Matrix factorization or matrix decompositions are methods that represent a matrix as a product of two or more matrices. In this example, matrix factorization decomposes the data matrix A into the product of two lower ranking matrices U and V, where U contains a basis function and V the weights. There are various types of matrix factorizations, such as LU factorization, Cholesky factorization, single value decomposition, etc., etc., etc. Matrix factorization is widely used in pattern recognition, image denoising, data clustering, also, etc., etc., etc. We have previously successfully used matrix factorization methods, most prominently in our work on video reconstruction, demosaicing, dynamic range imaging, and RGB plus NIR infrared imaging. In the work presented here, we will use two methods, non-negative matrix factorization and K-means. We were inspired by the work of Lee and Sung, published in Nature in 1999, who found that non-negative matrix factorization learns a parts-based representation of faces. NMF was applied to a database of about 2,500 grayscale facial images, each containing 19 by 19 pixels. Illustrated here on the left is the K equals 49 rows of V, which forms a set of basis images. Now, a particular instance of a face can now be approximated by a weighted combination of these basis images. And the weighted combination is given by the row of U, And if you multiply the two, you see on the right then the approximation you get, and you can compare it to the original. If you look closer, it's kind of seeable. If you look at the 3 matrix, you actually see in black the positive values, and you can already see and make out some facial structure. So the power of NMF for semantic interpretation was well known. So our contribution is basically just to make some useful applications and algorithms. So NMF works very well for ReLU-based CNNs. The rectified linear activation function, or ReLU for short, is a piecewise linear function that will output the input directly if it is positive, otherwise it will output 0. It has become the default activation function for many types of neural networks because a model that uses it is easy to train and often achieves better performance. The resulting activation matrices are thus all positive, making NMF a logical choice. And now by controlling the rank of the factorization K, we can induce different levels of compression to neural network activations. We found that applied to network activations, the factorization into V and U can be thought of as a decomposition into what and where. This is very similar to other instances of dictionary learning. And in addition to opening an interpretable window into the hidden activations of a CNN, the matrices U and V are also useful for real world tasks, such as co-localization and image search. So let's first look at U. We can reshape U into heat maps. As the image gets processed layer by layer, the hidden activation at the ith layer of the CNN is a tensor A, shown on the left, with a width and height of W and H, respectively. In most cases, H and W are smaller than the H and W of the original input image due to the pooling or subsampling operation commonly used in CNNs, the ReLU we just talked about. The number of channels C is usually defined as part of the network architecture, and in deep layers it's usually between 256 and 1024. So to apply matrix factorization, we thus partly flatten A into a matrix. Note that the matrix A is effectively a bag of features in the sense that the spatial arrangement has been lost. The rows of A can be permuted without affecting the results of the factorization. We can naturally extend factorization to a set of N images by vertically concatenating their patch features together. Consequently, a single column of U can be reshaped into N times H times W and can be viewed as a set of N heat maps, each one of dimensions H and W. So the spatial dimensions H and W are those of the activation, and so of course have much lower resolution than mostly than the original input image. So we can match the size of these heat maps though with the input image by just using bilinear interpolation and upsample them to the same size. And then we can actually overlay the N heat maps on top of their respective input images. So considering that we take the activations of the last layers, they really are much lower resolution than the image, and thus rather imprecise. By giving each of the case sets of heat maps a different color, we can overlay U with the original images all at once, as shown in this figure on the right. This is an example of K equals 3. So our method works as follows. We take a small number of images, 3 to 5 of the same object, and run them through a pre-trained network like BGT19 and BESNet 50. No, we do not train again. The network has never seen our images before. But given the activation matrix of the very deep layer, our method is able to localize the same semantic concept. In other words, the heat maps we obtain will localize in each of the images the same semantic object or object part. So we call our method deep feature factorization for concept discovery, and we published it a few years ago at this same conference. So let's give some real examples. Here's a gymnast, 5 different moments in time from the ICOG segmentation dataset. To repeat, VGG pre-trained has never seen these images before. We feed them to the network and perform NMF on the last activation layer. This is a result when we choose K equals 1. The body of the gymnast is well identified. Note again, we perform NMF on the last layer. The resolution of our heat maps is much smaller than the one of the image, but the localization, i.e. where it is quite perfect. For K equals 2, we can now see that we extremely well separate body and limbs. For K equals 3, we can now separate the body, the arms, and the legs. And for K equals 4, we get body, arms, legs, and the gymnast's bar, which is actually quite amazing. So what is our observation? The decomposition we perform shows what information is relevant and what isn't. The absence present of a part is relevant, its position or orientation isn't. So we benefit here from the invariance learned by the CNN. So we can say for the VGG19 network, K equals 1 often highlights the salient object. Setting K larger than 1 results in decomposition into semantic parts of the object. And then incrementing K reveals a cluster hierarchy in feature space. For example, in our what we just showed you, this body, midsection, and limbs, and then arms and legs. Let's now look at another image, another scene. Here again, for K equals 1, gives us the elephants. Remind you again, this is again the same ICOG data set, not seen by VGG19 in training. K equals 2, similarly as before, upper and lower body. So that was the gymnast. Idem for K equals 3, K equals 4, here the ground information. Just because it's so much fun, give you some more. Here is another example for K equals 4, pyramid, rider, background, never seen by VGG19, and the Taj Mahal for K equals 3. We'll see this before. Now, what about the different kind of architecture? ResNet. So ResNet has residual connections and is actually, built quite differently than VGG19. So again, we use the pre-trained ResNet 50. ResNet 50 has not seen these images before. And here again is the gymnast. While K equals 1, there's actually not much to be said. But K equals 2 shows that we actually well separate background from foreground. K equals 3, limbs, separation of limbs and body. And now K equals 4 becomes a little bit difficult. It basically shows background information. And with the 5, it shows the bar. So what can we observe? We can use the matrix U for semantic localization. The matrix U can be reshaped into case sets of low resolution heat maps. Each of those sets corresponds to a semantic part based on the learned CNN variance. Increasing K reveals a part hierarchy in feature space, so we can go from object to object part. If we use an architecture that uses residual connections, e.g. ResNet, leads to distinctly different matrix factors. They're not the same. What we can now do, though, is we can put a threshold, we can threshold the heat map to get a binary co-segmentation map. And we can place a bounding box around the co-segmentation map, and we can actually do very good co-localization results. Now, I'm not going to go and explain this code, how we did the co-segmentation, co-localization in detail. I'll do it for the paper, but our results are as good as better as the domain-specific methods. So you might have some question why I bring up a method that was published 4 years ago, a lifetime if you consider computer vision machine learning. However, we recently got a very nice email from the maintainer of PyTorch GradCam, which is a widely used library for explainable visualization of network activations. In short, the EFF story deep feature factorization was added to it. And there's also a very nice tutorial, so please go check it out. In his email to us, he referred to DFF as an amazing and overlooked method. We were personally pleased with his assessment. So let's now also look If U was the where, now let's look at V as the what. We already saw that in the example of V and so on. So V is a global descriptor of the image. So if U shows us spatially where a certain concept is, V is the representation of that concept in CNN feature space. So recall that when A is a CNN activation matrix, each row represents an image patch embedded in C-dimensional feature space. The space is a latent space, and as such, it has no a priori interpretation. Each row in V, so the k rows in V, represents a point or a direction in that C-dimensional feature space. In the previous section, we inferred the semantic meaning of VK via the spatial distribution of its corresponding UK. So under a clustering interpretation of NMF, each UIK serves as a weight associating a data point AI with the cluster center VK. So we can consider heat map locations as matching when they show strong weights with respect to the same centroid. For this reason, we consider that the matrix U encodes where and the matrix V encodes what, with the latter being represented in C-dimensional feature space. So C-dimensional feature space a priori is not visualizable, right? But we were curious to see, so, if V encodes what, let's first visualize what these key K V vectors actually encode. For that, we use a gradient descent visualization method of all A rows in V represents a point or a direction in that C-dimensional feature space. In the previous section, we inferred the semantic meaning of VK via the spatial distribution of its corresponding UK. So under a clustering interpretation of NMF, each UIK serves as a weight associating a data point AI with the cluster center VK. So we can consider heat map locations as matching when they showed strong weights with respect to the same centroid. For this reason, we consider that the matrix U encodes where and the matrix V encodes what, with the latter being represented in C-dimensional feature space. So C-dimensional feature space a priori is not visualizable, right? But we were curious to see, so, if V encodes what, let's first visualize what these key K V vectors actually encode. For that, we use a gradient descent visualization method of Ola et al. For this, we feed not several, but only one image into our pipeline and create our U and V matrices. And then we generate an input image that maximizes activations in that direction. Since a row of VK inhabits this space, it is interesting to see if these visualizations agree with our interpretation of the image via the high heat maps that we derived from UK. So let's look at some of the images we already saw before. So here's the Taj Mahal, an ICOT data set. And then here is the visualization. So the blue order of the visualization shows you actually which heat map or which V vector is considered with the corresponding U vector. So the blue highlights the dome of the Taj Mahal. And if you look in the visualization, you can actually make out some of dome-like structures. Here red is the same for the spires, highlighted with the red heat maps. And the same for the facade of the Taj Mahal, highlighted by the green. Similarly, you can do exactly the same thing with the elephants. So blue heat maps highlight the top of the body, which is also visualized with the corresponding visualization. And red is the body, kind of the ears that are shown in the visualization. Then the green is a little bit of the lower body. Here we can make out a few trunks. And then orange is the backgrounds, the floor actually, and here that actually also works quite well. If we go with ResNet 50, these actually, visualization are much harder to visually interpret what they actually mean. So blue is the background, and here you can say, okay, fair enough. We can see the trees. Okay, that makes sense. But then already, here is the upper body is in blue. That doesn't really make no sense. Okay, maybe with a lot of fantasy, you can have the trunks, but maybe also the legs. And the ground, yeah, the orange ground works better. And then the purple is somewhere in the middle, and yeah, with a lot of fantasy and forgiveness, you can probably make out some of the elephants. But it did inspire us to say, well, we can see some structure in these V vectors that could correspond to, loosely said, a descriptor of an object or an object cloud. So we tried it out on content-based image retrieval. First, we have instant-based image retrieval. That's relevant for images that are depicting the same instance. Or we can also have semantic image retrieval, which is relevant for images of those depicting the same class. So we experiment with both. And here you see the reference. I'm not going to go and discuss the method too much. You could look it up in the paper. And I just show you the results for semantic image retrieval. So we did the semantic image retrieval using the Pascal-Bock database, which has 20 classes. The results are in mean average precision at 30 to account for the imbalance of the classes. You can see that the image descriptors based on V, especially when using the BGG16 network, which is at the bottom, ResNet 50 is on top, outperforms all other methods for all classes, and sometimes by a large factor. So here you can see the, the other 10 ones, and if you look at the mean, we are doing better by quite a significant factor. I'll refer to the paper for the rest of the results. But to summarize this part of the presentation, V is a global dictionary representing important concepts, semantic concepts. We can use the rows of V to directly visualize using gradient descent. And the image descriptors derived from V are useful for semantic image retrieval. And if we actually add the spatial information of U, we get even better, very good performance on instant-based image retrieval. So now what about GANs? I have shown you what the uncovering semantic concepts in CNN looks like and its potential application, segmentation, localization, and image retrieval. Now, being able to also localize semantic parts in generative adversarial networks, or GANs, will open up a much bigger application field of semantic image editing. And so we went on this journey too, first with the following results. Let me first show you a video of a paper at CVPR 2 years ago. One thing I have to thank for these virtual conferences, at them we have video. And so we did know at this point that GANs achieve state-of-the-art image synthesis and that you could do very good global edits between two images that has been shown before. But we were curious, can we do localized editing of semantic objects, like in this case, the eyes using some target, or the nose using some target, and the mouth, like in this example. And of course, we didn't just want to do it on faces, we also wanted to do this on unaligned reference and target images, which you now see here for the car, and we can have the cabin, the bumper, and the wheels. So it's about changing local semantics in an image. We have a reference image, we have a target image, and we condition the style transfer, if you will, or the image transfers on the eyes, the nose, the mouth, and all semantic concepts. We do this by using exactly the same kind of thinking or kind of reasoning we used before. So we went to go and look for where actually is what encoded. So now not using NMF because of the architecture of the GAN, but using actually spherical k-means, we could go and analyze each one of the layers of the GAN using different Ks. So here you see an example using style GAN, the Flickr face database, the layer 32 by 32 for a K by 2. And you already see it's actually pretty good separation between faces and backgrounds. Same layer, K equals 3 already separates some semantic concept, mouth and eyes compared to, again, the background and the rest of the face. And with K equal 10, we get a good separation of all the facial features. With K equal 25, we oversegment. And similar to the layer of 128 by 128, k equals 25 is a meaningless clustering we observe. So we found actually that lower layers have greater control of shape and higher layers of texture. At an intermediate resolution layer, the 32 by 32 I showed before, faces are spatially disentangled into semantic objects. So we labeled clusters manually. This is done once offline per GAN dataset. Using a large batch of generated images, in our case it's about 200, we qualitatively evaluate the cluster mask different layers and ranks k, choosing the most semantic set. And then we go and find the best overlapping channel for these clusters. This is the channel for eye, nose, mouth. And now by manipulating these channels, we can make the local change to the semantics, i.e. we change the look of the person as shown in the video. So here, just to remind you again, I showed you the video, so I'll move on. We continued that work. So, found a way of actually not using target references anymore. So we can just take an image and find latent space direction in which we can move towards semantically meaningful edits. We optimize these directions based on a semantic segmentation, which can be supervised or non-supervised. And here again, a video showing you the different ways, different edits. Here's the mouth, and the eyes, the eyebrows, the nose, hair, background. Just because it's so cool. More mouth, eyes, eyebrows, nose, hair, background. So what about real image editing? Remember, these were GAN images that were all basically generated and they're not real images. So in the same paper, we actually also showed that using some GAN inversion techniques, you could take a real image, a real photograph, map it into the latent space, and then start doing the same editing, like the hair, the eye movements, or even However, at this point in time, GAN inversion is still not perfect. So if you take a person might have actually seen, like me, see that it doesn't quite work that well yet. So it is not ready. But hey, they continue to work. So let me conclude. Comprehensive neural architecture explainability and interpretability is still a ways off. We have progressed quite a bit. We're not the only ones. Many of you here in the audience are also working on this, and everything we do will help us get a step further. My point I wanted to make is some of the old tools for mathematics, image and video processing are really helpful in solving some of these mysteries. And even if you're looking for explainability, once you find a solution, that can actually help to new applications, a lot of cool things that actually improve the photographic experience for everybody. So I would like to thank again everyone here who's listening, who's still listening, and of course my two former in Edo Collins and now still of ESAN's PhD students and all the co-authors. These are the first authors, many co-authors from the lab, but also from outside the lab. And I want to thank them too. Bye-bye. Have a good day.
Okay, so this was the first invited talk. Unfortunately, Professor Sustrung is not with us because of some other appointment that she was not able to schedule. If you have questions, she is more than happy to answer to them if you send them by email. Now let's move on to the second challenge report. Andrei, this challenge report is on the efficient single image depth estimation on mobile devices.
Okay, so the second mobile AI challenge is fast and accurate single image depth estimation. And this is also a very important task for mobile devices, as this problem is used in many different tasks, in many different applications running on mobile devices, such as portrait, multi, mobile cameras, where depth estimation is used to distinguish between foreground and background that should be blurred, in augmented reality, in gesture recognition, and a number of other popular applications. And in this challenge, the participants had to design an accurate single image depth estimation model that can achieve nearly real-time performance on mobile and IoT platforms. The participants were provided with a dataset collected using the Z stereo camera. So this dataset contains more than 8,000 RGB depth image pairs, and depth images consist of 16-bit depth maps are scaled to VGA resolution. The performance of all solutions submitted in this challenge was measured using root mean squared error, using scale invariant RMSE score, and using the runtime on the target Raspberry Pi 4 platform. And on this platform, all submitted TF-Lite models were processing VGA resolution images. And the final score of each solution was computed based on its CI-RMSE scores and the runtime on the Raspberry Pi 4 platform. During the development phase, the participants were able to optimize their models both locally using EA benchmark application, where they were able to load and test the runtime of their models. And they also had a chance to upload their solutions to remote server and to get the runtime on the target Raspberry Pi device. This slide presents the final results obtained in this challenge. First of all, I should note that all submitted solutions were extremely fast. In particular, they all were able to process VGA resolution images on Raspberry Pi 4 under 150 milliseconds. And the top two solutions were able to achieve an FPS to achieve the performance of more than 20 FPS on Raspberry Pi 4. And this is quite impressive, since Raspberry Pi doesn't have any dedicated AI accelerators, so all execution was happening on its relatively low power CPU. So, and despite of this, both the first two solutions were able to achieve nearly real-time performance, and the rest of the solutions were still able to process, to predict the depth maps very fast. The first also in this ranking table, you can see a solution from Tencent marked with asterisks. This is the winner of the last year challenge. And we can see that this year the performance of top solutions was improved heavily compared to last year competition. So in particular, we see an almost 2 to 3 times increase in the final score. And for instance, the first solution is both more accurate and more than 2.5 times faster than the best submission from last year. So the challenge winner is Team TCL. They used quite standard model design for this task that consists of a unit-based architecture where MobileNet v3 is used to extract features from the input image. And to make the model efficient, they also downsampled input images from VGA resolution to the resolution of 160 times 128 pixels. And the model itself predicted depth map of quite low resolution, of 64 times 48 pixels. That was, these predictions were further resized to the target VGA resolution. And the entire model was trained to minimize scale invariant log loss function. The second solution from team AI-HAT used more or less the same design, so also unit-based architecture and with mobile NetWith3 features, but it proposed a more efficient decoder part. And same as the previous solution, it was downsampling input images by a factor of 4, but in this case, the predictions were even smaller. So the resolution was only 32 times 24 pixels, and then these predictions were upscaled to the target VGA resolution. And despite of this model was still able to make quite acceptable predictions. Maybe they are not very perfect, maybe they are a little bit rough, but because of these optimizations, the model was extremely fast. And if running it, for instance, on the recent mobile chipsets, smartphone chipsets, then it would be able to achieve more than 500 FPS when running it on GPUs or on NPUs. And the model was trained also to minimize scale invariant, logarithmic gradient, virtual norm, and robust losses. A more detailed information about these top solutions and all other submissions made in this challenge is provided in the challenge report. You can find it at benchmark.org/challenges. And if you have some questions, you can ask them. Otherwise, we'll switch to top submissions proposed in this challenge.
Okay, any questions? Okay, so if not, then thank you, Andrei, and let's proceed with the presentation of hybrid transformer-based feature fusion for self-supervised monocular depth estimation. And the authors are here, and we'll take the questions after the presentation. Okay, I will play for them the video. Okay, just one moment.
Hello.
Okay.
Welcome. This is a presentation on our transformer-based feature fusion for self-supervised monocular depth estimation. My name is Hemant, and this paper is a collaboration with my amazing collaborators, Maitreya Soinji and Professor A.N. Rajagopalan. Traditionally, depth estimation has been a big use of the topic. It entails the use of a stereo pair of images to determine point correspondence. These corresponding sequence is with the advent of deep learning, monocular depth estimation is possible with paired data consisting of images and depth space. Self-supervised monocular depth estimation is a challenging version of the problem where paired data is the This is the property of a polarly consistent. Wherein a field is warped onto another by estimating depth and force. Such pipelines are generally trained using photographic process between the warp frame and the ground truth. State-of-the-art self-supervised methods use an encoder-decoder architecture to estimate depth and force. Such networks are clearly convolutional. As depicted here, the convolution operation captures only a limited reflecting field per pixel, whereas the tension-based architecture has every other pixel contributing to the output for each pixel in the feature map. Depth is dependent on several global geometric attributes such as perspective. Therefore, it is suboptimal to use the convolutional architectures for the task at hand. Our objectives in this work are to capture long-range dependencies in image pixels by training a network for the intended task, to build an efficient fusion pipeline for features that represent global and local information, and to use the features to generate accurate depth. Coming to our method, as depicted in the figure, our model consists of a depth encoder, depth decoder, and a pose estimation network. Our pose estimation network has been borrowed from LTM2. All three submodules of our model are trained in tandem using photometric losses. The depth encoder further consists of the transformer-based global encoder, low-resolution local, and high-resolution local encoder blocks. The global encoder block consists of a transformer module and captures global contextual information in the training data. The local blocks use a series of ResNet and downsampling blocks to capture local information at different resolutions. Symmetric to the encoder, our depth decoder uses appropriate upsampling and transformer blocks to generate disparity maps of image dimensions. Our transformer block is a standard implementation of the transformer encoder and decoder with self-attention and sleep connections. Our feature fusion block uses a mask predicted using the low resolution local feature representation to combine all three representations using a series of convolutions and concatenation operations. Objective function used to train our model uses a smoothness regularization along with the photometric loss. The smoothness regularization ensures that the predicted depth maps are smooth, that is, the gradients among the pixels are very large. The symbols shown in the equations carry the same meaning as in the paper. Our qualitative results suggest an improvement over the state of the art, especially in terms of crispness of edges. This is backed by our quantitative results, which show that we outperform the state of the art in 4 out of the 7 standard depth estimate metrics. Evaluations show that neither the local nor the global features would have yielded similar gain in performance in isolation. Further, we show that it is not just the increase in parameters, but the efficient design choices and fusion that yield the shown gain in performance. Please refer to our paper for more details. Thanks for listening.
Okay, so if there are questions, the first author is here with us. So if you have questions, just unmute yourself and ask directly, or you can just write in the chat. Okay, so if there are no questions, then thank you to the authors. Thank you, Snehal.
Thank you, sir, for the opportunity.
Welcome. And let's move on to the next talk about light depth. And the authors provided a pre-recording that I will provide to you. And they will be here to take the questions.
Hello, everybody. This is Zhenyu Li. It is my pleasure to present our work, Light Depth, digging into fast and accurate depth estimation on mobile devices. This paper presents our solution to the mobile AI and a single image depth estimation challenge. We got the second prize in this track, and the paper is accepted to ECCV workshop. In this challenge, we need to consider the model fidelity and inference time. So we start to construct our solutions from the model design, data aggregation, and training strategies. I first present our network architecture. Following most of previous methods in monodepth, it consists of an encoder and a decoder. The reset modules on the input and the output are adopted to accelerate the inference on the mobile device space. And we also drop out the last decoder layer here. Generally, the model is trained on the normalized images, but we find that the normalization is time-consuming. So after the training, we propose to merge the normalization into the first convolutional layer of the network. It greatly reduces inference time. Here we present the double R crop augmentation strategy used in our solution. Compared with the commonly used random crop, we also randomly adopt different crop patch sizes during the training. It increases the diversity of the training samples. During training, we adopt various loss terms. While previous methods using the single siglog loss, we adopt additional gradient loss. virtual norm laws, and the robust laws. For more details of those law terms, please refer to our paper. Finally, we attempted to adopt the distillation strategy, which is commonly used to enhance the small model. For the teacher, we choose the swing transformer as the encoder. In terms of the distillation laws, we use the structure-aware laws, in which the similarity of the feature maps will be constrained. Also, instead of training of scratch, we adopt a double-stage training strategy to improve the effectiveness. Here, I present the results of the depth estimation challenge. We rank second in this track. Notably, our solution achieved the fastest runtime among our counterparts. As shown in the first table, our network is carefully designed with only 5 convolutional layers in the decoder, containing both 3 times 3 and 1 times 1 convolutions. Merging the image normalization can also contribute to the decrease of inference time significantly. Then we present the effectiveness of the double arc cross strategy. It can improve the model performance by increasing the diversity of the training samples. Then we show the distillation results. Interestingly, we find actually previous distillation strategies can hardly improve the model performance. We believe a more reasonable distillation pipeline for depths can be elaborately designed in the future. Finally, we present our model's inference time on various devices. Interestingly, it is CPU friendly, achieving a faster speed than the one on the GPU devices. So that's all about our paper. Thanks for listening.
Okay, so is there any question for the authors? Okay, so if no questions, then we move on to the next talk, the U-shaped transformer for underwater image enhancement. And for this work, I will play the provided video by the authors.
Underwater images frequently have problematic issues, such as color guests, color artifacts, and blurred details. Those issues could be explained by the strong absorption and scattering effects on light, which are caused by dissolved impurities and suspended matter in the medium. Therefore, UIE-related innovations are of great significance for improving the visual quality and merit of images in accurately understanding the underwater world. The existing data-driven-based UIE techniques suffer from the lack of a large-scale dataset containing various underwater scenes and high-fidelity reference images. So we released a large-scale dataset containing 4,279 real underwater images and the corresponding high-quality reference images, semantic segmentation maps, and medium transmission maps, which facilitates further development of UIE techniques. Besides, we reported an U-shaped transformer network for state-of-the-art enhancement. The network's CMS, FFT, and SJFMT modules could solve the inconsistent attenuation issue of underwater images in different color channels and space regions, which has not been considered among existing methods. Combined with the multi-color space loss function, the contrast and saturation of output images are further improved. This is the experiments and visualization results. The extensive experiments on available datasets validate the state-of-the-art performance of the reported technique with more than 2 dB superiority. This video demo provides the comparison results on real underwater videos. We compared our U-shaped transformer with 2 traditional methods and 2 recent deep learning-based methods. The raw underwater video was obtained from nature footage.
Okay, are there questions for the authors? Okay, so if there are no questions, then we'll move on to the next talk, the multi-page learning, looking more pixels in the training phase. So for this work, I will run the provided video.
Hello, everyone. Thanks for watching the video. Today, I'm going to talk about my work, multi-patch learning, looking more pixels in the training phase. Due to the limitations of computation capability and memory of GPUs, most image restoration tasks are trained with cropped patches instead of full-size images. Existing extensive experiments show that the model trained with a larger patch size could achieve better performance, since a larger patch size typically means larger receptive fields. However, it comes at the cost of extremely long training times and significant memory consumption. To alleviate the dilemma mentioned above, we propose a multi-patch method to expand the receptive field with negligible memory and computation increase. In addition, we collect 100,000 high-quality images of 1,000 categories, following ImageNet, from Flickr.com for low-level image tasks. Our method improves the quantitative performance by 0.3412 decibels on the validation set of Compressed Input Super Resolution Challenge, ImageTrack. Our contributions consumerized as 2 points. First, we propose a multi-patch method to extremely expand the receptive field in the training phase, which only increases negligible memory and computation. Second, we create a large-scale, high-quality image dataset for low-level vision tasks, named Flickr 2KL dataset, which contains 100,000 high-resolution images covering 1,000 categories. For low-level image tasks, there are already some high-quality dataset, like DIV2K, Flickr 2K. But these datasets only include a few images. It's not suitable for large transformer network. To better stimulate the ability of the network, we created a large high-quality dataset, which called Flickr 2KL. Our Flickr 2KL dataset contains 100,000 high-quality images. We first collect 200,000 4K resolution images that contains 1,000 classes using Flickr API. Then we filtered low-quality images by quality assessment metrics VQ score and keep the number of images in each category not less than 60. After filtering, our dataset contains 100,000 images, and the number of images in each category is not less 60. To improve the per-pixel quality of the images, we downscale the original 4K resolution images by 2 times. Finally, we get the Flickr 2KL dataset with 100,000 images of 2K resolution. This part is about multi-patch training strategy. For most low-level tasks, such as image super resolution and artifact removal, the networks are trained with cropped patches rather than the full images. The network can only look at the pixels inside the patches during the training phase, even though the network's ability is becoming much more powerful and the receptive field of the neural network is very large. Larger patch sizes usually result in better performance. However, due to the computational capability and memory constraints of GPUs, it is not practical to train the network with full images. In this paper, we proposed an easy but efficient training strategy. We regard the central patch and its 8 surrounding patches, 9 patches in total, as a patch group. We denote the patches in the group as P1, 2, P9 from top to bottom and left to right. Considering the spatial correlation of the patches, we flip the 8 surrounding patches before feeding them into our network. After getting the flipped patch group, we directly concatenate them as the network's inputs. The subsequent training is consistent with the traditional methods. We conduct ablation experiments with the DIV2K validation set. As shown in Table 3, our created Flickr 2KL dataset introduces 0.1395 decibels performance gain. In addition, our multi-patch model achieves a significant improvement of 0.2017 decibels compared with traditional patch-based training method. That's all I'm sharing. Thanks for watching.
Okay, any questions? Okay. So if you have questions, always use your unmute and just ask directly at the end of the presentation, or you can just write in the chat and then the authors will respond after the presentation. Okay, so if no questions, then let's move to the second invited talk of the day, and this is given by Professor Björn Omar from University of Munich. Björn, welcome.
Hi, good morning. Can you hear me all right?
Yes, everything is fine. So
you should be able to see my slide. Is that correct as well?
I'm saying that you started screen sharing. I still don't see the slides yet. Okay, now it's working. So the floor is yours.
Thank you. Thanks, Radu, and it's great to be with you this morning. This talk will discuss recent breakthroughs in powerful generative models, but also identify their very specific limitations. We will then discuss stable diffusion and further ongoing work to render generative models both lightweight and powerful so they can be used by everyone, even with limited resources. Just imagine the great power this little cursor here has. Well, you may say it's just a cursor, but data and machine learning have actually turned it into this. An interface to the digital world that allows you to search and find almost anything. But you can only get what is already there. And now imagine the infinite power this cursor would have if it could create what's not already there. If you could express an idea or describe an image, and this cursor would then render your idea without requiring any technical abilities on your end. So by merely typing what you want, you can then create a sunset over a mountain range and say it should be all on canvas, or alter its style and turn it into a vector image. You could also in-paint scenes, increase the resolution, or turn a sketchy rendering into something more artistic. Now imagine this tool would not require service of a big tech company, but run on your own computer and that of millions of others who were previously lacking the artistic skills. It would actually democratize the tools to creatively express yourself. For that, it was key to make interaction as simple as writing, I want this and that. And it was important to make the approach powerful, sure, but, and that sets it apart, it needed to be accessible. And with that, I mean not just that we published and released the approach open source, we also aimed at making it work on ordinary consumer GPUs with less than 10 gigabytes of VRAM. This allows the millions out there to use it as opposed to methods that only run on servers of big companies. Now, key to all of this is a learning algorithm that essentially extracts and compresses the essence and characteristics of billions of images into a small approximate model of the reality, or rather what is depicted in those training images. So we want to synthesize images. Yeah? There are numerous approaches, but they are all facing a dilemma. They want to, on one hand, maximize the quality, but at the same time, they have to trade this against the diversity in the data, needing to represent all the data that is out there. Powerful likelihood models now combine both the quality and the data coverage and build a bridge between both. Diffusion models stand out in particular as they require no normalization and therefore are flexible with respect to network architectures. Transformers have been used, generative adversarial networks, and so on. And these models now define the state of the art when it comes down to image synthesis. And so comes that basically all recent approaches to visual synthesis have been built on diffusion models. One more benefit is that they now finally have a stable training routine. They don't rely on the minimax optimization, which was tricky with generative adversarial networks. They come with a Latin variable, which allows us to easily edit samples, and they have a convolutional backbone typically, which provides for much higher resolutions than are typical with autoregressive models. But these models are expensive due to the long Markov chains that they have. And with that, I mean that during training, you take an image, and a diffusion model training would then proceed by adding noise, a tiny bit of noise, but do so in 1,000 steps, for instance, until all the signal is eventually gone when you move to the far right-hand side here. Now, with that, we've just removed signal. What's the point of that? Well, the point is that you would, in a diffusion model, utilize that as a self-supervised training objective and turn this process around. So you essentially use a denoising autoencoder, for instance, here, to take a noisy signal and learn to turn it into something which is a tiny bit less noisy. Now, the key to that working is that this denoising autoencoder is the same on all different noise levels, and it works at the same resolution. So what we are obtaining is essentially representations, intermediate ones here, which are not differently blurred, but rather differ in semantic granularity. So you start off with this highly detailed mushroom here, and then as you're moving towards the right, you're losing more and more of the features of this particular mushroom, turn it into something more generic. Now, the strength of such strong likelihood models is at the same time also becoming kind of a curse for them. They want to capture each tiny bit of the probability function, probability distribution of our training data here, even tiny modes with imperceptible details. And that means if you look at the rate distortion curve of what is learned from the data, you notice that most of their bits are actually allocated to details that are not perceptible to you and me. Differences here that you cannot notice in the images. And in contrast, the details that we would all care about, differences here between the person wearing glasses or not, their gender and the like, semantic differences, are encoded by comparably few bits. So what we want is kind of represented only very scarcely, and what we don't really care about gets most of the bits. So where should we go? The common solution to this problem so far was to simply scale up those models. Scale them up, with that I mean scaling up the memory, the model size, and with that scaling up the memory came hand to hand, and scaling up the compute, leading to models with billions of parameters typically. Now, besides not being kind of the most beautiful approach, that also means that we face problems when really looking at the data distribution, because the data distribution eventually has long tails, as you see here towards the right. There's lots of IKEA type simplistic images, but there are images when we move out to the right, which you would have a hard time capturing by merely scaling up this process because they are so rare in occurrence. At the same time, this also implies an enormous cost, not just in terms of money, but also in terms of carbon footprint and so on. And that is not true only for training, but most importantly, and that's what I want to focus on here, for inference. Existing approaches typically required server hardware for inference, which essentially precludes them from all the people out there that don't have this hardware out there, and fewer players that can utilize such approaches means that there's less diversity, typically reduces the creativity, and for research that means that there are fewer labs actually capable of pushing this technology forward. So essentially a monopoly on this crucial technology would have a critical societal impact. This is okay if the company has as its motto, don't be evil, might be still okay then, but what would we do if this is then carried on by different players who have also a lot of compute and which have different social standards. Now, that's why our goal was to democratize this research on visual synthesis by essentially rendering smaller models more effective. Now, the stumbling step towards that is that powerful likelihood models like autoregressive and diffusion models are very expressive when it comes down to long-range context. This is great, but this comes at a high cost when they want to model local details. Contrast this with convolutional neural networks. They have a powerful inductive bias, which means that they can only focus or efficiently focus on local interactions, but that they can do very effectively due to the small kernel sizes. Now, the idea was to essentially combine the strength of both approaches. The power of strong likelihood models to model long-range context with the effectiveness of this inductive bias of convolutional neural networks when it comes down to local details. And this motivated a two-stage approach. Where in the second stage, we have our diffusion model here, which has in the forward process this diffusion process, which adds noise to the image, and then trains a denoising UNet here to remove this noise in a lot of tiny steps until we end up with the signal that we started with. Now, the powerful sort of contribution here is that we are not doing this in the image domain, but rather we have in a first stage an autoencoder-like architecture, which takes the pixels and then encodes that to a latent space. A latent space which we obtain by running a convolutional encoder, which is great in efficiently covering local details, and compressing this by means of a discrete codebook-like representation, patch by patch, as you see here by this grid. Now, in contrast to VQ-VAE, for instance, the training objective is, for one, that we utilize a pixel-wise, on this patch-wise level here, we utilize a perceptual reconstruction loss rather than going for L2 or L1. And secondly, and most importantly, we utilize a discriminator, a patch-wise discriminator, which helps the model to favor realism over a perfect reconstruction. Now, this locally gets the most out of individual patches. If you then, for instance, put a transformer on top of this architecture, you get our VQ-GAN approach, which models the context between consecutive patches. Due to this autoregressive model, you can prepend, for instance, a text conditioning, and then conditioned on this starting sequence, complete and establish contextual relationships between your different patches. Now, this VQ-GAN approach turned out to not only give very decent qualitative results. If you contrast it here against the DALI approach, which actually came out a few days after this VQ-GAN approach, you see that the results are arguably crisper, but more importantly, this happens at a higher compression, meaning the model is smaller and even yields crisper results. And 4 times compression, as in that case, for a transformer architecture with quadratic complexity, typically implies a 16 times computational gain. You also see this in a quantitative comparison against the VQ-VAE and VQ-VAE2 approach, where VQ-GAN significantly improves on FID. Now, we have this two-stage approach here. In addition to that, it allows us to condition on text and images and so on by passing through an encoder. In our case now, typically CLIP, but could also be different encoders. And the important contribution here was that we now, in this UNet architecture, introduced cross-attention layers, cross-attention modules, which essentially try to do the denoising that the UNet does, but in a controlled fashion, controlled by this additional conditioning mechanism. So in each denoising step, you take the conditioning into account and push the denoising a little bit more in the direction that your conditioning wants. This conditioning can be very generic. So you could do text to image. You can also take a semantic layout and output images, or do super resolution, complete an image, or even turn a depth map into an image. When conditioning on a semantic map, we here observe that the approach, due to its stochastic nature, can sample from the envelope of possible images that correspond to this semantic map. For instance, different weather conditioning, different seasons, times of day, and so on, all corresponding to the semantic map, like these two examples here. Or you can change the semantic map and get different seeds. The approach has achieved state-of-the-art in class conditional synthesis on ImageNet, and also in image in painting, where due to the simple conditioning mechanism, you simply concatenate the original image with a mask which you want the algorithm to inpaint, to hypothesize or hallucinate what's behind this mask. And there it has also achieved state-of-the-art in painting. The model can, as said beforehand, also do text-to-image synthesis. And here I just want to highlight that due to its convolutional nature, it can be trained on a significantly lower resolution than we want to do inference on by simply sliding down this convolutional approach. What recently turned out to be very attractive to a lot of users seems to be an image-to-image synthesis guided by text. And here we utilize the very interesting approach of SD-Edit, where you take your conditioning image, add a bit of noise. You're not going all the way till all the signal is gone, but just a tiny bit, and then run the backward process of the denoising process of the diffusion model to conditioned on your text signal, then reconstruct the image. And with that, you can do some very quick sketches in a paint program, add a text prompt, and then turn that into an image. Or you can here change, for instance, the style and make it a little bit more Van Gogh-like. All that without much artistic skills. Now, a few tricks that I want to highlight if you're doing research in that direction as well. What turned out to be very important is classifier-free guidance proposed by Ho and Salimans, which essentially improves conditional image generation models, taking these conditional models and every now and then, typically 10 or 20% of the time, essentially eliminating the conditioning signal, and other than that, in the remainder, utilizing conditional signal. So it's the same model. You don't have to actually change the model, just during training, every now and then leave the conditioning out. Secondly, different text encoders. We played around also with different text encoders, and here BERT and CLIP style encoders. And here CLIP turns out to actually give a very decent compromise in terms of size. We want to run this on consumer GPUs, and trade-off to performance of the overall model. And lastly, and this is actually where Stability AI came in. They sponsored the computational on large AWS resources, but the recommendation is to not just do this all at once, but in different steps. Here, first try training on a lower resolution, on fewer GPUs, on a large data set, and only then, after this warm start, go for the actual resolution that you would then want to train on, and do so on first just selected images to get a kind of pure direction where you would want to go, and then ramp things up only afterwards. Now, this approach has spurred a lot of creativity. A lot of people are already using it, and I recommend this search engine that has been put together by others called lexica.art, where you can see what people have created with it. There are a lot of plugins out there already for Photoshop, GIMP, Blender, which allow you to combine that with the strength of the respective software environment. And last thing I want to just remember, which I just recently saw, there are people even doing video clips based on Stable Diffusion. And as you may have known, there's a lot of work also now going in the direction of videos and animations. So let me summarize. This latent approach to diffusion models and VQGAN actually combine the power and efficiency of strong likelihood models, the expressiveness of powerful likelihood models like diffusion models and autoregressive models in modeling long-range context with the efficiency of convolutions in representing the local detail. This means that the approach now during runtime becomes efficient in terms of memory and computational cost and runs on consumer GPUs. This has democratized the access and essentially unleashed the creativity of the millions out there, and it has rendered high-resolution image synthesis possible due to this convolutional backbone. Lastly, the generic simple concatenation and cross-attention conditioning that we proposed also has opened it up to a lot of further applications. Now, I see quite a few future directions. If you carefully look at those images, you see that there's still a lot to improve. Improve in terms of the Latin space autoencoder, which has been trained separately in our case, and that can definitely be improved. Going for larger models is surely important, and to an extent more important than improving the image representations. And lastly, going for more parameters as well. But the later of the two, both of these last two examples will evidently potentially forfeit the ability to run on consumer GPUs. Now, I want to give you a bit of context on where we are now presently going, and some approach, some work which is only going to come out towards the end of the year, this NeurIPS. And so far, I've basically asked the question how we can render powerful likelihoods model more effective. Now I want to transition and ask a more profound question, what we should learn with those models at all. And what do I mean with that? Well, if you look at a very skilled artist like Monet, when he was drawing and painting some trees, he was actually going out and looking at the trees as he was painting that. Now, what's the point with that? I mean, as Ronald Reagan so infamously once said, a tree is a tree. How many more do you actually need to look at? I mean, wasn't Monet good enough that skilled enough that he knew what trees are? Why does he actually need to step out? And we all know that he was a very skilled artist. So apparently there's a reason behind that. Nature gives you an infinite amount of sort of diversity, and you can utilize that as inspiration, but even more so as a careful signal when you're actually doing inference, so to speak, painting new images. Contrast this with how deep learning presently works. So we essentially take all that there is during training and stuff all of these little patches, these zillions of examples of flowers and trees and whatever else into individual weights, into individual neurons, and then we're done. And then we just do inference. We never look at images during inference time as an inspiration like Monet did. So what I want to advocate for is a paradigm shift. But if you closely look at work done by Alyosha Efros, Thomas Leung, like some 20 years ago, you see that this is more like going backwards and then into the future. Things which with neural networks these days, however, haven't been done over the last decades or so. And that is, we observed that powerful likelihood models are very expressive when it comes down to long-range context, but it wouldn't be good to have them waste their performance on local details. Now, what I want to hear advertised is not representing local details at all in a generative model. Instead, take a database of patch examples, which can be separate from the training data, take separate patches, collect those, and then during inference, look up those local details as you want to paint your image rather than taking them out of the weights of the neural network. So we here, for instance, took a patch database, which is disjoint from the training set, collected random patches, 9 million images from which we were drawing 20 million patches. And then the autoregressive or diffusion model can focus on what they're good at, learning the composition of those examples, but they don't have to learn the patches themselves. So how does training work? As usual with a likelihood model, you take samples from your training set and you want to reconstruct those. But rather than just trying to resemble this distribution itself, we here condition on site information, which are essentially the patches which we have drawn, nearest neighbors, for instance, to the patch that we want to reconstruct, patches that we draw from this database. And then I hope you agree that this makes this synthesis process, this process of drawing samples from this distribution much easier. Let's say you want to draw this eagle here, and these are the patches that you get from your data set. There are a lot of details that you now don't need to memorize in the model, and you just need to learn how to combine them properly. Now, we technically don't take those patches right away, but rather we take a fixed encoder, for instance, CLIP, and feed that as conditioning signal into our likelihood model. And both this encoder and the retrieval algorithm are both fixed. They're not trained with the model. Now, during inference, you can now simply swap this database and also change the conditioning. You can condition on a class label, you can condition on text without conditioning and draw from those databases. It's important to notice here that we don't require any access to the training data. These databases, as well as the training database, are different from the training set. And what's more, they can be even swapped during testing. And if you do so, I want to simply give you the take-home message. If the test scenario is more complicated, you typically see more benefits. So the more complicated the test scenario is, the more benefit you see from this semi-parametric approach. And I hope that makes sense, right? If you deviate from your training scenario, it evidently makes help to draw samples and be provided with related samples from this test set in that case. Now, this retrieval augmentation provides you now with a lot of flexibility. You can train a model on ImageNet and then fix this model. Yeah, don't alter the model, but simply swap the database that we conditioned on and swap from ImageNet over to Wikiart. And the model post hoc, without any training, becomes not a model that can synthesize realistic images, but more stylistic images, because it now draws the samples from Wikiart. Besides this flexibility, the approach evidently also allows you to do zero-shot text-to-image synthesis and give you your happy vegetables waiting for supper, or a tiger that's happy standing in the kitchen. But most importantly, you probably already wonder, isn't retrieval augmentation, having to draw samples nearest neighbors during testing, during inference, making the approach slower? And here the benefit is that the scan library that we utilize for patch retrieval, for approximate nearest neighbor retrieval, is actually super efficient. So from 20 million images within less than 100 milliseconds, less than tenths of a second, you can draw your nearest neighbors. And since the model now can become smaller, as you can see here, a number of parameters when you compare against state of the art, at the same performance or even then a higher performance, this means that the approach in effect actually becomes faster. For instance, like here, a 10 times improvement without sacrificing performance, because smaller models now become more effective and retrieving the nearest neighbors doesn't cost you extra. Now, with that, let me summarize. Retrieval augmentation essentially points to a novel direction, essentially not trying to learn the individual samples, individual patches in powerful likelihood models, but using them to simply combine those samples that you draw during testing. So retrieval augmentation with that leads to smaller models at an improved performance, and all of that by having the powerful likelihood models concentrate on what they're best at. Focus on compositions of the scene rather than learning local details. The approach, in addition to that, also allows for a very effective post hoc transfer of models to novel domains. And with that, I'd like to close. Thank you for your attention, and thank my wonderful team who made all of this work possible. And I'm happy to answer any questions if you have.
Okay, thank you very much, Professor Omar. Okay, we have a couple of questions. Maybe the best is if Jumanji Tropic, could you unmute yourself and ask your questions? Jumanji? Okay. Okay, so Jumanji is asking a couple of questions. So I will start from the last one. Could a retrieval augmented model get to the size of Stable Diffusion?
Could it what? Could it get?
Could a retrieval augmented model get to the size of Stable Diffusion?
To the size. The idea of retrieval augmentation is that you effectively could make the models even smaller with that, yeah, and with that even more efficient. Sure, you can start with the size of Stable Diffusion, but then further improve on that and reduce the size essentially, and that was the idea of retrieval augmentation.
Okay, another question is, so typically the latent space for the diffusion models is like 8 times smaller than the pixel space. Is there any validation to this?
So we evidently measured the size being that small. We also done in the paper experiments with different compression ratios. So I just point you to the paper, the VQ-GAN paper from last year, and the latent diffusion model paper, which is Stable Diffusion, from this year, where we have experimentation showing what happens if you change this compression ratio along the whole range of sort of different scaling factors.
Okay.
Can I ask a question?
Yes.
Thank you for giving me this opportunity. If I understand correctly, in the autoencoder, it used the activation GALU instead of ReLU. But many evidence shows the ReLU activation can create a sparse transformer, sparse model, and therefore we can compress the model more. Do you have a plan to maybe testing this idea? Just simply change the GALU activation to ReLU.
Yeah, we're evidently sort of exploring that further, different architectures there. So with the denoising autoencoder, we had previous work even utilizing transformers there, then utilizing UNet architectures like we've shown here. And this was definitely not the endpoint of what we're exploring. Same goes for the VQ-GAN encoder-decoder architecture there, where, as I indicated, there have been already work by others, but also by us, in improving this architecture further. I just recommend you taking a look at that. And apparently, this can also further improve performance of the model.
One more question. I have been playing with the Stable Diffusion model a lot. Given the same center, if you sample different initial random noise, you will get like a very different image, right? So the randomness of the image might depend on the initial random noise, the initial random noise ZT. So I'm wondering if we can add the randomness to the text file. So what I mean is that instead of provide the randomness through ZT, but we add randomness to the padding the randomness to the text embedding. So therefore, yeah.
So evidently, this is a feature. There is not a one-to-one correspondence between text that you condition on and the image that you get out. That's why you need this initial space that you sample from to, as I've shown you with these examples where I change, where I fix the semantic map, for instance, then change weather conditionings and so on, all based on the seeds. There have been approaches which fix these seeds and then potentially change the conditioning. And then with that in a more careful manner, change the output image. And together with that, I've already seen approaches which also in a more stochastic manner change the clip-based embedding there, the textual coming out of the textual conditioning signal to explore that space even more so. So yeah, this is definitely a direction that has already also been explored by others.
Okay, cool. Thank you. Thank you.
Okay. Any other questions? Okay. So while you are still thinking, I have another question. So do you think that it's possible to speed up further the diffusion models, let's say by a factor of 10?
I would hope that that's the case. And I've seen, again, work by others in this short amount of time that this has been out, where they have significantly more compressed the representations, which then typically implies during inference time this model becoming faster. If anything, research in convolutional architectures with binary networks and so on over the last couple of years has shown that typically this first shot is only a starting point for, and that's the beauty, right? Letting it out for the millions to utilize it. There's many more people having more interesting ideas, pursuing it further than a single research group could have. But the answer is yes, and I've seen already other people going in that direction and speeding it up and compactifying the models.
Okay, and speeding up also the convergence of the optimization?
The training. Now, training evidently requires you, if you want to be really great and you look at that more conceptual point of view, you essentially want to learn the PDF of all the world out there. And now for that, you evidently need to look at a lot of training samples. I've seen, much like, and that's another pillar of research in my group, deep metric learning approaches already go in the direction that they carefully select, and we had to do this ourselves, carefully select the data that goes into the training process. That's why I just highlighted under this tips and tricks section, that you typically do this in a staged fashion, like the samples that you inject into the algorithm. I see there's a lot of sort of ongoing work in figuring out how to better and which samples to better throw into the model to further improve training speed. But there's no free lunch, right? If you want to understand what all the images out there actually are, you need to look at quite a few of those. And that means that it's still going to take some time training. So this is not going to be as swiftly as inference anytime soon.
Yeah, but it's a very challenging and very interesting avenue, you know. We just want to improve it. Okay, so if there are no other questions at the moment, then we will stop here. Thank you very much, Professor Omar, and we are very happy to have had your talk. Okay, so if there are some other questions, Professor Omar anyway will be more than happy to answer to your questions if you send them by email. And yeah, okay, so thank you. And now let's move to the next talk, and will be the presentation of Andrei Ignatov about the
micro ISP. Yeah, first.
Yes, so will be a presentation of Andrei about the micro ISP, and let's see what it is about. Andrei, the floor is yours.
Okay, so before going to the fourth mobile EA challenge, we'll first present a micro ISP paper that will introduce you to this topic and provide a baseline solution for the considered problem. And the paper is called Micro ISP, processing 32 megapixel photos on mobile devices with deep learning. The current mobile ISP systems are very complex solutions that are performing different kinds of image manipulation, including image demosaicing, white balancing, image denoising, sharpening, and so on. Since the quality of raw mobile photos is still very low, the systems are the standard. Traditional systems are not able to improve all aspects of mobile photo quality, and as a result, in process images still suffer from different kinds of issues such as noise or a watercolor effect that is used to suppress it. And therefore, one would ideally want to replace the entire ISP system with a more powerful deep learning-based solution. Another problem is that this solution should actually process high-resolution photos directly on mobile devices. So, and in this case, high resolution means not like HD or full HD resolution. This means the resolution of 12, 20, 30, or even 50 or 100 megapixels, as the resolution of the latest mobile sensors is extremely high. And therefore, the designed model should be very memory efficient. It should be able to run on mobile AI accelerators. Otherwise, it would be infeasible to process large images on mobile devices. It should be quite compact so that we can bundle it with a default camera application. And of course, its computational complexity should also be very low. Otherwise, we won't be able to run it even on dedicated AI accelerators. So to design this model, first we had to come up with the data set that would be used for training it. And we collected a novel Fujifilm Ultra ISP dataset that consists of images captured with raw images captured with Sony Exmor camera sensors installed in the MediaTek Dimensity development board. And target high-quality RGB images were captured using 102 megapixel Fujifilm GFX 100 medium format camera. And on this slide, you can see some sample results, some sample images obtained with MediaTek's ISP system and the corresponding image from the Fujifilm GFX 100 camera. And the difference between them is quite dramatic. And Fujifilm is able to produce images that are excellent in almost all aspects of image quality, in almost all image quality aspects. Then, as we have the data set, we developed a novel micro ISP architecture, and its general, this architecture is shown on the slide. So the model is processing input data in parallel in 3 different branches that are predicting R, G, and B color channels of the RGB image. Moreover, every branch has only 4 filters in each convolutional layer. And this was done to achieve the minimum possible memory consumption by the model. Using lower than 4 filters will lead to a significant loss of information. So in some sense, this is the lowest possible number of filters that can be used in the model. This architecture also used optimized attention blocks, which structure is shown on the right. And the computational complexity of each block was approximately twice smaller than the corresponding complexity of a normal 3x3 convolutional layer, which means that these attention blocks are very computationally efficient, and running them is extremely fast. And the entire model was trained with a combination of MSC, SSM, and VGG-based perceptual loss functions. The final architecture is fully compatible with Android and API 1.2, which means that it is also compatible with the recent mobile AI accelerators. The size of the model is just 158 kilobytes, and the model consumes less than 1 gigabyte of memory when processing 32 megapixel images on mobile GPUs, which is actually very small. For full HD resolution images, memory consumption is even less than 100 megabytes per one image. So once we designed this model, we trained it on the collected Fujifilm Ultra ISP dataset, and first we performed visual observation of the obtained results. So you can see the full resolution images reconstructed with the micro ISP model in the 3rd column. Here you can see target Fujifilm photos, and in the 2nd column you can see the results obtained with MediaTek's default built-in ISP system. And one can notice that the micro ISP model was able to perform correct reconstruction of RGB images. White balancing, color rendition was performed quite nicely. The resolution of the resulting images was relatively good, and there were no artifacts at both local and global scales. And the reconstructed images, in terms of color rendition, they were closer to the target Fujifilm photos than the images produced with MediaTek's built-in ISP. When comparing texture-wise, the results generated with MediaTek's ISP and the images generated with the micro ISP model, we can notice that the photos rendered with micro ISP are surprisingly looking much more naturally. So in particular, we can see that the colors are much more vivid, and the texture is also looking much more naturally than the one of the photos generated with MediaTek's ISP. And the reason is that the standard handcrafted ISP systems are usually using various kinds of filters used to enhance local image texture, and at the same time they are brightening the images significantly. And because of this, the resulting photos are actually looking a bit artificial. So they exhibit quite strong watercolor effect, like this cartoonish texture rendering. And yeah, therefore, a bit counterintuitively, the results rendered with neural network are looking far more naturally than the results rendered with the standard commercial ISP systems. And therefore, overall, if we compare all image aspects, then the micro-SPA model was able to perform the same or slightly better than the standard handcrafted ISP system of the MediaTek platform. In terms of numerical results, micro-SPA model performs better in terms of Pearson and SSIM scores than the other compact architectures designed for this task. And as expected, it is able to process much larger images of resolution of up to 32 megapixels directly on mobile devices, directly on mobile GPUs. And it's not possible to do this with any other common efficient model designed for this task. In all other cases, the resolution is limited to 18 megapixels or even lower. In terms of runtime, the model was able to demonstrate a real-time performance on the majority of last generation high-end SoCs. So it was able to achieve more than 30 FPS on Snapdragon 888, Google Tensor, Exynos 2100 chipset, and on the last generation SoCs, the results are even better. And this shows that one could potentially use the system even for raw video processing, as its performance is sufficient for processing 30 FPS. Processing videos at 30 FPS. And this model is also compatible with the latest AI processing units, and we checked its performance on the MediaTek Dimensity 9000 mobile chipset, and you can see the results here. The runtime in this case, the runtime on its AI processing unit is 4 to 8 times faster than in case of CPU-based execution. But what is more important is that the power consumption, that the energy efficiency of APU inference is much better, especially when we are dealing with quantized model. And this is very important for on-device inference, as the battery of mobile devices, the capacity of this battery is quite limited, and one needs to use as low energy as possible in order the phone to be able to process many images without being discharged. And yeah, that's the end for this presentation. So overall, this micro-SPA model presents an important baseline for the considered learn smartphone ISP task. Are there any questions? Okay, if there are no questions, then we are moving to the Learn Smartphone ISP challenge. Okay, yeah, here is one question. How is the model performing in low light conditions? Well, in low light conditions, the model is still able to reconstruct colors and to reconstruct texture, but the problem here is that in low light conditions, the images contain a huge amount of noise, and one needs a more powerful model for performing image denoising. So in particular, In order to suppress noise, one should either first perform raw image denoising, and then one can also apply this micro-SP model and get acceptable results. Or one can use a multi-scale architecture that would be removing noise inherently. But yeah, in this case, this architecture would be significantly heavier. Okay, another question. It works, yeah, this model, 1 second. Yes, so there was a question from Michael Kudelsky. If, well, right now the model demonstrates real-time performance for Full HD images, and whether it would be possible to achieve real-time performance for higher resolution, for higher resolution images. Yes, it should be possible to achieve this, and well, if you check a benchmark ranking, then you'll notice that the latest generation APUs are becoming even more powerful than the APU used in the Dimensity 9000 chipset. So there will be soon a presentation of next generation AI processing units from all major SoC companies, and their performance, and you will see a huge boost compared to the current results. And if we are talking about processing high resolution images, then this means that we should probably be able to process to achieve real-time performance when processing 2K resolution images. As for 8K resolution images, it might also be possible to achieve real-time performance, but with a number of additional optimizations like quantizations and some extra low-level optimizations. And well, even if right now the performance would be slightly lower than 30 FPS, then in case of 4K image processing, then you can expect that maybe in 1 to 2 years, the performance of mobile AI accelerators will increase to an even higher levels, and it shouldn't be a problem to do this. Okay, so if there are no more questions, then 1 second. Then we are moving to the fourth Learn Smartphone ISP Mobile AI Challenge. So in this challenge, the participants were solving the task that was just introduced. It's the same end-to-end rotor GP mapping problem. The participants had to replace the entire mobile ISP system and achieve good runtime results on mobile GPUs, and being able to process raw Full HD images on mobile devices. The participants used the same Fujifilm Ultra ISP dataset that was introduced, and all solutions were evaluated using PSNR, SSAM, mean opinion scores, and the runtime of the media flight models was measured on the Snapdragon 8 Gen 1 chipset with a powerful Adreno GPU. And in this challenge, we had 2 tracks. In the first track, the final score of all submissions was computed based on the PSNR and runtime results. In the second unconstrained track, the results were computed only based on mean opinion scores. And during the development phase, again, the participants were able to optimize the architecture of their models with AI benchmark application. And again, since we used TFI GPU delegate in this competition, in this challenge, then the runtime that the participants were obtaining on their local devices was proportional to the runtime on the target platform. And this slide shows the final results obtained in the competition. The overall best results was achieved by Team Multimedia. The model submitted by this team was able to demonstrate both good visual fidelity and runtime results. So for full HD resolution images, it was able to process one full HD photo under 12 milliseconds, and at the same time achieve quite good PSMA under the same scores. So this solution is marked with asterisks since the original model submitted by this team had corrupted weights, and unfortunately, the authors were able to fix this issue only after the end of the competition. The best runtime in this challenge was achieved by Team Myalgo. In this case, they were able to achieve more than 150 FPS on the Snapdragon 8 Gen 1 GPU on full resolution images. Though, of course, visual and numerical results were substantially worse than the results of the multimedia team. And the best fidelity scores were achieved by Team Acacia first. Despite the fact that the solution was much larger, so in particular the size of the model was over 200 megabytes, it is still able to process one full HD image under, well, it takes approximately 1 second for this on the considered Adreno GPU, which means that one can potentially use this solution for HD resolution raw image, full HD resolution raw image processing. When talking about the perceptual quality of these solutions, then there wasn't a single model that was producing ideal results. So just some of the solutions were doing better in one aspect, some other solutions were doing better in some other aspects, like denoising or color rendition or texture rendering. It's quite interesting that half of the models demonstrated more or less compatible visual results. So we cannot say that there is just one solution that is doing much better than the rest of them. And all these results were unfortunately slightly worse than the results of the baseline PyNet model that was initially proposed for RotoRGB mapping solution for RotoRGB mapping problem. But yeah, these solutions are more efficient, and what is interesting is that, yeah, the solution proposed by Team Multimedia, as was already mentioned, it demonstrated not only good numerical results, but it demonstrated also one of the best visual results. And therefore, we are moving first to the description of the model proposed by this team. So you can see the architecture proposed by Team Multimedia on the slide, and it is using eRobConf block as a basic unit of this model. The structure of this block is also depicted below. And the idea here is that this block consists of a large number of convolutional layers of different size and shape. So in case of eRobConf 5, the size of convolutional filters is ranging from 1 to 1 to 5 to 5. And this allows to learn a diverse set of filters and achieve quite good numerical and visual results. And the main trick here is that during the inference phase, the entire block is merged into a single convolutional operation. And this operator is basically equivalent to the entire block. So you can just check the proposed reparametrization technique, and so the original block and this convolution, they are doing exactly the same way, the same stuff. But of course, if you're using only one convolution, then the efficiency of the model increases dramatically. And this allows the team to achieve not only good numerical results, but also good runtime on the target platform. The authors also used an additional channel attention module that helped the model to converge faster. And additionally, when training the model, first the authors train it to do image painting, basically to perform masked raw data. After performing these tasks, and they trained it to do ROT-RGB mapping with a combination of Charbonnier, cosine, similarity, and page losses. So overall, this is a very interesting architecture that is delivering quite nice results on the considered task. The official challenge winner is Team Myalgo. The authors based their solution on the last year's mobile AI top solution, and they further optimized its architecture by reducing the number of channels and by improving the quality of the dataset by removing heavily misaligned patches from it. And the model was trained to minimize L1 loss function only. And one other solution that should be mentioned here is a model proposed by Team NRSI. The architecture designed by the authors was based on the unit and hourglass architectures, and the exact structure of the model was obtained with neural architecture search. And the authors also used model latency as an additional penalty in order to get more efficient model at the end. And the final architecture was trained to minimize combination of L1, MSSM, resonant perceptual based, and color histogram loss functions. So a more detailed description of these architectures and other solutions proposed in this challenge is provided in the challenge paper. So are there any questions? Okay, if there are no questions, then we should probably move to the description of TOPS, to presentations of top submissions in this challenge.
Okay, thank you, Andrei. Let's move on to the next presentation. The authors are here. They asked for me to play their pre-recording.
Hello, everyone. Today I'm going to present the topic about residual feature distillation channel spatial attention network for ISP on smartphone. Traditional mobile ISP pipeline usually involves a sequence of steps including demosaiking, noising, gamma correction, and so on. Parameters and algorithms of traditional ISP are usually tuned and modified separately, taking into account the particularities of the corresponding sensor and optical system. Despite the extensive use of handcrafted ISP solutions, the end-to-end property of Learned ISP model makes it very competitive to learn RAW to RGB mapping directly to generate high-quality image for mobile camera. By learning RAW to RGB mapping to produce DSLR-like RGB image from mobile RAW image, Learned ISP model can offer an encouraging way to close the hardware gap between mobile camera and DSLR camera. Mobileye Learned Smartphone ISP Challenge were held in order to develop efficient and practical solutions. An EarnNet like PNet based on PyNet was proposed as baseline. Besides, SmallNet simply used several stacked convolutional layers and achieved the highest score. ZatNet utilizes the channel attention and spatial attention mechanism to boost the performance of Learned ISP. NuAutoDEX also offers some inspiration for Learned ISP task. Our proposed network consists of source feature module, enhance feature module, and recovery feature module. Source feature module leverages a single ECB layer to roughly extract shallow feature from raw image. Enhance feature module consists of two stacked modified RFDB for balancing effectiveness and efficiency. A long-term residual connection is added to avoid performance degradation and gradient vanishing. Finally, in recovery feature module, a depth to space layer is involved in the middle of two ECB layers for upsampling feature and recovering to the full size. And our loss function is a combination of Charbonnier loss and SIM loss. We widely employ the range parameter reasonable edge-oriented convolution block to enrich the representation capability and enhance high-frequency information extraction while remaining the efficiency. We incorporate extraction of the first and second order spatial derivative into the design of the block to enhance edges and details, and further extract the hidden information from the feature maps in training stage. We introduce a modified RFDB to build our backbone. Our modified RFDB is constructed by progressive refinement module, channel spatial attention layer, and one convolution which is used to reduce the number of feature channels. We use the block to yield better fusion of spatial and channel features. For quantitative evaluation, our proposed method ranked third in Mobileye 2022 Learned Smartphone ISP Challenge, which achieved the best image quality while remaining competitive on runtime. And for qualitative evaluation, obviously, we can observe that our results are better than others with less noise, false color, zipper, and checkerboard artifacts, especially in color boundary and texture area. We conduct a ablation study and compare our setting with another 3 variants. As we can see, stacking to modified RFDB using channel spatial attention layer and structural ray parameterization technique can bring a better performance, while runtime is acceptable. That's all. Thank you for you listening.
Okay, are there questions? Okay, if not, let's move on to the next presentation. Real-time under display cameras, image restoration, and HDR on mobile devices. Marcos, are you there?
Yes. Wait a second. Okay, so I'm having some problems now with the second screen. So if you can move forward, Radu, 1 second.
Okay, so we'll get back after the next presentation. So the next presentation is provided by Stephen Tell, is about computationally efficient neural network for real-time high dynamic range imaging. So
yes.
Stephen?
Yeah, hello. Just showing my screen.
Yeah.
Is that okay?
Yes, you can see it.
Okay.
Yours.
Thank you. So welcome to my presentation about CAN HDR, computationally efficient neural network for real-time high dynamic range imaging. So the aim of high dynamic range imaging is to produce information in dark and bright area of our scenes compared to traditional low dynamic range imaging by using more bits to encode each pixel. So in our case, we want to produce high dynamic range image using a edge device with only one sensor. So for that, we have to capture multiple images with different exposure time. Each images have different information. So to mail them in an efficient way, we propose the CAN-HDR network. The CAN-HDR network is a non-coder decoder architecture. First is divide the spatial dimension by 2 using encoder, Stridian encoder. We use an attention module in order to align the features of non-reference images to the reference one, so to decode the images. And the merging steps is done using only a sequential concatenation and fusion images. So, and finally, we got the original dimension using the pixel shuffle operators. So for the spatial attention network module, we use the block attention module. We did an experimentation to use some traditional attention, spatial, and channel attention module. And so we aim to get the same quality using a more efficient module. So SCRAM is basically a block attention module, which reduces the size of the inputs by 2, channel size. And so, as I said before, the pixel shuffle proposed in super resolution is used to get back our original dimension, spatial dimension. In order to get a similar quality than state-of-the-art network, we use knowledge distillation. We use the prediction of the proposed HDR-GAN network to teach our model as teacher for our model. And so we saw it particularly works well. We think it's because of the methodology used to make the data set, which focus more on foreground motion and less on background motion, non-controlled motion. So the ground truths in the data set have some blurry ground truths, blurry features. So using the prediction of the HDR-GAN helped our network to be more stable during the training. So we see on the right table that our network gets similar result to state-of-the-art network, and visually too. And we also did an efficiency comparison using full resolution, HD full resolution images, and on the Apple MacBook M1 neural process unit. We run all the network using that. And so we saw that our network is able to be run in real time. Also, we run our network as our main objective is to run on mobile phone. We run our network on Apple iPhone 12, and each can be run at approximately 25 FPS. And so thank you for your attention. And if you have any question in the future, don't hesitate to open an issue on the project pages. Thank you.
Okay, are there any questions?
I do have one question. Related to the HDR, how many, so as I understand, it's a single mode HDR, or how do you fuse the images?
Sorry, can you repeat the question?
So exactly how do you create the input image? From where do you combine?
We have the three images with different exposure time, and we merge all these images thanks to it's a convolutional neural network, encoder decoder, and we all work in 32 bits, and so finally it produces a final HDR thanks to a final after the pixel shuffle, a final convolution layer.
Okay.
Okay. So, any other questions? If not, then thank you, Stephen. And let's proceed with the next talk. And we have the third invited talk of the day is Professor Felix Heide from Princeton University and AlgoLux. And he mentioned that it's better to play his pre-recording, and he might be here for the Q&A session.
Thank you so much for having me. I'm really delighted to give today's talk about designing cameras in an end-to-end fashion to detect what I call invisible, that is imaging and vision in harsh conditions. Today's imaging and vision systems surround us in our daily lives. We use these for personal devices, in health and robotics, and in our self-driving vehicles of today or of the future. But to build really robust vision systems, we must handle edge cases. Edge cases can not only be edge cases such as classes that are really seen, for example, also weather conditions, as shown here, dense fog, where I'm showing you a histogram, or a capture campaign in Europe, where we capture a small amount of ultra dense fog. And it is challenging to use supervision of existing supervised models to tackle all of those edge cases, just in case these cases are need a very massive machinery to capture those cases. And also, we want to make sure that we handle those edge cases not only for one specific camera system. We have the ability to build up a very large system, very large training group that allows us to capture, re-annotate, some active learning in there. Do that for one particular system, for one camera generation, but also do that for different cameras for diverse applications. So let's have a look at one specific harsh case. This is a harsh case that doesn't happen that harshly. That is just nighttime imaging and computer vision. Here you see an example of the captures that today's grid systems, autonomous vehicles, have to handle. In this case here, we have very low contrast around discontinuities, lots of ambiguity in the scene, but also lots of ambiguity introduced in the ISP, in the post-processing, in the sensing itself, due to HDR capture conditions that we have to handle here. So it's not really only scene that it is, in fact, the whole chain, all the way from photons, from some source in the scene itself, all the way down to an image or perception. There is a typical imaging chain that could be found in some kind of vehicle, for example, where light enters the scene, it's focused through some optics in the sensor, which digitizes the light and gives us a digital reading that we then process in a complicated cascade of individual processing blocks in the so-called image processing pipeline ISP. That spits out an RGB that can then feed into a downstream network to more object detection. And so, as I said today, all of the edge cases happen anywhere in that signal chain, can happen in the scene itself, in the optics, in the ISP. All of these edge cases are really handled in the downstream neural network using supervised training. We know that that works. That is a good approach, but it doesn't really solve the problems where they happen. So the best practice is to use supervision to handle the edge cases. And that is not only because that is the most successful approach, but because downstream neural networks have differential. So we can actually add training data that covers those edge cases and then have our model learn to cover those edge cases. The earlier blocks in the signal chain, the imaging chain, are not necessarily differential. So we have ISPs that are not differentiable, sensor designs that are not differentiable, optics that are not differentiable, the scene itself is also not differentiable. So this makes it challenging. And so we have practice to manually design those blocks that are essential in an overall system. And this is done today by GoldenEye experts. Months and months of hand tuning, for example, the ISPs, parameters as an example. Then those experts design with the cross-domain expertise, those blocks, make them perform good with respect to traditional image quality metrics, and also sometimes visual inspection. So those blocks are manually designed, and it does not necessarily mean that they're optimal for vision applications and subject detection. This really goes for all steps in the imaging vision stack. So in this talk, I'll show an approach how we can take those blocks, ISP, for example, make it differential, make us enable us to optimize the weights, the parameters, the processing itself to perform better and to tackle those edge conditions, edge scenarios where they're oftentimes generated, where the ambiguities are generated in the earlier layers of the camera and in the scene itself. And I'm also going to show how we can even further down the line in the optics, how we can design customized optics, can really build an end-to-end system that goes all the way from photons in to detection out and optimize the entire camera stack. And even going one step further, I will show you how we can represent the scene with a virtual model and then think about completely different new ways how to do object detection and inference, for example, by matching observation as optimization. So let us first dive into ISPs. So I want to look at a computational camera pipeline that optimizes ISP for the edge cases. So we can at least rule out the edge cases that are introduced in the ISP itself. So an ISP, as I mentioned before, contains many complicated processing blocks with a large set of discrete and continuous parameters. And these blocks are oftentimes not different. So how do we make it different? This works in two steps. First, learn a differentiable proxy function, an approximation of the underlying ISP that mimics the ISP. So it takes as input raw images, raw sensor readings, outputs, and RGB. And then we take that proxy network and we fix its states, and we can then backpropagate gradients from a loss function that may be image or downstream network all the way back to the parameters inputs of that proxy. So we can solve it as an optimization. So let's first look at how we learn this differential proxy. So consider a black box function that is our ISP that takes as input raw input images and parameters, the individual ISP block parameters that affect the behavior of the ISP. Then what we do in order to generate a training data set that we can use in order to mimic this ISP is sample the parameter space, the parameters of this black box function. That gives us a training data set of parameters, input image, and outputs of that black box ISP. It could be a hardware ISP, software ISP, it doesn't matter. Now what we do is we take a relatively standard image-to-image network, UNet with some minor modifications, takes as input the parameters and the input image itself, and we generate then, we optimize this network to have behavior that we intend with this particular network, that is to reproduce the behavior of the ISP itself, depending on input I and a set of parameters P. So now once we're done, finally training our network on this training data set that we generate hardware ISP, we freeze the parameters of this particular network, and we keep it then as a function that mimics our ISP. But now the nice thing is this is a differential function that we can use to optimize the input parameters. This is the second stage. So we take this fixed network and takes the input parameters, the particular raw image we're interested in, and then we place a loss function on the output of that particular proxy ISP. Let's say, for example, we have a perceptual loss function that is defined on the output of the ISP and a reference output, a specific target value that we want to achieve. So for example, from simulated data. Then what we can do is we can take that task loss and backpropagate gradients from the task loss through the fixed neural network all the way to the input parameters. Find us optimal parameters that perfectly represent our target image, minimize our target loss function, solve a black box parameter optimization as a first order optimization problem using existing optimization algorithms, stochastic first order optimization. So now how do we use this machinery to go further to joint image processing and detection? So a relatively naive approach is to take a fixed neural network, a downstream neural network, object detector, for example, and concatenate that with our proxy. And then we have an end-to-end pipeline that itself is differentiable. We can define an IOU loss on the outputs of the object detection network. Now backpropagate the gradients all the way to the input parameters of the ISP. Optimize optimal ISP parameters for that particular IOU loss. We can even go one step further and we can include the parameters of the object detection network itself in this optimization, slightly change the optimization up so that we can use different learning rates, do some tricks on the learning schedules, but in the end, we can basically optimize for both the ISP parameters, hardware ISP parameters, as well as object detection network weights. And this is an approach that works extremely well. So even on a small data set, just to show some cool qualitative examples of the table to outperform state-of-the-art stacks that have been deployed in the wild. For example, here we reproduced object detections on the Tesla Autopilot stack that we reverse engineered, and you can see this version of the Autopilot stack looks relying quite heavily on data. There's lots of figure in there, detections, and can do really well even with a relatively small data set. We do some pseudo raw data input that came from cameras here. Even though we don't have the incredible amount of training data that Tesla has available, machine learning is not about it. We have benchmarked against them and achieve substantially higher available bodies on the large datasets that we captured. So here's an example, very different sensor, the AR21, and has kind of a harsh conditions, just mounted randomly. Different cameras can be done very efficiently with this approach because we in all of the parameters drawn here, all the way from low-level image processing blocks to There's another example in extreme harsh weather. You can see that image processing approaches jointly with downstream detection certain issues we have. Multi-sensor setups, for example, right up to being usable because of the heavy mix. So just a few examples that show you that this is a successful approach to overcome key challenges in vision systems. So let's go one step further down the chain. Look at how we can optimize optics together with the entire stack, together with the ISP, with the downstream. So today's optics design is done manually. Manual optical design tools such as ZMax or Code5. You see some of those guys, imaging and optics experts that optimize really elaborate optical systems and do well in these traditional tools. But key thing here is really that they're optimized in isolation for traditional mentalized loss functions that trace spots on this without consideration of downstream application. These modern tools are really awesome in the sense that we have a huge library of science that optics engineer can rely on, different that features different materials, all kinds of different applications for these optics. And they're really easy to use. But as mentioned before, the downside is that we cannot really easily propagate gradients through the optics. We will design the optics jointly with a computer vision stack. We overcome this by building again a proxy model, differentiable modeling of the point spread function, the statements for especially the varied point spread function, trace here through an optical system. By modeling these PSFs, we describe the optical system with a neural network as a proxy function for ZMax or Code5 itself. And so what are the optical design parameters? Can be individual radii, surface descriptions, the description parameters, can be different spacing parameters, different material types. So all kinds of different parameters can affect these optical PSFs, which describe the characteristics of the overall optical system. So now what we can do is similar approach like before. We can consider parameters, these parameters that I just mentioned, and we can generate a data set using Zemax forward ray tracer black box function, as far as we're concerned. Produce outputs that we can use for training, and use our PSF generator network, which generates a PSF of a certain field and a window. And what we have here as an architecture is, and we can identify the loss function to optimize that network, but what we have here as an architecture is a network that consists of an MLP and a convolutional encoder to produce those outputs. And as before, we can learn the weights of this network, proxy Zemax if you want so, by sampling through different parameter settings, and then using this as a training data set, optimizing the loss between the PSF net factor and to simulate a forward model with the complex Zemax ray tracer, and finally fix this. And again, what we can do is similar like the SP optimization, or as we can optimize for optimal PSFs. In this case, optimize for tight spot size. And you can see here the result of the optimization of the parameters, so radiance backpropagated all the way through the to the individual input parameters of the optical system, and we can do well design an optical system in this network. So we have validated this approach and built actually several optical systems for imaging, display purposes, object detection, traffic light detection. And each time we get a different tailored to the domain specific use case. So what we have here in this first case is an optical design that is optimized for natural image capture. But you can see here, if you look at the middle fields, that we get a design which has much narrower tail, so we have such a long tail. Nominal design, by the way, is a design which in this case here was designed over 2 months by optics engineers that were trained to do this, find the best design, and tweak all the Zemax parameters, optimizer parameters in the best fashion. This is what they came up with. We find a very different design. In this case here, we can see here has a larger f node, get a little bit less light efficiency through this one here, slightly peakier PSFs, and we can handle that on the construction side fairly efficiently. And the ISP gives slightly more noise in low light conditions. We can still recover that, but the overall sharpness here is drastically improved. If we jointly optimize this together for hardware ISP, we get a better output, which is visibly better here in this case. Again, yet another different ISP to optimize this with a neural network. Now let's have a look at automotive object detection. Entirely different PSF. What we get is a very uniform behavior of the PSF, especially the blue channel, and larger PSFs than the normal side. And you can see that this actually improves detection quite substantially, although we get slightly more blur. In this case here, the F number is actually lower. So we do want to make sure that we get more light here in this design for object detection, and we can on average do substantially better. Here is the last example where we have traffic light detection, so small objects at the periphery of the image. You can see here that for 6 degrees and 8 degrees overall extent of the sort of core tail of the PSF, which contains most of the energy, is contained to a smaller set of pixels, so we get less blur for those regions, and that helps to detect those small traffic lights. Is a qualitative example, and you can see here that we detect substantially better. In all cases, we've done a quantitative evaluation, detecting up to 5 to 10% improvement in the damage precision for these images. So now I want to look at sensors. We've looked at the whole chain from ISPs to optics, but I haven't talked about the sensors. How can we use sensors And the smart design of the whole sensors was new sensors to overcome some of the challenges that we have in the edge cases that we talked about at the beginning. So let us have a look at a scenario like this: harsh weather, where we have a lot of backscatter affecting severely LiDAR measurements. First response is reported, and at the same time, a lot of scattering. We see repeat capture, spatial capture. We can gate out some of these backscattered components affecting both stereo and LiDAR sensors by devising a new sensor that gates out some of these contributions. Gating works as follows: send out a pulse of light, and we only record light that comes back to the sensor at the given time. Here you see 3 gate slices, 3 different temporal offsets, 3 different temporal gates that capture in the scene. And you can see here that the first slice, we've gated out all the far components, path, very long path lengths. In the second slice, we've gated out early components and long components. Last slice, we've gated out a bit. So that allows us to gate out certain path of the light transport in the scene. We can take this sensor, bolt it on a vehicle, and then comes nothing else than a gated camera source, diffuse, flash, laser source, mount here below the bumper, and we add a camera. We can devise a 3D object detection architecture that uses these gated images in a very nice fashion. You can get 2D proposals out of these gated images because they're very high spatial resolution, other than existing LiDAR measurements. They are basically at the same resolution of RGB camera sensors. And at the same time, through the variations of the intensity indicated images that we capture, we have depth encoded. So they also have a direct encoding of depth at this high resolution. That can be used and get really nice 3D object detection results. And it works well in harsh conditions. Here you see an example of a night capture, which is challenging for conventional RGB pipelines, stereo pipelines, and the architecture works quite well here using this gate. Showing outdoor image here. There you see color-coded 3 little broken slices in red, green, blue. And here's some more harsh cases in dense fog. And again, completely different modality. Here we use a very tiny data set, 1,000 samples to train this number. But for fog doing at long distance, this approach gives robust predictions. Another scene for fog. This is pedestrian installation there. Here, overland drive, also very challenging, not much to get in E captures in this case, get nice results, which is in very, very sharp contrast to LiDAR, which do not work in this case with backscatter, and they have a low resolution at long distances because of the scanning approach. Scan LiDAR, scan. Now, another thing that you can do, this new sensor modality, which is train other models. For example, a model called zero scatter, which takes input RGB images, so affected by the haze scattered in the scene, and produce images that have this can on the resulting images that a dehazing network produces, define a loss that produces, simulates gated images, and then measures the difference to the actual gated image uses this as a loss function to train the network weights of this K-sig network, which works because these K detectors are not affected as much as other modalities by the backscatter in large sizes. Here's an example of this Cowan's tool, and you can see here that especially for long distances, we get really good K-sig results. This approach here under challenging conditions. These are all unseen scenarios. Here's an example in fog that shows you that you can do quite a bit this approach is an indirect way to supervise system imagery. So I've talked about different approaches that tackle the whole and vision chain all the way from photons in to the optics, to a particular sensor, to the ISP, a detection network to an output of that detection. But what I haven't looked at so far, what I alluded to at the beginning of my talk, is the scene itself. So how can we reduce the beauty of the scene, and the scene differential itself? This is what we're going to do here. Next last portion of my talk, which introduces the concepts of so-called neural scene graphs that we can use for inference and data generation. So let's look at a dynamic automatic scene, such as just a scene from Kitty. If you take a frame T at a given time, then what we propose is to model this entire scene with an implicit scene representation that's based on scene. So what is the scene? You consider all the dynamic objects in the scene, all of the vehicles here in this case, then they're all the nodes of this particular scene. The scene graph is nothing else than a directed axis graph, and at edges of that particular scene graph have transformations that transform the objects to their particular positions in the scene. Such scene graphs, seemingly very simple, are a very well-known concept in computer graphics that explored there for a while to model complex compound scenes that consist of many different objects. So how do we represent this entire scene? This image here, just an array of pixels with a scene graph, implicit neural scene graph. So we first take out one specific object here. Let's, for example, take the truck here of interest, and that now is a node of a scene graph. We assume that we have, let's just assume we have this bounding box comes with a tracker, for example. And what we can then do once we have a transformation of the bounding box, the 3D scene, is that we can shoot an array from the camera through this bounding box. And every location that we sample the bounding box, different sampling schemes we explore, we can sample the radiance, which we represent with an implicit neural radiance, representing this particular truck object. We can collect the radiance, can integrate it, and we get only the radiance that is reflected from this particular point on the truck. And we do that by introducing one model for all the trucks and all the vehicles. That is one implicit model for all of the objects which are from the same class. So now, what do we use in order to represent the radiance? We use a neural radiance field, a NeRF, super popular neural rendering approach. And what we do here is, instead of using a typical NeRF here, we implement it as a two-stage model where we give not only the location, the direction that we want to sample the radiance in, but also the location of the particular object, P here in the global scene, and a latent code. Latent code encodes differences between the individual object instances that we represent with our model, and the position that we can put here, P here in this case, makes sure that we encode global illumination effects depending on the position of the vehicle or the object that we want to represent in the scene, depending on the position where it is in the scene, depending on the illumination. So we add these two inputs to a conventional nerve that outputs color and opacity at every given location that we sample it at, and then we integrate those along array. So now we can do that for all objects in the scene, define them all as individual nodes with shared models. We use a few separate models for trucks and cars, then encode these individual nodes with the codes that we optimize for during the training time, and then generate pixels by accumulating the relations of all of these individual dynamic objects we have seen. So all of the dynamic objects are now handled by individual modified radiance fields that we model using. Now, what I haven't talked about so far is the background itself, static background that does not change. For that, we just use a plain nerve, but we sample it in slightly different ways or scales. We just use a set of planes, multiple planes that we sample this particular nerve at to get background components, static components in the scene that we model. Then finally, we have a full array representation of the radiance through the scene. We take all of the samples of the dynamic objects and static background objects and integrate them, which gives us a final nerve, gives us the full image that we want. So now if you want to represent a different frame of the same scene here, all what we have is move these individual node representations around, keep the background as is if we don't through the scene, and evaluate there again at a different location. So all of a sudden we have an implicit neural scene representation that allows us to modify scenes and change scene arrangements, scene configurations, generate entirely new scenes. And I want to show that here. So for example, we train our scene graph representation on a few videos from Kitty data set. We can add trucks, move them around, put them in different locations, rotate them slightly. All of this is consistent with the rotation cues, allows for occlusion and realistic. Here's an example of the illumination effect. You see the highlights move along with the vehicle. This is a coded representation. So obviously, background nerves move into the scene, change locations, vehicle location, then of captured words. Finally, once we have such a representation, we can take a graph and optimize it so that it matches an input image. So how do we do that? Let's say we have this as an input image, here the bound truth, bounding boxes are over the Kitty data set. Let's assume we have a neural scene representation or a scene graph, and it's correct. Then what we can do here is, so here we start with a sample of this particular scene graph, somehow initialized different approaches that we have explored. And then we optimize this scene graph to produce as an image that is as close as possible to the input image just by optimizing the latent codes and the transformations of the individual nodes. And that gives us a representative image of that scene and an entirely different approach of object detection. We can obviously also use neural scene graphs to generate very large training data sets of pseudo-simulated data and train feed-forward networks to do object detection, other perception tasks on these relatively large data sets. So in summary, I've shown you a number of approaches that tackle edge cases, harsh cases that you have to handle in perception systems, by designing systems in an end-to-end fashion, particularly looking at the entire camera chain, including post-processing, sensors, optics, and the scene itself. And I'm convinced that such perceptual cameras will allow us in the future to overcome a lot of the challenges that we have with today's supervised training approaches, especially when we're at the point when we can generate large data sets, pseudo-simulated data with neural rendering approaches. We're at the stage where we can use these training systems and can generate conditions which are the best to. So more decomposable, interpretable networks handling the edge cases exactly what's happening allows us to achieve some of these scenarios which are in fact superhuman vision capable, such as fog, snow, other challenging conditions that for us as humans are sometimes solved. So with that, I'd like to thank you all for the interest in my talk. I'd like to highlight that some of the results and papers that I've mentioned are all on my webpage, which is shown on the title slide and this last slide here. With that, thank you all.
Okay, so this was the talk of Professor Felix Heide. Unfortunately, he couldn't show up for the Q&A session. So if you have questions, please address them directly by email and he will do his best to respond. Okay, now because we are a bit behind schedule, let's move on to the next talk, and we have a challenge report on reverse ISP and row reconstruction. Marcos?
Yeah, okay, perfect. So actually, yeah, there was a delay with the previous presentation, but I will do first the UDC, the real-time UDC image restoration, and later I will introduce the reverse ISP challenge.
Okay.
Screen real quick. Okay. Yes, so there was a delay before, sorry for that. My name is Marcos Conde and I am a PhD student at the University of Würzburg with Professor Timofte. And I'm going to talk briefly about real-time under-display cameras image restoration and HDR on mobile devices. So during this workshop, we have seen the most common degradations that we can see due to the ISP, and that touches and it's related with the, let's say, the back camera from smartphones, but actually the new trend, given the selfies and all the frontal images that we have to take, is to include the camera in the front of the phone, usually above the screen, but now the new trend is to include the camera under the display, which actually increases the degradations because of the display that is above the camera. We can see this UDC image restoration problem as quite a complete restoration problem because we have our observation Y and we have the real image X, and we can consider certain blur artifacts given a K-kernel, certain noise, and clipping and tone mapping effects due to the dynamic range of the scene. I have to highlight and mention the solution that is state-of-the-art to solve this particular problem proposed by Feng et al. At CEPR 2021 called DiskNet and their dataset called SYNF that they collected using real PSFs from smartphone cameras. Now, most of the solutions that we find either use the PSF from the camera because we can estimate them, despite this quite difficult and you need access to the camera. Or the solutions like the one we propose here don't use the PSF or any kind of information about the camera, are completely blind, and most of these solutions are based on classical U-Net architecture. So we propose a U-Net architecture with different kind of dense residual blocks, and undilated convolutions, and we have the main branch, which is a unit, and an attention branch, which comes from some ideas from HDR to control the overexposed areas in the images. Now, the trick and what we proposed is how to distill a complex network that we define as DRM UDCnet into a smaller network that can fit into smartphones. So we can perform this restoration real-time on smartphones. And we call that network Light UDCnet or LUDCnet. And you can consult all the details about the distillation and the training in our paper. Now, I'm going to show you briefly some visual examples so you can understand how we can solve all these artifacts, the blur, the noise, and the diffraction artifacts due to the shallow display that is above the camera. We compare with the state-of-the-art methods from CVPR and previous years. And as you can see, the main problem that these images present, and I have to know that these images are synthetic, is the diffraction artifacts and high HDR. And successfully, we can solve that problem. But most importantly, as I mentioned before, we want to use these networks in smartphones in real time. And most of the solutions that I showed before cannot be integrated into smartphones. So we need to distill those solutions and create a compact version. What we can see here is what happens when we do that. When we go from DRM to LUDCnet, we can see that there is a clear loss in quality and performance, but at the same time, we really improve the quality of the input images. These are other examples, and we saw the error maps. And well, as it is quite clear in these examples, the majority of the errors are related with the diffraction artifacts, which is the most challenging degradation in this case. And the most important part of our work is not only to solve this problem using a blind method without requiring the PSF or any information about the camera. The most important part is that we managed to distill a complex model into a compact model that can be used in smartphones in real time. And related with the mobile AI workshop and previous presentations, we also use the AI Benchmark app to deploy these models. And we use 3 different commercial smartphones to measure runtimes and compare performance. And in our case, the proposed model has a certain decay in terms of SSIM, as we can see here, but we can process full resolution images in under 1 second in several commercial smartphones. And this proves that it is indeed possible to solve these problems in real time if the models are compact and efficient enough. And actually, something very interesting that you can check in our paper is that these models trained on synthetic data can generalize to real data. Okay, and now, without further ado, and if you have questions better after the next presentation, and also related with cameras, I will introduce the reversed image signal processing and raw reconstruction challenge. Oh, sorry for this. Okay. There's a problem. Organized by myself and Professor Timofti. And I will explain what is this new term, this made-up term that we define as reverse ISP, and why we want to recover raw readings from the camera. So first of all, I have to mention the related work and from where these ideas come. The Learned Smartphone ISP challenges proposed at different editions of AIM and Mobile AI workshops, and different methods to model the transformation from RAW to RGB, like Flex ISP from Professor Heide, Deep ISP, and PyNet from Andrei Ignatov. This transformation from RAW to RGB is well studied, and there are plenty of methods and papers about this, but we don't find a lot about the opposite, how to recover raw sensor readings from RGB and why this is important. So, as we all know, there are many problems that are performed in the raw domain because of the linear properties of these images. However, raw datasets are quite scarce in comparison with RGB datasets, and its collection is expensive, especially if we want to use DSLR cameras or modern smartphones. Most of the ISPs are proprietary, so we cannot know what is there, and therefore it's quite tricky to reverse engineer, let's say, the process and generate high quality raw images. And also, quite interesting is that in previous editions of the entire workshop, we could see that it is possible to recover parts of the hyperspectral cameras given the RGB measurements. So indeed, looks like we can recover information from the camera from the RGBs, and therefore we aim to establish a benchmark to solve this inverse problem. As previously explained by many speakers, the ISP is kind of a black box with many blocks inside. Usually, most of them are mathematical operations, not too much deep learning inside this black box. And there are some methods that, obviously, if you know these parameters from the camera, allow you to process these raw images and generate high quality pleasant RGBs. The problem is that we want a blind method. We don't want to use any kind of metadata or information from the camera, as this is the most common scenario and the real world scenario. And what we want to do is, given an RGB, recover each raw camera sensor readings without, as I said, any metadata. And by doing this, we can reverse the ISP transformations. Now, how do we solve this problem? What we propose is this challenge, and we use only smartphone cameras. Why smartphones? Because, as we all know, the smartphones cameras have a very complex ISP to, given the limitations of the lens, reduce the degradations that occur. We select mainly the Samsung S7 and the Huawei P20 Pro, but as I'm going to explain now, we also use the Samsung S6 and Samsung Galaxy S9. Now, participants have access to the Huawei P20 Pro data and the Samsung S7 data from the datasets that I previously mentioned. And the important part and how we evaluate these methods is we provide a first round test set that only contains images from the Huawei P20 and the Samsung S7. And then there is a second round test where we include images from these similar sensors from the same family. And by doing this, we can also prove, as we expect, the certain generalization capabilities of these methods to recover raw images from other similar sensors, given the RGBs. Now, this is the benchmark from the challenge, where we summarize the number of teams from more than 140 submissions. At the end, 11 teams made it to the final phase by submitting the code and fact sheet. And the highlighted teams are what we consider the winners of the challenge and honorary mentions. And as we can see, overall, depending on in this case on the camera, the reconstruction in terms of PSNR and SCM is quite good. Something that we have to note here is that the images from the 7 are not perfectly aligned, but aligned enough to use, let's say, a pixel-wise metric. But for the P20 Pro dataset, we really focus on SSIM, since the misalignment between the RGB and the RAW is notable. Now, how do we, or what kind of solutions have we seen in this challenge? Well, mainly we see deep learning. All of the solutions are blind methods, end-to-end deep learning methods, but there are kind of two directions. One direction that is partially model-based, and other direction that is completely end-to-end deep learning. Now, some visual results so you can understand the limitations of these methods to recover raw images. On the left, some images from the Samsung S7. And as we can see, all the solutions proposed from teams kind of match the color distribution of the raw image and also the details. But as I mentioned before, the Huawei P20 samples are not perfectly aligned, and therefore learning from not perfectly aligned pairs is way more difficult. And we can see that the models have certain problems to generalize when reconstructing raw images. And therefore, we can see some blur artifacts and also some color variations. What we can conclude from this challenge, first of all, is that it is indeed possible to recover raw readings from RGB measurements from the cameras. All the methods proposed in this challenge are model agnostic, which means that you can really learn how to reverse any ISP without prior information. And you can even learn to do that without having, let's say, perfectly aligned RGB and raw pairs. Most of the solutions proposed in this challenge are efficient enough to use them offline to generate or augment raw images from RGBs, but also many of the methods are efficient enough to be used online as an online augmentation. And the final conclusion would be that indeed approximating inverse functions of real-world ISPs is very, very tricky given the quantitation from the images, the HDR, and well, that we don't know what is going on inside the ISP, right? But I will let the participants to explain themselves their solutions. Learned reverse ISP with soft supervision. We'll have 10 minutes because we consider it the best paper. And then RISP-net, a network for reverse image signal processing, will introduce an end-to-end network, reversing image signal processors by reverse style transfer. Will introduce some concepts from style transfer networks applied to this problem, and overexposure mask fusion will explain exactly how to deal with such quantitation and HDR problems. Now, yeah, I want to thank everyone that is here, obviously sponsors of the challenge. I suggest you to check our project page because you can check all the camera readies from the papers. Some of them are not on archive, so if you want more information there, you can find the code from the participants, these slides, and the camera ready papers. And if you have further questions, you can obviously contact me and email me at any time.
Okay, are there questions? Okay, if there are no questions, let's see if the next talk, we have the authors of the next talk here. Okay, learn to reverse ISP with soft supervision. Okay, I will play their video, and they will be afterwards taking the questions.
Hi everyone, my name is Yue Zhang from Central South University. I'm very glad to be here to introduce our recent work. Our paper is named Learn Reverse ISP with Software Supervision, and our team is CSU. Raw image is signal channel raw data obtained from CMOS, which is the foundation for camera image. Cameras capture sensor raw images and transform them into pleasant RGB images using their integrated image signal processor. It is worth noting that the raw image usually has a high dynamic range of at least 10th power of 2, which provides more information and is helpful for image processors. Attracted by the beneficial attributes of raw images, some works carry out the research on RGB to raw images. Unfortunately, they focus on designing handcrafted model-based methods or complicated networks, while ignoring the spatial property of raw image, namely the high dynamic range. Although the high dynamic range of raw allows for a more detailed representation of the data, it may increase the difficulty of network learning. To make up for this problem, we propose to relax the origin supervision to a multivariate Gaussian distribution, instead of forcing the network to learn the given ground truth. As shown in figure, this brings two benefits. The learning goal of the network is softened, simplify the learning process, and the network could capture pixels around the given supervision during the training process implicit data augmentation. So in this work, we introduced a novel soft supervision-driven network, SSDNet, for RGB to raw mapping, and we propose new loss functions based on the soft supervision that enable the network to further cope with the learning of multivariate Gaussian distributions. Finally, we construct an encoder-decoder structure that incorporates convolution and transformer. Giving an RGB image Y, we apply SSDNet to get the reverse raw image X. And we can obtain the corresponding absolute error map E sub GT, where X sub GT is the ground truth. In fact, we relax the origin ground truth in conjunction with this error map into a multivariate Gaussian distribution as X sub SP, so that the network can fully capture the supervision information. To learn X sub SP, a simple approach is attaching a sub-network in the network, as shown in figure, and then use L1 logs, enable the whole network to learn the mean and variance, where E is the output of the sub-network. However, this approach is not really taking advantage of the learning distribution. For this reason, we propose a testing resampling strategy to enhance the restoration results. Specifically, we sample instance and average them to get the final results, but this approach brings additional computation costs. In contrast, we provide another training resampling strategy. We sample the supervision in the distribution as new supervision, X sub RP. In this, SSDNet would capture not a given supervision during training, but a large number of possible samples existing in the soft supervision, where alpha is a hyperparameter to balance learning targets. During training, we would attach a sub-network on the main network, the same as figure. While testing, the sub-network could be simply deprecated for saving memory. Then, we construct an encoder-decoder structure that incorporates convolution and transformer. The overview architecture is shown at the top of figure. The SSDNet is based on symmetrical unit architecture. SSDNet has 3 encoder stages and 3 corresponding decoder stages. Its basic building blocks of the encoder and decoder follow the same context fusion module, CFM. As shown in the left bottom of figure, CFM has 2 stages, respectively the convolution transformer mixed module and the feed-forward network. Next, we can see the experimental results. We perform extensive experiments to verify the effectiveness of our method to perform raw image reconstruction. To balance computational costs and performance, we finally choose the 7x7 kernel size. We verify the importance of the interaction operations, respectively the channel attention and spatial attention for self-attention and convolutional branches, as shown in Table 1. Both of these interactions are effective in improving the restoration performance. Top performance is achieved in combination. Soft supervision is another important element in delivering the effectiveness of SSTNet, as shown in Table 2. Since the test resampling strategy imposes an additional computation burden, that is not as simple and elegant as the end-to-end training resampling strategy. Therefore, we adopt the training resampling strategy by default. We submitted a result obtained via the proposed method to the ARM reverse ISP challenge, as shown in Table 3. Quantitative raw reconstruction results at the final test set of ARM reverse ISP challenge. Best results are in bold. Ours are in blue. Next, we compared our SSTNet with existing inverse ISP methods on MIT 5K datasets, as shown in Table 4. Compared with previous methods, our SSTNet has achieved the state-of-the-art performance. This clearly demonstrates the effectiveness of the proposed SSTNet. Finally, we leverage our learned raw reconstruction model to raw denoising, generating synthetic data using the inverse ISP model, and then use them to train the denoiser. We report our raw denoising results on the SIDD datasets in Table 5. Our method has achieved comparable results with the latest methods. Best results are in bold. In summary, we propose a new learning target and an effective network for data-driven RGB to raw learning. We first exploit the unique property of raw image, high dynamic range, by suggesting relaxing the supervision to a multivariate Gaussian distribution in order to learn images that are reasonable for a given supervision. Then, we propose the encoder-decoder architecture SSTNet, combined with the above two components. Our method achieves an effective RGB to raw mapping. In particular, our method achieved promising results in the ST track of ARM reverse ISP challenge. At last, we demonstrate the application of RGB to raw on a denoising task, implying that this research can be a valid tool for raw image denoising. So there are basically all the things about our paper. Thank you for listening.
Okay, the authors are here. If you have a question.
I do have one question, and then I will pass the torch to you that also has one question about this paper. So thank you for participating and for your solution. Very insightful. I want to know. So you do an experiment on raw denoising, and basically you take RGBs, you generate synthetic raw images from those RGBs, and then you measure and you prove that by doing this and training with synthetic data, you improve on denoising. My question is, which data set did you use to generate synthetic raws? And did you do it offline, or did you do it on the fly as an augmentation?
Thank you for your question. That is an imagement
Okay, so you use ImageNet to generate synthetic rows.
Yeah.
Okay, okay. And did you do it offline? Did you get all the RGB images from ImageNet and then generated rows?
The data is generated offline.
Okay, okay. Okay, thank you.
Okay.
And another question, yeah, why does the training sampling is, we believe that this approach is equivalent to adding very small random noise to the ground truth, which makes the network see many samples around the ground truth while learning. So essentially, this approach is a special kind of data augmentation. Yeah.
Okay. Other questions? So if there are no other questions, thank you. Thank you, Yuzhan. And let's move to the next. The next presentation is RISP-Net. And I have a talk that I can play for the authors, and they are around to take the questions.
Hello everyone, here I will give a brief presentation on Let's start. I will introduce the people in class. The first part is the view of our work. Usually, the image formation has pipeline with transmitting sensor data to human readable RGB images, and the reverse as task is to restore the raw data from the RGB images. This task is challenging due to the information load from converting 12-bit or 14-bit raw data to 8-bit RGB images, which is a typically irreversible operation. However, previous work as listed on the slides have typically involved some prior knowledge into the model, resulting in more complicated approaches. Here is a graph of NEF-like, a model proposed to deal with image restoration tasks. It achieved exciting results in the image deblurring task and the image denoising task. So it is natural for us to put forward a question that is, can NEF-like perform well in a similar raw imagery construction task? According to experiments, our answer is yes. Furthermore, to improve raw recovery performance, we enhance the basic work of NEF-like with two newly defined modules for the TOA and SH. In part 2, I will illustrate our method in detail. This is the figure of our network architecture. Similar to most image restoration methods, it adopts an encoder-decoder-based architecture. An encoder with multiple stages will learn the basic representation of RGB images, and a decoder with a number of stages will reconstruct the two images. Each encoder stage and each decoder stage utilize a stack of RSP blocks to achieve efficient feature transformation. Next, I will introduce the basic block of our RSP. We name it RSP block as demonstrated in the figure. RSP block divided into sequentially residual blocks. The first residual block is composed of a visualization, a 1-to-2 convolution, a 3x3 x-y convolution, a TOA module, and a 1-by-1 convolution. The structure of the three-order attention module namely TOA is shown in the green box. It contains three successive attention. That is the state attention, the spatial attention, and the channel attention, and the simple attention. These three attention options utilize to achieve efficient feature extraction by capturing the long-range dependencies among the features. Then let's look at the second residual block. It consists of a layer normalization, a SH module, and a 1-by-1 convolution. The full name of SH is Simple Activation Gate. Complementary to the TOA, SH can capture local dependencies among the features effectively, relying on its convolution operations. The next part is the experiments. These are the results of the AIM 2022 report SP challenge. with 1/3 place on both track P20 and track S7. We also do an evaluation study to confirm the use of the TOA and the SH modules in facilitating performance improvements. Here are the results. You can see that the SH module increased the required performance by 0.03 decibel, and that the TOA module should bring another 0.13 decibel performance gain. Okay, I will give a brief conclusion now. In this paper, we developed a global management level platform with effective TOA and SH modules to execute the reinforced ISP task. Extensive experiments show that our method achieves state-of-the-art performance for the reinforced ISP task, which is of great benefit to the downstream tasks. Thanks for listening.
Okay, any questions? We have one of the authors, at least usual, with us.
Is there something? Yeah. Otherwise, yeah, I do have one question you about your method, and thank you also for participating. So you showed one table, or your colleague showed one table in the presentation where with an ablation study of the blocks. This was one of the most complex architectures presented at the challenge, and I wanted to know, in terms of complexity, how much does complexity increase when you use this third order attention?
Okay.
Sorry, can you repeat the question again?
So when you use the third order attention, how much does the model complexity increase, at least in terms of parameters? Or if you calculated flops, that would be also good.
Let me see. I remember that using the TOA module, our parameters were add a lot. But I didn't remember clearly the exact number. So can I provide the exact number later?
Yeah. No problem. It's okay, and I'm pretty sure that in the paper you mentioned the ablation. So I just wanted to know how would you compress the network further, because with the channel attention and the spatial attention already following a NavNet architecture is already quite stacked, and with this third order attention, how would you reduce the number of blocks and parameters overall?
I need some time to think the question. Can I answer it later?
Yes, no problem. You can.
Okay, so if no other questions, then let's move on. Thank you. Shall we go?
Thank you.
Okay, the next talk is about reversing image signal processors by reverse style transferring. And I have the presentation from the authors.
Hello everyone, I am Furkan Kınlı from Özyeğin University. With my colleague Barış Özcan and my supervisor Professor Furkan Kıraç, we have participated to in 2022 Reverse ISP Challenge to test our idea on this specific problem. In this study, we have applied reverse style transferring strategy for reversing the image signal processor operations. A standard RGB image can be obtained by feeding the raw data acquired by the camera sensors to the ISP pipeline. Data-driven learning methods mostly use sRGB input images. However, in previous studies, the raw images are found to be better suited for ill-posed low-level vision tasks, such as denoising, HDR, or super resolution. Also, there are very few raw image datasets that are available for deep learning-based methods. In the literature, using synthetic data for training the deep learning models is arguable practice. To improve the synthetic raw image quality, we can estimate the raw image from the sRGB data when attacking low-level vision tasks. AIM 2022 Reverse ISP Challenge aims to obtain a network design or a solution which is capable of producing high-quality results with high fidelity with respect to the reference ground truth. We have participated to this challenge in order to test the idea of modeling some disruptive or modifying factors as a style factor. We define the problem of reconstructing raw images from sRGB input image as a reverse style transfer problem. Assuming the raw format is the original version, any visual change related to the image signal processor's operations can be considered as an additional style factor injected into the original version. Following the idea in our prior work, we can model the effects brought by the ISP operations as the style factor and remove these injected changes by directly reverting them back to their original style. To achieve this, we propose a novel architecture, namely RST-ISPNet, for learning to reverse the ISP operations with the help of adaptive feature normalization for transferring the style information. This figure demonstrates the overall architecture of our proposed strategy for this task. For architectural details, please refer to our paper. In this study, we have used two datasets in our experiments, which are provided by the challenge organizers, Samsung S7 Deep ISP dataset and ATH Huawei P20 dataset. Both datasets contain raw and sRGB image pairs, but the instances in P20 dataset do not align completely. We have measured the performance of our proposed architecture with two metrics, PSNR and SSIM. During our experiments, we have used ADAM optimizer with 10⁻⁴ learning rate and batch size of 8. Our experiments have been done on 2 times NVIDIA RTX 2080 Ti GPUs, and we did not use any additional data for training and any ensembling strategy for inference. Let's look at the quantitative results. This table summarizes the challenge results, and our method is not competitive in the rankings. Although our results do not seem as competitive among the other results, we believe that investigating the idea of modeling the disruptive or modifying factors as the style factor is an important and open to improvement approach for this problem. For visual comparison, our proposed solution does not have superior performance on the task of reversing the ISP operations. According to our observations, using adaptive feature normalization for removal leads to losing the high-frequency details in the output. Even if we have tried to use wavelet-based discriminators for our adversarial training, yet it still gives out the performance. The problem in our results still holds for track P20, even it's far stronger than the one that we faced for track S7. The blurring effect mostly leads to losing the high-frequency details in the output, so the decrease in the performance for challenge benchmark. We think that the alignment issue among the pairs for this dataset may lead to amplifying the problem in our strategy. Also, another reason for the amplification of this issue could be to use an adversarial training, since the real and fake image suffer from being exactly the same for the discriminator, and it does not help the training at all, even making it worse. To summarize, we thank the organizers for this challenge, since we have had a chance to try our idea for this problem. In our approach, removing the effects of the ISP operations by feature normalization leads to losing the high-frequency details. Also, the alignment problem in the data amplifies this problem. Overall, we need to reconsider the use of discriminative regularization on learning style factor. Nevertheless, we believe that the style of being sRGB is successfully reverted back to the style of being raw in our final outputs. This is the end of presentation. Thank you for listening.
Okay, unfortunately, the authors are not with us at the moment. So if you have questions, better address them by email. So now the next talk is the paper ID 361 on overexposure mask fusion, generalizable reverse ISP multi-step refinement. So is any author here with us? Okay. So I'm repeating. Is any of the authors of overexposure mask fusion paper with us? Present the work. Okay, so if no one is here, then this was the last scheduled presentation before the lunch break. Now we have a 25 minutes break, and then we'll resume with the fourth invited talk of the day on neural inverse rendering that will be provided by Dr. Pratul Srinivasan from Google Research. So in 25 minutes, we'll resume with Dr. Srinivasan from Google Research, an invited talk on neural inverse rendering.
Hi, Pratul.
Hi. Are you able to hear me well? I can't hear you.
I can hear you, but okay.
Hello? Is the audio okay now?
We are hearing the echoing. There is echoing in your.
Is this any better now or no?
Still echoing.
Okay, let me. Is it just a headphone issue maybe?
Could be something from the drivers.
How about this? Is that better?
No, still the same.
I've been changing the microphones. How about this? Is this any better?
About the same, not changed.
Please try no headphones. Let's try.
Okay.
Hello? How about this?
No. Now it's even worse.
Even worse. Oh no. What should I do with that? Maybe try moving inside and see if that's any better.
Okay.
Does that improve at all inside?
Okay. Now
is it okay now? Is it acceptable better?
Okay, it's a little bit better. It's less noise, but I hear echoing.
I'm not sure what to change to fix that.
Okay, so maybe the best is if you are putting again the old headset.
Yeah, let me try that again. Yeah. Okay. Just give me a second. I'll grab some things. Was this any better?
Now it's still a little bit of interruptions and echoing.
There should be no background noise. No, I'm not sure what to.
Okay, I think that
Let's change to fix it. Sorry now.
It's stabilizing a little bit. It's fine.
Okay, yeah, hopefully that's. Okay, let me try one more thing with no. How about this? Is this any better?
Yeah, much better.
Okay. Okay. The trick was
now
inside no
working. Yes. Okay, so I will stop my sharing and you could start your sharing.
Okay, great. Yeah, sorry about that.
No problem.
Okay, so one option is to connect to this workshop through your phone. So you.
He solved. Now we can hear him properly, Andrei.
Yeah, so yeah, hopefully audio is working well, and then is the the screen sharing looks fine?
Yes, it's working. Perfect. Okay,
great.
so
Awesome.
We are about to start the afternoon session, and the first talk is invited talk, and we have Dr. Pratul Srinivasan with us, and he will give a talk on neural inverse rendering. Okay, now I think without any further ado, Pratul, the floor is yours.
Great, thank you. Yeah. Yeah, maybe I'll just quickly, just to get started, I'll mention a quick little about myself. I recently graduated from a couple of years actually now. Since I graduated from my PhD, I worked at Berkeley with Professors Ravi Ramamurthy and Ren Ng, and worked on a lot of problems of interface of computer vision and graphics, and specifically like inverse rendering, view synthesis kind of problems, and that's what we'll be talking about today. And right now, I'm a research scientist at Google Research, and I work with John Barron, Ben Millhall, and Peter Hedman. And so a lot of the work I'll be talking about is shared with some of them, as well as a lot of other collaborators. Cool. Yeah, to set the stage today a little bit, I'll focus on a subset of computer vision problems. And this, you can think of the problems that fall into the subset of problems as inverse rendering. And so by that, I mean that, okay, so let's break that down a little bit. By rendering, I mean that we have, there's a function or some procedure that takes you from a 3D representation of a scene to rendered images of that scene, given a camera viewpoint. And so as we're visualizing here, you can visualize maybe the geometry from different viewpoints. You can render the color from different viewpoints. And by computer vision as inverse rendering, I mean, I'll focus on the problems that what we're trying to do is invert the rendering procedure, right? So what we've actually observed are pictures or captured or rendered images of the scene, like we're visualizing on the left. And by inverse rendering, I mean, we want to invert this rendering procedure. So to go from captured images to a 3D representation of the scene, such that you can use this 3D scene representation to re-render the scene from different viewpoints, as I'm showing this example. And even more than that, right? In addition to re-rendering the scene under new viewpoints, you might want to do things like change other scene properties like the lighting, like we're visualizing on the bottom left, right? So you can see that this pinecone scene is we've captured it from a handful of images, and we're rendering it from new viewpoints, new environment lighting, point lighting, and so on. Okay, so and then the class of solutions I want to focus on today are frequently called like optimization-based inverse rendering, or analysis by synthesis, or even render and compare. So these are all words that kind of mean the same thing. And what they mean is that we're going to endow like this 3D scene representation with some parameters theta. And in a optimization-based inverse rendering or analysis by synthesis-based inverse rendering approach, what we want to do is just take the scene representation as described by some current set of parameters theta, render the images from the viewpoints that we've observed them, or viewpoints or lighting or whatever the setting that you've observed these images from, and take a look at the rendering loss and backpropagate the rendering loss onto the parameters of the 3D scene representation theta. So the overall approach is very simple. All you're trying to do is mostly gradient descent on these parameters that describe the scene representation to minimize the loss of re-rendering the images that you've actually observed of the scene. And even more specifically, I'm going to focus on a set of approaches that you can think of as neural fields. So neural fields as the specific kind of representation that we're going to focus on for these computer vision as inverse rendering tasks. And I'll break down what I mean by neural fields in a second. So yeah, this concept is frequently called neural fields or coordinate-based networks. And the overall high-level idea is that you can use a fully connected neural network or multilayer perceptron or MLP that just takes in a continuously valued coordinate in the scene functions domain. So for example, like we're visualizing here, this like scene of a bulldozer, you might have a continuously valued 3D XYZ position of a point in the scene and maybe inside the bounding box of the scene. And we're going to have a function approximator that's going to take that continuous value 3D coordinate, and it'll output a description of the scene at the specific point. Okay, so then the logical question is, what would you want to store at any point to describe the scene? And today I want to focus on a spectrum of approaches. So the idea is that based on actually how you want to edit the scene, in the sense that what do you want to render at test time, what you want to change about your renderings, that'll lead you to what you want to actually store in the neural field at any point. So for example, on the leftmost of the spectrum, you might say, all I care about is taking my 3D scene representation and rendering it from a set of different viewpoints. And on the right end of the spectrum, we're saying, what I want to do is take the 3D scene representation and render it under different viewpoints, different lighting, different materials. Okay, so let's start with looking at how would you want to what would you want to endow a neural field description of the scene if your goal is just to vary the viewpoint after you've optimized the representation of the scene. Okay, so on the approach I'm going to talk about for this end of the spectrum is NeRF, for neural radiance fields. And I'll just provide a brief overview of that before getting on to the rest of the spectrum. But so in the case of neural radiance fields or NeRF, what you're going to store in the neural field at any point is the volume density and outgoing or emitted radiance of particles at a location. Okay, so quick overview of NeRF is NeRF's project that I worked on at Berkeley with my colleagues Ben, Matt, John, Ravi, and Ren. And at a high level, you can think of NeRF is going to represent the scene as a volume, and you can think of it as a cloud of tiny colored particles. And to render a scene that's described as a volume in this way, we need to think about, what if you have a scene that's described as a volume, what are the physical effects that you want to represent? So volumes can absorb light. So for example, in this picture of smoke, you have light that's arriving from behind the volume, behind the smoke, and it's being absorbed before it can reach the eye. Volumes can scatter. So the fluffy white appearance of clouds is due to essentially light being bounced in all kind of directions and being scattered in the middle of the cloud before it makes its way back to the camera of the eye. And volumes can emit light. So like in this case. In NeRF, we're actually going to ignore the scattering component and model the scene as just a set of volumetric particles, continuous field volumetric particles that absorb and emit light. And so the representation of NeRF is that at any point continuously valued 3D location in the scene, you'll have a color that's emitted from particles at that location along a viewing direction. So for example, the ray that's going through the camera in this example, and a volume density, which we'll call sigma here, which just describes the local density of particles at that location. And so you have the input is a point, continuously valued 3D point, as well as a direction that you're looking at that point from. And NeRF uses a positionally encoded MLP, which will describe the color that's emitted by particles at a location along that viewing direction, as well as the volume density of particles. And what you do to render a ray is that you just query this representation at a bunch of points along each ray. You get the color emitted by particles at each of those positions, as well as volume density. And you can combine them all together through a standard volume rendering integral estimate. And so the specific math isn't going to be very important for the talk here, but generally you could think of the final color that arrives at a ray that goes through the camera as a weighted sum of the individual colors of that the particles of light emit at different positions along the volume. And the weight is it's a product of two factors. One is how much light is blocked earlier along the ray, and one is how much light is contributed by that specific segment. And as we mentioned before, in this analysis by synthesis kind of approach, what you do is that we just train this MLP to describe the volumetric scene by looking at the images that we've observed of the scene and using gradient descent on the MLP's parameters such that it best reproduces or re-renders all these images. And here's some examples of scenes that you can reconstruct using this kind of approach. And so, as we can see here, NeRF-based methods are able to optimize super detailed representations of complex scenes with fine geometry and appearance details. But because we've selected this specific representation for what does the neural field store at any point as emitted radiance, it fixes us to only being able to render the scene under changing viewpoint, right? We have no way of trying to figure out how light interacts with the scene to figure out how the scene would look like from a different lighting, for example. Okay, so yeah, if we're maybe interested in rendering a neural field of the scene that allows you to change lighting and material properties, let's look at like how we would want to represent the scene in that example. So the example I'm going to use here is what you can think of as a neural reflectance field, and I'll describe that a little bit more. But a neural reflectance field, instead of just volume density and emitted color, I'm going to the field will store volume density, something you can think of as like geometry, local geometry orientation, or a normal vector at any point, as well as parameters of a BRDF, or a function that just describes how what is the ratio of incoming light, the ratio of light that's reflected along given any incoming and outgoing directions. Yeah, so let's break that down a little bit more, right? So in NERF, as I said before, NERF represents a volume of particles that emit light, right? So here's like the soy visualization of a cloud of particles that are emitting light. And to render a scene, you just sample a bunch of points within the volume, and you ask how much light is emitted by these points along towards the viewing direction, and you kind of integrate that. And this doesn't really let you simulate how light leaving a point might change with new lighting conditions, right? All we have is the neural field is saying how much light is emitted by points at this location along this direction. And so if you want to like now also instead of just editing the viewpoint, you want to maybe edit the lighting, you need to be able to answer this question like, how does light leaving a point towards the camera change? How does the reflected light change with any new lighting condition? So the basic first step you need to take is replace this model of particles that only emit light with a model that describes how particles reflect incoming light. So when you're seeing this visualization, you can have a description of the scene lighting. So for example, these three colored light bulbs. And instead of saying, modeling the scene as particles that emit light towards the camera, we'll model the scene as particles that just reflect incoming light. And so a standard way of describing that is like a BRDF, or a bidirectional reflectance distribution function. And that's just a function that describes how particles reflect light given a incoming and outgoing direction. Okay, let's think about how you want to compute the color of this camera array with this kind of a scene description, like a reflectance field. And we have only considering direct lighting, right? And by direct lighting, I mean that we're just considering the effects of the emitted light that comes from the light emitters and it's reflected by particles along the camera array back towards the camera. Okay, so to render this kind of scene description, you first have to query the network just as a NERF for the volume density at each point along the camera array, right? And that's to figure out this how much each point is blocked by the closer points in the volume. Right, so how visible is each sample location from the camera? And then from that, you actually then need to calculate how much light arrives at each one of these sample locations, right? To figure out how much light is then reflected. So to do that, you compute the visibility between each point and each light sources, again, by densely querying the neural field representation for the volume density along each light ray. And you can imagine this is even more complex for indirect illumination, but for now, this is the kind of mental model you need to think of. If I want a description of a 3D scene, that allows me to now edit lighting, right? You need to just first model how any particle in the volumetric scene reflects lighting, and you need to have this additional computation for how much light arrives at each point in the volume from your light sources. And using this relatively simple change to a NERF-like model, you can actually produce really nice relighting results. And so this paper, Neural Reflectance Fields, was like one of the first works that extended NERF to enable relighting by using the MLP in NERF to predict parameters for BRDF at a continuous point in space. But as you might kind of guess based on the visualizations from before, simulating this can be really computationally expensive, right? Essentially, you have to, if you want to consider all the effects of like indirect illumination, inner reflections, and that kind of thing, you have to do a full kind of light transport simulation throughout a volume. And so simulating the right light transport through, especially a volume where you have to do a forward pass of a network to describe what the volume contains at any location, can be really computationally expensive. So this kind of work ends up being limited to maybe more simple lighting, like we're showing here with a single point light source. And more recently, we've also worked on ways to make this general idea more efficient by, you can imagine maybe simplifying the geometries. Instead of considering full volumetric geometry, you might say, maybe I can take a NeRF of a scene, distill it into like a surface kind of representation, and then figure out, okay, how does each point on the existing surface of the scene reflect light? Okay, so let's go back to this question of what should a neural field store a new point, right? So I've described 2 points on this like spectrum, right? So on the left end of the spectrum, all you want to do is edit the viewpoint of the camera at test time, or after you've recovered a representation of the scene. And on the right side of this spectrum, I've described, okay, how we want to represent a scene if you want to change, in addition to viewpoint, also maybe lighting, or maybe even want to edit the materials, right? Then as we saw, you can actually kind of, there's a big change in the computation that's involved to move along the spectrum. So one way of actually thinking about it is like a spectrum of caching to simulation, right? So like the less you want to modify about the scene or the camera or lighting parameters after you've recovered the scene, the more you can think of the underlying neural field representation as caching a lot of the physics computation that would actually have to happen to do the simulation, right? So it's like a spectrum of caching to simulation, where the more and more you want to edit the physical properties of the scene, like the lighting and materials, the more you now have to re-simulate the flow of light through the scene. And the less you want to edit about the scene, the more you can say that optimizing a network to represent the scene is actually caching or amortizing the kind of physical computation that would need to happen to model the flow of light through the scene. And the interesting thing here, right, so yeah, spectrum of simulation versus caching. And the interesting thing here is that there's like a huge in-between zone between what was kind of traditionally in computer vision, we tend to think of only these endpoints, right? They think of like a lot of view synthesis or image-based rendering as only want to change the viewpoint. And on the other end, maybe if people are more familiar with like intrinsic decomposition or full-on inverse rendering, we want to do a full lighting, material, geometry decomposition of the scene. But there's a lot of interesting space in between where you can imagine that there's a lot of benefits in more efficient rendering where you don't have to do a full light transport physics simulation to re-render the scene under different edits. But you can still maintain control over certain kind of components or properties of the scene. So a really interesting question to ask now is like, what lies in between these extremes, right? So like, what different representations can we use in between these two that still allow us to maintain control over and edit certain components that really want to edit? And I'm going to describe one of these today. So there's a project that we presented at CVPR 2022 called RefNeRF, Structured View Dependent Appearance for Neural Radiance Fields. Okay, so let's take a look at a NeRF reconstruction of a scene with kind of complex looking materials, so including these really shiny materials. So at first glance, NeRF renderings look pretty good, but if we focus on a shiny object like this chrome ball, it actually kind of, the illusion of NeRF's quality kind of breaks down, and it's clear that NeRF is unable to really accurately represent and render shiny surfaces with spectral highlights. And NeRF's renderings of the chrome ball don't really look like what we'd expect from a mirror, right? The reflections appear kind of cloudy, and they don't really move smoothly across the surface as they should. And this is actually a failure in NeRF because NeRF often fakes shiny appearance by hiding stuff behind a semi-transparent surface, as you can kind of illuminate by just rendering the scene in front of a checkerboard pattern. We can see the checkerboard pattern peeking through the edge of this chrome ball. So in this this kind of project, I want to present an approach called RefNeRF that it's designed to kind of fix specularities, and it does it in this way that explores this in-between spectrum between these two representations. We're going to rely on the optimization of this model to amortize a lot of the physics light transport computation you think you might need to do to actually simulate really high quality view-dependent appearance or kind of physically realistic appearance of fancy materials and shiny objects. So yeah, our model fixes this problem essentially by taking a different approach to representing the view-dependent aspect of scene content. Let's do a little quick dive into why does NeRF actually fail to represent shiny surfaces. So here's an example of a metallic ball with two rough bands. And if you actually train NeRF on 100 images of this scene from different viewpoints, you get a pretty disappointing result. Like despite this extremely simple geometry, NeRF kind of fails to render convincing views. And you get this appearance like fog that fades in and out instead of sharp reflections. And I'm going to describe how we're able to fix this in a efficient rendering kind of model that is able to really capture the underlying geometry really well as the view-dependent appearance that's seen. So let's dig in a little bit into why standard NeRF fails badly on the simple scene. So here's an illustration that's showing like an overhead cartoon view of the same scene. So there's to better understand this issue, let's render the scene from the back to the front of the scene. And what we're gonna do is only rendering what appears behind a plane in the scene. And we're gonna sweep the plane over time from the back to the front and show what the rendering looks like. Okay, so here's when the plane's at the very far back. And what you can see is that in addition to this expanding shell that fills the image from the outside in, there's actually a lot of fuzzy material inside the ball that's getting accumulated as we sweep the rendering from the back to the front. And this kind of reveals that NeRF is representing specular reflections as these glowing emitters that are embedded in the scene and that kind of shine through a foggy semi-transparent surface instead of correctly replicating the view-dependent appearance of points on the surface. And so trying to extract geometry from these cloudy explanations is a real problem. So one way you can visualize the geometry in the underlying NeRF is you take the normalized negative gradient to the density field. So this just tells you what's the direction at any point in which the volume density is decreasing the fastest. So for example, at this interface between free space and the object, like the arrow that we're showing here, the normals are going to be pointing outward from the object, right? Because that's the direction in which the volume density is decreasing fastest. And the structure inside the object makes these the way we sample and define these normals, alternate directions, and that causes the accumulated normals to be very noisy or pointing in a lot of different directions. So if we render these normals in NeRF, you can see NeRF's extracted normals are really foggy and noisy. And when you change the viewpoints, you can actually even see these bumps that are lying inside the surface that are caused by these like fake bright specularities. Okay, so let's think about how we can fix this. How can we enable NeRF to represent better view-dependent appearance for shiny materials while not having to go all the way to the end of the spectrum and do full light bouncing transport simulation? So first, we're going to introduce a regularizer that encourages the model's density to be more concentrated and surface-like, and to prevent this foggy geometry and improve the surface normals. And then we're going to use these like more accurate surface normals to rethink the way in which view-dependent appearance is represented in NeRF-like models. And this is specifically designed to simplify the function that network has to learn for simulating view-dependent appearance. And I'll talk about that in a second. So let's first look at how we improve the geometry in normals. So consider a single ray that passes through the sphere, right? So as we saw before, NeRF's foggy geometry results in normals that face away from the camera, but still contribute to the final rendered color. And that's what we saw in this like kind of foggy gray appearance of the normal vectors before. So we're going to introduce a new type of regularizer that penalizes this appearance. And so, for example, this normal that we're going to show in red here, right? So consider this point on the outer surface of the ball. So this normal vector is pointing on the same hemisphere, is pointing towards the camera, and so this is not penalized. And this other normal here is actually pointing the wrong way, right? It's not pointing towards the camera, but it's actually fully occluded, right? We don't actually see these points in the volume that have this normal, so we don't penalize that. What we are going to penalize is normals like this, which are partially visible, so they actually show up in the final rendering, but it points away from the camera. The normal is oriented away from the camera. And you can kind of think about this as like a more intuitive regularizer where like if you look around in the world and you see opaque objects, you shouldn't really be able to see surfaces that point away from you unless you're looking at semi-transparent surfaces. And another way to visualize what this regularizer is going to do is like by looking at the rendering weights, like how much is, if you look at all the sample points along the ray, how much does each of them contribute to the final rendered color? So here are the rendering weights along a ray that passes through a NeRF model that's trained on the same shiny ball scene from before. And here are actually the corresponding normals at these points that we sample along a ray. And you can visualize the regularizer effect during optimization by, it's actually encouraging the normals to face the camera more, which also ends up tightening up this weight distribution and reducing the fogginess. And now if we look at the back to front renderings of the same scene using our method, it no longer hides emitters inside the object, and you get a lot nicer density. And if you now visualize normals again compared to NeRF, our required normals are much better at capturing underlying object geometry. Okay, so now we have like a regularizer that helps improve the surface, make the NeRF geometry a little bit more surface-like and better. Let's use them to improve the way we model view-dependent appearance. So there's an underlying issue with NeRF, which is actually the way it parameterizes view-dependent appearance is kind of problematic. So let's consider a camera that's pointed at a single surface point, right, in this toy visualization. And if we let's look at the actual outgoing radiance, the ground truth outgoing radiance for a point on this ball that's marked in orange. And we're going to look at this for every viewing direction as we parameterize by the viewing angles phi and theta. So if we look at the outgoing color from the scene for all viewing, it looks like this on the right. And when the point moves, this is what the function looks like. If we move this orange point along the ball. So even for like this really simple shape, the view-dependent appearance, the actually underlying function of what does this point look like from different global viewing directions changes very rapidly across the surface. And it ends up being really hard for a function approximator like an MLP to interpolate from a limited number of observations. So one of the key contributions that we have in this paper is to use these improved normal vectors that we've reconstructed at each 3D point. And we're going to reparameterize the outgoing radiance actually by the reflection of the viewing direction about the normal. And this reparameterization makes the underlying function a lot simpler and easier for the network to interpolate. So with this, if you consider this reparameterization and look at the actual underlying outgoing radiance parameterized by the reflection direction, we can observe that the only change actually happens when a point moves between different materials. And, oh, sorry, yeah. And by different materials, I mean materials that are more or less rough. And so to better understand the effect that this roughness has, let's like zoom in and consider the small surface patch. So if the material is very smooth like a mirror, all the reflection directions in a patch of surface kind of point the same way, as we're showing here by these aligned purple arrows. And this highly concentrated distribution, right? On the right, we're visualizing the distribution of reflection directions over the sphere. And if you make the material rougher, these reflection directions don't actually no longer point in the same direction. They actually fall under a lot wider distribution. So in order to help our method explicitly model this idea of roughness, we encode the distribution of reflection directions and feed it into the network. And so we first have the underlying represent the MLP predict a scalar roughness at every 3D location, which we use to define a Gaussian-like distribution over reflection directions. And in order to encode inputs in a way that captures high-frequency details, NeRF uses what's called a sinusoidal positional encoding, or positional encoding. And instead of using the sinusoidal positional encoding in NeRF, we instead project the reflection directions onto a set of spherical harmonics, which are analogous to sinusoids on the sphere. And we're going to call this a directional encoding. And instead to encode a distribution instead of a single reflection direction, we're going to look at the expectation of this directional encoding under these predicted Gaussian-like distributions of the roughness. And we'll call this an integrated directional encoding. And it has a pretty intuitive behavior where regions with smooth materials have high-frequency components in the encoding, as we're showing in the bottom row. And if we consider materials with rougher materials, wider distributions, like we're visualizing now on the right, these high frequencies become attenuated, and you can see that the colors kind of get washed out in the bottom row, which results in the network producing a blurrier view-dependent outgoing appearance. And after this improvements, our model is able to recover really accurate normals and geometry of the scene, as well as render convincing specular reflections, like we're seeing in Simple's case. And let's take a look at some more complicated examples. So here's an example where the top performing MITNeRF algorithm reflections are really foggy and inconsistent. And our method now is like able to successfully produce realistic specularities that smoothly move across the surfaces that you'd expect. And we can apply these ideas to even real data and render realistic views of, for example, this toy car, and recover really accurate scene geometry and notice like the consistent reflections on the car's windshield. And one of the really cool things about this specific way of factorizing view-dependent appearance is that it kind of decomposes the appearance into meaningful components that allow us to do a lot of scene editing without having to do full light transport simulation. So here's this visualization of some of these components, and we can use them to do things like edit the roughness of a scene. So here's an example where let's focus on the shiny metallic objects inside these boxes, and we can artificially increase the roughness of these points, and increasing them actually does the right thing. It makes the balls appear less shiny. And so this is interesting, like it's a new knob on material editing without having to decompose the scene into very kind of standard BRDF materials that would involve more expensive integration. And you can do the opposite, like decrease the roughness of objects in the scene, which makes like other less shiny objects, like the one in the middle right, appear shinier. And you can do other cool things with this representation, like separately edit the specular and diffuse colors. So in this example, we're just editing the diffuse colors of this car, and that the actual color of the reflections, right? The reflections you're seeing on the hood and the windshield of this car remain the same. And you can do like manipulate the amount of diffuse and specular color to alter the perceived material properties. Cool. So yes, looks like it's about running out of time. But so to conclude, I think there's a really interesting range in the spectrum of like just editing the viewpoint, which is maybe what we see in more traditional view synthesis kind of approaches, methods, and editing the idea of having to do a full material and lighting decomposition and to edit the viewpoint, the lighting, and the material. And I think there's a lot of these interesting in-between approaches that maintain the efficiency of like NeRF's original representation and don't require you to do full light transport balancing, like volumetric path tracing simulation, but still provide really useful nods on editing the scene for when you're rendering. Great, thank you.
Okay, thank you very much for the very thorough introduction in NeRFs, and also, yeah, very nice results that you already achieved. So, if there are questions, please unmute yourself or write your questions in the chat room. Okay, meanwhile, I will start with a simple question, but it's quite complex. So, how could you comment about the complexity in both training and also the scaling with the higher resolution? So at the moment, the models are quite small. And, yeah.
Are you sort of referring to like maybe a standard NeRF or like because it's interesting, the scaling is actually one of the big differentiators between when you, the more kind of light transport simulation you want to do, like the more your model requires you to do light transport simulation, the worse it ends up scaling, right? So for example, even I stopped sharing this, but if you consider if you have points along array and you have like a point light source, right?
Yeah.
Okay, in a standard NeRF kind of model, it's linear compute with the number of points along the array.
Yes.
But now so as you essentially, if you want to do higher and higher resolution images, right? You need to sample higher and higher you have a higher sampling density of points along the array because that kind of constrains the effective resolution of your representation, right? So say if I have like really high resolution images, but I only ever render them in the NeRF by valuing a few points along the array, you're going to have like an alias issue of aliasing here. So then you have like you have to say linearly scale the number of samples along each array to render higher and higher resolutions. If you want to also not even just simulate direct lighting with a single point light source, that jumps to quadratic, right? Because for each point along there, you have to also sample points along the same volume towards the light. And in the same way, like you can't undersample, or you can't have very low sampling density because you'll have the wrong light visibility. And it gets, you can imagine it gets worse if you want to do indirect lighting simulation, stuff like that too. So one of the nice things is like, it seems very useful to have these models that just by training them, it kind of amortizes this light transport computation you would have to do, right? For example, like in the RefNeRF model, you're training it to implicitly do the integration across all incoming lighting directions because you've only said, I'm only ever going to query it at a single reflection direction, and you just have to tell me, the network has to tell me what is the correct color, right? And so if you have 2 points of different materials, the thing that changes is that one of them has to integrate over a wider distribution of reflection directions and one doesn't. And instead of explicitly doing this integration where now you have to sample more rays and incur this like bad blow up of complexity, you rely on the fact of training this to match the images to kind of amortize that physics computation you have to do.
Along the same direction, assuming that we have like a case scenario where we are just training. Let's say the resolution is relatively low. Okay, it's not a problem for a NeRF model. And the task here is we just wanted to give the opportunity, to generate or to change the viewpoint within that streaming. Okay, And
you said a streaming?
A streaming is what we are doing now. Okay, and we just want to give the opportunity to create an Earth online, a model, okay, and then to be able to change slightly the viewpoint. Okay, so do you think that this kind of training could be possible? I mean, to reduce the training complexity and to be able to pick it like in an online fashion and build something over a stream?
Yeah, so I think that's a really cool idea, and I think you can imagine. I haven't seen a version of this like that exists, but you could imagine something that maybe incrementally solves or adjusts, like kind of using the more and more observations. Like I've like imagined like just take the first frame of us talking on video chat. You have a pretty, from a single viewpoint, you have a pretty terrible geometry estimate, right? You have like maybe you can get like a course with someone off of depth kind of thing. And then as I talk to you, I move a little bit more, and you can imagine kind of incrementally updating the geometry, incrementally updating it to have more complexity. And then you could also imagine like constraining. Okay, so like as you want to render more motion, more camera motion, I guess, like more like this, like more parallax. You need a higher and higher depth resolution of your representation, essentially, right? It's like a disparity scaling thing. So you could imagine, I guess, like in a streaming application in the very beginning, if I don't have that many observations of a lot of camera motion, maybe I should have a very simple kind of representation. And as I have more and more observations, by either me moving or the camera moving, I should increase the geometry complexity of my representations in a way that, like if you want to be like the most resource efficient, I guess, in the streaming kind of scenario. Something like that would be really interesting. Yeah.
Okay, are there some other questions? So I think that
yes, Radu, please give me 1 second.
Yes.
So thank you for your presentation, Pratul. Actually, someone in the chat asked if the presentation is publicly available. I assume that maybe we can.
I will be sending these slides to this workshop's website, I guess. So it should be. I'm not sure. Yeah, it should be up there.
So you'll find the slides on the webpage, and we are planning also to provide the whole recording of the talk also online, publicly.
It will be basically available using the same link as on the website. So if you go to the workshop website, you'll see a YouTube link, and if you click it, you can both see what's the workshop now, and you can also check it later.
Okay, so if there are no other questions, then thank you very much.
No, one second, because actually that was yeah. So
okay,
just Chris, I'm wondering, what are your tricks or suggestions when it comes to recover high frequency details when you render?
Sorry, could you repeat that? I think I didn't quite catch.
What are the common tricks, or kind of what would you do if you really don't care about the resolution but the details? Because NeRF usually, produces blurry rendered images. So if you aim to kind of render high frequency details, what are the common tricks that you would need to use?
Yeah, so actually, okay, so in the original kind of NeRF paper and formulation, the main knob you have to control how many high frequencies that you can represent in the underlying NeRF is this positional encoding thing, right? So you pass, I didn't really cover that here, but you take your continuously valued coordinates and you pass them through a set of sinusoids with different increasing frequencies before you pass that to the network. And the underlying idea is like using higher and higher frequencies in the encoding allows the network to use like a finer interpolation kernel and represent higher frequencies. And so that was one way of doing it. But then like since original NeRF, we've seen other ways. So like a lot of these like a hybrid feature grid plus MLP representations, like if you might have seen like instant neurographics primitives, like there's instant NeRF stuff from NVIDIA, they have a different approach to doing this. You have like a kind of a cascade or a set of different feature grids at increasing resolutions, and then to represent really high, like the highest frequency, the highest sampling rate grids that you can't fit on your GPU memory, they have like this hash encoding trick, which is really cool. So I think, yeah, so in the pure MLP setup, it ends up being you change the frequencies in which you modulate your coordinates before passing them to MLP is like the main knob you have on controlling the level of detail you can represent. And then in the kind of the methods that use also like feature grids or actually like store 3D voxel grids with features, the resolution of the grid that you're storing with features is the main thing that limits your resolution. And there's cool tricks to get around not being able to store a full, like instantiate essentially a full super dense grid in memory, such as this hash encoding. Or you can imagine other things, like maybe you can imagine something that kind of incrementally trains. And you start with like a very sparse voxel, start with a very dense, but low resolution voxel grid, and then you sparsify and increase resolution as you think, oh, maybe in this region of space there's more content, then I can subdivide this voxel and then solve for what exists in those. And you can imagine something like that, like some papers do things like that too.
Okay, thank you.
Okay, thank you very much, Pratul, for the very nice talk, and also about your revealing the details, behind what can we do in good practice. Okay, so let's move on with the challenge report on efficient image resolution on mobile devices, mobile MPUs. Andrei.
So the fourth mobile AI challenge was quantized image super resolution challenge, and the problem itself is probably known to all of you. So, and this is also a very important task for mobile devices, as right now it is actively used for upsampling image and video data coming from various media platforms. It is also used in telephoto cameras. So for instance, you can find an efficient super resolution model in the latest Google Pixel 7 Pro device that allows you to achieve a zoom rate of 30 in your camera. And of course, like this is not a completely optical zoom. Extra 10 times provided, well, maybe extra 4, yeah, or between 4 and 10 times is provided only due to deployment-based solution for this task. So, and the participants had to solve exactly this problem. They had to design an efficient and accurate 3 times image super resolution network. Moreover, the model had to be fully quantized in order to be compatible with all mobile and IoT NPUs. And ideally, the participants had to achieve real-time performance on mobile NPUs. So the task was quite hard. The participants were provided with a popular diff2k dataset. Probably I don't need to provide you with an introduction to this data, as the majority of you already used it in the past. And the performance of the models was evaluated using PSNI, SSAM scores, and runtime results on the Synaptics VS680 platform with a VeriSilicon NPU. So this platform is used in many smart TV boards. And of course, these boards need efficient super resolution models in order to perform fast video upscaling. So for instance, video upscaling from YouTube, from some other platforms. This is especially very important when you have high resolution TV set. So for instance, you have 4K screen, or right now they all even exist 8K screens. And in order a video to be looking good, sometimes you need to upsample it to the resolution of this screen. And also the final score of all solutions was computed based on the PSNI and runtime results. During the development phase, same as in other challenges, the participants were provided with a benchmark app that could be used for local model optimizations. And during the development phase, they also had an opportunity to upload their TensorFlow-like models to an external web server and check the runtime on the target Synaptics board directly. And the participants were also provided with even more information about not just the entire runtime of their models, but the runtime of each layer of their submitted network. So there was lots of information that could help the participants to design quite efficient solution for this platform. And this slide shows summarized results obtained in this challenge. Well, first of all, we should say that all solutions, solutions submitted during the final phase of the competitions were very efficient. So all of them were able to process full HD, to generate full HD resolution images under 75 milliseconds. Moreover, you can see that top submissions were able to achieve a speed of more than 30 or more than 60 FPS. So which means that they can upsample low resolution videos to a full HD resolution at a rate of 60 FPS. Additionally, this year we didn't see any major issues with model quantization. So those of you who checked our previous reports probably know that last year lots of teams just failed to do proper quantization of their models, and the resulting solutions were demonstrating very low accuracy. This year almost everything is good, and in the majority of cases the accuracy drop caused by quantization is not exceeding 0.1 dB. The best solution in this challenge was provided by team Z6, and quite interesting to compare this result to the last year top solution. This is a BPN model. This is the best model proposed in the Mobile AI 2021 image super resolution challenge. And we can see that the current state of that model outperforms the previous baseline, both in terms of fidelity scores. So there is quite huge improvement in SSIM score and in runtime score. So this year the model is almost twice faster than the one proposed 1 year ago. Also, quite interesting results were demonstrated by other teams. So you can see that there are solutions that are even faster than the top submission. And we should also mention that all submissions made in the final challenge phase significantly outperform the basic bicubic upscaling baseline. So in all cases, the improvement in SSIM score is like dramatic. And the same refers to PSNR score. So therefore, the solutions that are proposed here can really be used for upsampling images on many platforms, on many IoT and smart TV platforms, and they would demonstrate much better perceptual results than the basic bicubic upsampling, despite the fact that the runtime is quite low when executed on NPUs or GPUs or some other accelerators. The first, the challenge winner this year is Team Z6. They proposed a very compact model. Its design is in some cases straightforward, so only convolutions plus additional skip connections at the end. The associated depth to space OP. This OP was used by the majority of teams, as it does not require any computations. This is just a logical operator. And therefore, compared to transposed convolution, this OP demonstrates much better runtime results and memory consumption. But when you are dealing with such small models, the biggest challenge is how to train it efficiently. Because the smaller is the model, the bigger is the accuracy drop caused by quantization, and also the lower the results during normal training. So the first major issue here is that the TensorFlow's standard post-training quantization tools, they are performing symmetric quantization. Therefore, if the weights of your model are symmetric, this usually causes quite significant accuracy drop. So to ensure that weight distribution is not skewed, the authors added weight clipping to ensure that they're getting a symmetric distribution. Also, the authors performed fine-tuning of the model with quantized aware training, and this further improved the final result of the model. So this is a quite interesting solution, as it is really super compact, but at the same time it shows quite nice numerical results. The second solution, the second best solution, was proposed by Team TCL Research Europe, and the main idea here is structural reparameterization. So the architecture consisted of basic CLB blocks. Here you can see the structure of this block. So it consists of several convolutions, 1x1, 3x3, and 1x1, and additional skip connection. During the training phase, this block looks like this. And therefore, it allows to learn a diverse set of features and to boost the performance of the model. During the inference stage, this block is collapsed into one single plane convolution, 3x3 convolution. Therefore, during the inference phase, you are getting an extremely fast and efficient model. So you can see that the final architecture after this fusion consists of only 3x3 convolutions and one depth to space layer. There also is additional used channel pruning for detecting the least important convolution channels and removing them from each layer, which helped them to further boost the runtime of the model. And same as the previous team, they used quantized aware training for getting better accuracy after model quantization. The third-based solution, you already know this approach. They also used equivalent, they called it equivalent transformations, but this is basically the same structural reparameterization stuff. So in this case, the model consisted of basic REP blocks, and here you can see the structure of this REP block. And during the inference, it was like this, and during the training, it was looking like on this slide. And during the inference, it was also fused into a single convolutional OP. And you can see that the structure of this block is slightly different from the one proposed by previous team. So in this case, we have 1x1, then 3x3, then 1x1 convolution and skip connection. And here we have two parallel 3x3 convolutions followed by two 1x1 convolutions, and then we have summation, I guess. So yeah, the structure is slightly different, but at the end, this resulted in a very similar architecture. So we have, again, a simple plane network consisting of only convolutions followed by ReLUs and pixel shuffle at the end. And yeah, also the authors used equivalent transformations to replace addition and concatenation ops. And in this case, the model was trained with MSC functionality. So yeah, you can find a more detailed description of these top solutions and of the rest of the solutions in the challenge paper. There were many interesting models proposed in this competition, and some models are providing you with better runtime results, some models with better fidelity results and perceptual results. And again, depending on the hardware, the final runtime of the solutions might also vary a little bit. So if you're interested in developing efficient architectures for image super resolution, then in the report you have a description of, I guess, 25 different architectures designed for quantized super resolution on IoT platforms, and feel free to check it. So are there any questions?
Okay, so if there are no questions.
Yeah, then we're moving to image resolution papers.
Okay, thank you, Andrei. So the first image resolution paper after this challenge report is efficient image resolution using vast receptive field attention, and the authors provided a pre-recording.
Hi everyone, I'm Lin Zhou. I'm from XPixel. In this work, we designed an efficient SR network by improving the attention mechanism. About the task, efficient SR requires both the reconstruction performance and the light computational cost. Our motivation comes from the familiar attention mechanisms, inspired by recent advances in self-attention and VIT. We believe that there is still considerable room for improvement on attention mechanism based on CNN. Finally, yes, we successfully made some improvement and demonstrated a solid evolutionary model roadmap. The attention mechanism we proposed mainly contains 3 approaches, which are marked by the stars on this roadmap. We start from a very basic block of Model 1. Applying the first approach, enlarging the attention kernel denied, we get the Model 2. This brings obvious improvement of 0.15 dB, but also millions of extra parameters. Then we use the well-designed depth-wise separable large kernel convolutions, which will be illustrated later, to reduce this huge computational burden. Now we get the Model 4. Thirdly, we introduce a pixel-wise normalization operation to save the lost performance. At last, we, with some later refinement and increase on training burden, our WaveSR can outperform the SOTA models with less parameters. Here are the illustrations. And left, these 2 convolution layers save the parameters and also achieves a large receptive field. Pixel normalization normalize at every pixel position. And here is the architecture. We adopt the most common SR networks with the 4 stages and the building block without that much connections and branches, simple and compact. To make the model as little as possible, we make further refinement and experiments based on Model 6. Here we provide our conclusion as the reference of efficient network designing. The ablation studies thoroughly explored the model structure by adjusting the model type, normalization type, the sequence of layers in attention, and the receptor field. These help to conduct the eventual WaveSR. The results demonstrated the effectiveness of our pixel normalization. It can achieve a steady training curve and the best performance growth. On the right side are some other insights concluded. The proposed WaveSR, SMORE, achieves competitive performance to BSRN SMORE, which is our previous work and the winner of Entire this year. On visual comparison, our model can reconstruct stripes and line patterns more accurately. All the training and testing codes as well as the models have been released on GitHub. Here is the repository's QR code. Please feel free to contact me. And welcome to pay attention to and to follow our works. Thank you. If you have any questions, you can ask now.
Okay, so if there are questions, please ask. The first author is with us, Grace Linzhou. Okay, Lynn, are you there? Grace?
Yes, I'm here.
Okay, so a simple question.
Okay.
In the paper and also by the performance that you are showing in the challenge, it's quite clear that the design choices are quite good. Okay, but I'm just curious if there is something to learn from the training, or if you tried some other tricks to improve the accuracy of your model just by adding more.
Yeah. I concluded them, some of them on the PPT also. I can resharing the PPT. Okay, it's mainly in the papers, the conclusion ablation studies. and the detailed micro designing part. For example, we can our experiments prove that pointwise convolution should be placed in front of depthwise convolution. In detail, it means this block should be placed in front of the later two. And the other, take another example, and you can, we try different size of the attention kernel. Our motivation is to enlarge the kernel, enlarge the receptive field, but in the experiments, we found that it's not that good if the kernel is too big. 5 is a related better value, and other things, things like multi-layers upsampling block always brings promotion, and with little cost, with little parameters. And this means you can use two times pixel shuffle layers instead of 4 scarce single layers upscaling pixel shuffle.
Okay, thank you.
Okay.
Okay, are there some other questions? If not, thank you, Grace, and let's move on to the next.
Thank you.
Okay, the next presentation is about fast nearest convolution for a real-time efficient image resolution. And I will play the...
Glad here to share our paper Fast Nearest Convolution for Real-Time Efficient Image Super Resolution. This work was done by MagVI Technology in the University of Electronics Science and Technology of China. The source code and pre-trained models are already publicly available. Deep learning-based single-image super resolution approaches have drawn much attention and achieved remarkable success on modern advanced GPUs. However, most state-of-the-art methods require a huge number of parameters, memories, and computational resources, which usually show inferior inference times when applying them to current mobile devices. Our contributions are summarized as follows. We provide a comprehensive comparison of inference times for different tensor operators and network architectures on a smartphone. We propose a fast nearest convolution plane network, ANSI-net, that is mobile-friendly and can achieve the same performance as nearest interpolation. Our model can be easily deployed on mobile devices with 8-bit quantization and is fully compatible with all major mobile AI accelerators. In what follows, we will start with some experiments to show the potential choices of different techniques. First, Table 1 shows inference times of different commonly used tensor operation nodes. And Table 2 shows inference times of different convolution network structures. Quantization is also important for applying models on the smartphone. Table 3 shows the runtime and PSNR comparison on different quantization modes of ABPN. Based on above experiments, we propose the fast nearest convolution network for image super resolution. The most important component of the ANSI-net is the nearest convolution module, which is actually a special 1x1 convolution layer with stride 1. To achieve the nearest interpolation, the weights of the convolution are freezed and manually filled by S-square groups of 3x3 identity matrix, and each group would produce an RGB image, which just like a copy operation to repeat the input image S-square times. Then these RGB images can reconstruct an HR image through a depth-to-space operation. Table 4 shows the inference time between the proposed nearest convolution and other commonly used upsample methods on different mobile accelerators. Table 5 shows the runtime on different accelerators and the PSNR performance of the proposed ANSI-net on a Google Pixel 4 smartphone. In the experiment, we used the 2K dataset to evaluate the proposed method. and all approaches in this section are applied in data quantization. We compare the proposed NCNet with other lightweight real-time senior algorithms, such as FSRCNN and ABPN. The former is the pioneering DL-based senior network, and the latter is a superior method in Mobileye 2021 real-time single-image super resolution challenge. The proposed NCNet is faster than ABPN and FSRCNN on Android and ALPI, and also achieves the best PSNR performance. In addition, our method is even faster than bilinear upsampling while achieving an impressive performance. This slide shows the visual comparison on Diff2K. As we can see, the proposed method is robust to artifacts and able to recover rich details and textures. In conclusion, we introduce an efficient fast nearest convolution network, NCNet, for real-time super resolution. NCNet achieves a remarkable performance while preserving real-time inference. We also provide a comprehensive comparison of inference times for different tensor operators and network architectures on smartphone, which could help to select operators and architectures for real-world mobile devices. Thank you for your attention.
Okay, so this was the presentation. Are there questions? Okay, so if there is no question, then let's check for the next presentation. The first author is here, so I could play the recording. Garas?
Yes, I am here.
Okay, I will play the recording and you'll be here for the Q&A.
Okay.
Okay.
Hello everyone, I am Jaraz. I will present my paper titled with real-time channel mix network for mobile image super resolution. We are a group from Shanghai, Jiaotong, First China. First, I will speak about the introduction. Recently, deep learning based image super resolution method shows strong performance thanks to convolutional neural network. But even this CNN can mostly use large memory and have a lot of computation, which limited its use in mobile devices. To solve the problem, we propose channel mix network for mobile super resolution. The architecture of the proposed model as shown in the figure, we based our model in three ideas. First is block this channel and the feature mix composed of 3x3 configuration and 1x1 configuration. Also, this residual learning for the deep feature extraction. Also, this anchor-based learning that we inspire from the last year competition. Also, we use this deep to space to turn image to RGB domain. In our result, we will discuss the quantitative results, qualitative result in mobile hardware with Snapdragon 970. Also, we will discuss our application study comparison. For the quantitative result, we compare our method with the state-of-the-art method for three cases for float 32, post-training quantization-aware training. We achieve good performance compared with other method without much increase in number of parameters. Also, we will discuss our qualitative result. We compare our method with this method is the winner of the last competition in the urban media data set. Our model shows there is much improvement in the visual result compared to this model. Also, we will test our device in Snapdragon 970 hardware. We achieve, we tested in CPU and in ABI hardware. Actually, our model increased time by around 50 milliseconds for the CPU, around 4.5 for NBI, but our model show much increase in the PSNR. Finally, we will discuss our application study. To do our application study, we create four models. The first one, this model without this 3x3 configuration in the deep feature extraction. Second model without pointwise configuration in the all cases. Third model without this residual learning branch, and the last model just without the anchor-based learning between the input to output. The result of published result as shown in this table. First, this is our model. Second row is the model without 3x3 convolution, and there is much drop in the PSNR in all cases. In this case, second case is when there is no one by one convolution, and there is drop in the PSNR, but the much drop is happen in quantization aware training. The last two cases is without residual learning and without anchor-based residual learning. In this case, there is a small increase in the PSNR, but this add few less number of computational cost. In conclusion, we propose channel mixing network for mobile super resolution that is based in pointwise convolution to make channel mixing, and 3x3 convolution for the feature mix. Based in this block, we propose channel deep feature mixing network for mobile device that is contain only pointwise convolution and 3x3 convolution. Also, we achieve comparable performance in my 2022 competition, but we will work to improve our model to achieve good result in the next version of this competition. Thank you for listening. Any question?
Okay, so we have time for one question. So if no question, then we move on. Thank you, Yaras.
Okay, thank you.
We'll move on to the next presentation. And this presentation is DSR towards drone image sphere resolution. And I can play the video from the authors. And they will be here for the questions.
Hello, this is the presentation of DSR towards drone image super resolution carried out at the School of Computer and Information Science in Krefeld, Switzerland. Although learning is the super resolution method pushes forward to the state of the art performance, multiple constraints were along the way. The model are trained with certain assumptions on the deep model. The underlying data set are manufactured and suffer from accounting bias. Those data sets are typically captured along the horizontal direction and human level height. The methods trained on this domain do not generalize well to different data. Besides, drones can significantly benefit from super resolution solutions as they enable the drone to fly at a higher altitude and with a good image quality. We created our DSR to decide by capturing image pairs of the same sense with two cameras of different lengths. We take photos at 10 different altitudes for each sense. We use a DJI Mavic 3 drone for collecting the data. We match the exposure value between the two cameras. For raw data, we first collect the Bayer color filter rate to obtain 4-channel images. Since the images captured by two cameras has different fields of view, we crop the match the fields of view from low resolution images. Then we resize the match the fields of view to a fixed size. To improve the accuracy of our image pair registration, we use the pixel-wise color transfer algorithm from RealSR and histogram matching. We plot the average power spectral density of DSR with the two other data sets. The PSD at the lower altitude lies above the PSD of higher altitude images. This clearly highlights the existence of a domain gap across altitudes. We also estimate the blur cutoff between our low resolution and the high resolution observation. The blur cutoff estimated from DSR is similar to the one in real SR, but it's even more different than the qubit kernel. Its wider shape indicates a stronger flow. The benchmark state-of-the-art method on DSR. We evaluate the performance at its output to explore its effect. We see that the super-resolution network suffer a performance drop on DSR. It is also interesting to observe the variation in performance across output, and the ranking of different super-resolution methods have actually changes between data sets. We further evaluate the performance of super-resolution networks on DSR at the variable altitude with a reaching step. We continue the 7IR network on DSR. The domain gap between images captured at a different altitude also motivated us to build a method for incorporating altitude information. Our fine-tuning and the altitude-aware network consistently improve the performance of 7IR. In summary, DSR provides highest of lower and higher images for drawn images super-resolution. Furthermore, we capture distance at different altitudes to analyze domain variability. Then we benchmark the off-the-shelf super-resolution methods on DSR. Finally, we show that the altitude-aware architecture as well as fine-tuning can outperform DSR methods. To know more about DSR, please check out our paper and code. They are publicly available.
Okay, so are there questions? Okay, if no question, then we move to the next presentation, evaluating image resolution performance on mobile devices. And the authors provided
Hello,
pre-recording, and I will play it, and they will be here to take the questions.
everyone. Thanks for watching this video. Today, I am going to talk about our work, evaluating image super resolution performance on mobile devices, an online benchmark. The authors include Xindong Zhang, Wei Zeng, and Lei Zhang, whom are from the Hong Kong Polytechnic and the OPPO research. Deep learning-based image super resolution, SR, has shown its strong capability in recovering high-resolution image details from low-resolution inputs. With the ubiquitous use of AI accelerators on mobile devices, increasing attention has been received to develop mobile-friendly SR models. Because of the complicated and tedious routines to deploy SR models on mobile devices, researchers have to use indirect indices, such as flops, number of parameters, and activations, to evaluate and compare the efficiency of SR models. However, these indices cannot faithfully reflect the real performance of SR models on mobile devices. Ignatov et al. Developed an X-offline Android application, named AI Benchmark, to collect on-device statistics, including latency and memory consumption, for evaluating the performance of AI models on different mobile devices. MLPerf is a large mobile inference benchmark focusing on high-level vision tasks, including image classification, objection detection, semantic segmentation, and natural language processing. However, both the above two benchmarks require users to follow complicated routines to convert their models into a deployable format and cannot return the efficiency indices on time. For example, MLPerf updates its benchmark once a month. In addition, these benchmarks do not pay enough attention to the computationally more intensive low-level version tasks such as super resolution. Considering the increasing research interest in real-time SR models, it is highly desirable to develop a benchmark to conveniently evaluate and compare the on-device performance of SR models on mobile devices. In this work, we develop an online benchmark to fill the gap between model design and performance evaluation, especially the efficiency on mobile devices. Consists of 3 components: a web server, an edge server, and multiple mobile devices. Users only need to upload their model definition files via the website. Our edge server will automatically download the model files from the web server, conduct a series of model conversion and optimization processes, and pass the deployable TFLITE models to a set of wireless connected mobile devices for on-device evaluation. The key performance indices include hardware latency, memory, and energy consumption. Finally, the edge server will collect the evaluation results and send them back to the web server, visualizing them to the users. We evaluate the state-of-the-art lightweight, traditional SR models, as well as the transformer-based models, and we also include some representative methods from recent efficient SR competitions, like AIM 2020 and NTIRE 2022. More details and analysis can refer to our paper and upcoming official website. Thanks again for watching.
Okay, the authors are with us. If you have questions. Okay, if no questions, we'll move on to the next talk. And we have the pre-recording.
Hello, my name is Darius, and I would like to present you what I've done with my colleagues, Ilya and Nicola. Our project consists of an adaptation of conventional GPK field as shown previously results generational task closing the gap between phase and adjusted nodes. Compared to previous UKs, they proved that depth of the stochastic layers highly affects the performance of the models, and were able to develop models with up to 7 stochastic layers. They are based on hierarchical PA architecture, of which you can see an example on the screen, where latents from the approximate posterior and prior shared parameters along with the development. For the super resolution task, an external model is added, which we call LRA model, based on the architecture of the bottom other being transfer. LRA encoder would have A prime, which is the A for simply size of the top-down generic top-down blocks and also, in order to stabilize the training of the already sensitive architecture, 8 parameters are added, which gradually introduce the new values to the pre-trained models. Weights are initialized from pre-trained models that are some results. Other popular resolution models such as EDSR, ESR-GAN, and by comparing against EDSR, our model is sharper, being able to generate more details, but this is also reflected in metrics such as SNR and SSA, which have been shown to favor images that are more averaged out and taking the ESR and ESR-GAN, for example, is almost because ESR-GAN is sharper than ours, but at the same time introduces more artifacts from the generative process. Looking at more pictures, for example, the scanning image from the Z5 represent, we can see the same effects again, especially in the details of the eye in this specific scenario. Situating our model somewhere in between leveraging the sharpness, smooth details, artifacts, and averaged out details. In the end, to summarize the work, we believe that the results are competitive to other models. To look at some results, we are comparing with other popular super resolution models such as EDSR, ESR-GAN, and RFINet. By comparing against EDSR, our model looks sharper, being able to generate more details, but this is also reflected in metrics such as PSNR and SSC, which have been shown to favor images that are more averaged out and smoother. Taking a look at ESR-GAN, for example, we can see the opposite effect, because ESR-GAN looks sharper than ours, but at the same time introduces more artifacts from the generative process. Looking at more pictures, as for example, the Tucan image from the SET5 dataset, we can see the same effects again, especially in the details of the eye in this specific scenario, situating our model somewhere in between leveraging sharpness, smooth details, artifacts, and averaged out details. In the end, to summarize the work, we believe that the results are competitive to other models and is compatible with other popular single image super resolution methods. The training of a notoriously sensitive network was successful by applying some training stabilization methods in a straightforward way, actually. And we believe, even though the model did not reach a state-of-the-art metrics, this was not the aim, more so to show the potential of these in the image super resolution field, which are very few at the moment. We believe that our proposed method still has a lot of space of building upon to improve the results even further, as more facts such as layer architecture, the use of more flexible distributions, or a more thorough hyperparameter search could be investigated in the future. Thank you very much.
Okay, so this was the presentation. We have time for one question. So, no question, then we'll move to the next talk, and we have a pre-recording that will play. The authors are with us, and they will take the questions afterwards.
Hello everyone, I am Bahri Batuhan Bilecan, here to present you our latest work submitted to Advances in Image Manipulation workshop, held in conjunction with ECCV 2022. We present XCAT, lightweight quantized single image super resolution, using heterogeneous group convolutions and cross-concatenation. We propose an efficient, mobile device-friendly single image super resolution network. We use HX blocks, which are the heterogeneous group convolutions with coarse concatenation layers. This allows the information flow between groups and avoids relying on one-by-one depth-wise convolutions. We also propose a method for upsampling using convolution operations, which are highly optimized for mobile devices. XCAT runs much faster with high-quality results compared to the most recent methods, like the winners of the last year's challenge, XLSR and ABPN, and other popular methods like ESP-CNN and FSR-CNN. It's also worthy to mention that integer quantized XCAT operates in real time on Mali G71MP2 GPU with 320 milliseconds, and on Synaptics Dolphin MPU with 30 milliseconds and 8.8 milliseconds, channel first and channel last, respectively. This is the general structure of XCAT. XCAT is fairly lightweight, only utilizing two HX blocks, 2D convolutions, one of which is the proposed upsampling layer, a depth-to-space layer, and activation functions like ReLU and clipped ReLU. The internal structure of HX block is given on the top of the general network structure. In HX blocks, input tensor with 28 channels is split to 21 and 7, and then sent to heterogeneous group convolution blocks, where also the kernel sizes are different and optimized for this task. Instead of relying on one-by-one depth-wise convolutions and homogeneous group convolutions, like in XLSR's G blocks, XCAT utilizes cross-concatenations for the information flow between cascaded HX blocks. This allows for a faster and more mobile-friendly network structure. The upsampling layer is done by utilizing non-trainable identity kernels in convolution layers. The kernel reproduces the input tensor 9 times. From the perspective of depth space, this is equivalent to nearest neighbor upsampling method, with scale equal to 3. Using convolutions in tasks like this avoids the tensor copy operation, which are observed to be very expensive on mobile devices. Here, we provide different combinations from our relation study. Using cross-concatenation instead of one-by-one convolutions has a significant runtime advantage in return of a small PSNR drop. Using group convolutions instead of 3x3 convolutions, again, improves the network runtime speed immensely, only sacrificing a small amount of visual quality. Here we show the effect of using cross-concatenation operation. When more HX blocks are cascaded, the effect of cross-concatenating is much more visible. Here we also observe that utilizing cross-concatenations instead of directly concatenating the tensors provides a more robust quantization procedure. Some visual results are also provided for your interest. Again, XCAT runs much faster compared to the other methods, without any significant visible visual quality drop. Thank you for listening to us. If you have any questions, you may contact us via the email addresses provided in the slide.
Okay, actually the authors are also with us here. So if you have any questions, now is the time.
We are here, sir. So if you have a question, we can answer them directly.
Okay. So we have time for one question. So if no question, then we are moving to the next talk. Thank you, Mustafa.
You're welcome.
Hello, everyone. I'm Gus from ZTE Corporation. It's my pleasure to make a report for our paper, RCB-SR, Reparameterization Convolution Block for Super Resolution. Based on the formula, we know that the direction of our optimization is reducing the energy consumption and increasing accuracy of model. We adopt ECB-SR as our baseline and optimize the baseline from 3 aspects. 1. Network architecture. 2. Network architecture search, namely NAS. 3. Training strategy. The first method, network architecture. First, the multi-branch structure of ECB can be merged into one single 3x3 convolution by using the reparameterization technique. Second, replace the activation function P review with review. Finally, add a residual block between the first ECB and the last ECB for speeding up the convergence of model. The second method, network architecture search. Based on FGNAS method, we set up a search space. We mainly focus on 2 factors, the number of channels and the number of ECB blocks. Then we obtain 4 parameter configurations and we choose model 1 as the challenge model because of its highest score. Third method, training strategy. We train the model with input data of the range 0 to 255 direct. It can save time of data pre-process. And we train with CP loss instead of L1 loss. And L2 loss is used for filtering. It can increase the accuracy of model. We also provide some qualitative results. As you can see in the picture, our method reconstructed the image very well. This is the challenge result. Compared with the first, our team named ZL3LP gets higher PSSNM efficiency. The final score is very close. Conclusion. We propose a real-time video super resolution network named SPSR. Our method gets better balance between power and quality. We will further study the characteristics of video super resolution. Thank you.
Okay, we have time for one question. Okay, so if no question, then we move to the next talk. And the authors are here.
Hello everyone, my name is Ashutosh and I'm a research scholar in the Computer Vision and Pattern Recognition Lab, IIT Ropar. And I'm here to present our work named Unified Transformer Network for Multi-Weather Image Restoration. Due to several weather degradations, the visibility in the images gets reduced, and this affects the interpretability of the images as crucial details in the images gets affected. There is a rise in the use of automated surveillance and autonomous driving. However, in the weather degraded scenarios, the performance of these applications may get affected, and hence, multi-weather image restoration can be used as a pre-processing step. Prevailing works in the direction of weather degraded image restoration either have weather specific application, or they use separate encoders for encoding different weather degradation, or utilize additional data bias such as range streaks, transmission map, etc., which increases the data hunger for the method. The main approach of this work is to present a comparatively lightweight generalized architecture for multi-weather image restoration. So this is the network architecture for the proposed method. It consists of an original resolution transformer stream for processing original scales of the input features to restore the fine details in an image. Further, it includes multi-level feature aggregation stream for learning multiple sizes of the weather degradation. Also, we have used edge boosting skip connections for restoring crucial edge details in the images. The transformer blocks consist of window-based multi-head self-attention and locally enhanced feed-forward network. Here, we provide the analysis on several training settings. First, the network is trained in a sequential manner. That is, the network is trained only for rain plus veil removal, and then the same trained model is used for training on snow plus veil removal, and so on. This training technique suffers from catastrophic forgetting problem. Next, we train the network in a combined manner. That is, the network is trained on all the datasets at the same time. But the dataset for each task has different physical properties, and learning of all the tasks in a combined manner is ineffective as the trained model does not reach peak performance for each task. Finally, we train the proposed model with memory replay training, which gives better results as compared to other training settings. Now, after seeing the methodology part, we will analyze the results of the proposed method. So these are the quantitative results on some synthetic data sets, and we have used PSNR, that is peak signal to noise ratio, and SSIM, which is structural similarity index, as evaluation metrics. And this table shows the quantitative comparison based on computational complexity. And as you can see, our model is lightweight as compared to existing method in terms of flops. And these are some of the visual results on some synthetic data sets. And these are the qualitative results on real world images. This figure shows the application of the proposed method for the tasks such as depth estimation and object detection. As we can see, the outputs of these applications when operated on restored images give better results than when operated on weather degraded images. This shows the applicability of the proposed method for higher level computer vision applications. So in conclusion, we have proposed a comparatively lightweight and unified transformer network for multi-weather image restoration. We have analyzed various training settings, and we have provided extensive analysis on synthetic as well as real world images to show its robustness. So thank you so much for listening, and please visit the project page using the QR code given below. Thank you.
Okay, we have time for one question. we have one question that is asking about efficiency.
Hello, am I audible, sir?
So in the chat room, you will see a question. Do you consider efficiency when using transformer?
So like the main approach was like transformers were giving better results when compared to traditional CNN architectures when we are doing some experimentations. So to add a better performance, like image restoration is a pre-processing kind of step. That's why we have considered efficiency. So we are trying to make the transformers as lightweight as possible.
Okay. Some other question? If not, thank you, Ashutosh.
Thank you so much, sir.
Now let's move to the next presentation.
Present a multi-scale stage network for single image deblurring. For effective deblurring, the coarse-to-fine scheme has been widely adopted by classical approaches, which estimates an initial result from the coarsest level and progressively refines it at finer levels. The advantages of the coarse-to-fine scheme are twofold. First, it enables efficient deblurring, as it allows quick estimation of an initial solution at a coarse scale. Second, it also allows accurate deblurring as the blur size is small on a coarse level, so it is easier to deblur. Motivated by the classical approaches, the coarse-to-fine scheme has also been adopted to recent deep learning-based approaches such as Deep Deblur and SRN. Nonetheless, recently, there have been introduced several deep learning approaches that do not adopt the coarse-to-fine scheme such as DMPHN and MPRNet, which we refer to as single-scale approaches in this talk. Interestingly, the recent single-scale approaches tend to produce higher quality results with similar model sizes than the coarse-to-fine approaches. In this work, we address the following questions. Why do the coarse-to-fine approaches perform worse than recent single-scale approaches? And how can we fix them? To this end, we analyze the defects of the previous coarse-to-fine approaches. Then, we propose a set of simple remedies and a novel coarse-to-fine CNN architecture for deblurring. The first defect is their network architectures disregarding blur scales. Blur spreads a pixel value over an area of the blur size. Thus, to restore a sharp image, it is essential to use receptive fields larger than the blur size. Nevertheless, the previous approaches adopt the same network architecture with the same receptive field size regardless of the blur scale. The second defect is the ineffective information propagation across scales. The previous approaches estimate a deblurred image at a coarse level and pass it to the next level in the image domain. This causes a significant loss of abundant information encoded in the feature vectors at coarse levels. The third defect is the information loss caused by downsampling. To produce multi-scale input images, the previous approaches repeatedly downsample an input image. Unfortunately, downsampling causes significant loss of information as well. So, we propose a novel architecture named MSS-Net with simple remedies to the aforementioned defects. First, MSS-Net uses deeper networks for larger scales to use larger receptive fields for larger blur. Second, MSS-Net passes information from one scale to the next scale in the feature space instead of the image space. This can be also simply achieved by modifying only a small number of layers in the baseline network. Third, to avoid information loss caused by downsampling, we replace the downsampling operation with the pixel unshuffling operation. We evaluate three variants of MSS-Net of different model sizes: MSS-Net Small, MSS-Net, and MSS-Net Large. In terms of model size and PSNR, our models clearly outperforms previous methods, showing higher quality results with smaller model sizes. Our models also perform better in terms of computational time and PSNR. Here we have a qualitative comparison. This result also shows that MSS-Net can achieve better results. To sum up, in this work, we analyzed the defects of previous coarse-to-fine approaches and proposed MSS-Net with simple remedies. Our experiments show that MSS-Net can achieve higher quality results despite its simplicity. Thank you.
Okay, we have time for one question. The authors are here. Okay, so if no question, then Sung-Kyung, thank you.
Yeah, thank you very much.
Andrei, let's proceed with the challenge report for power efficient video super resolution on mobile MPUs.
So the last challenge in the mobile, the last completion in the mobile AI challenges was devoted to efficient video super resolution. And you remember the previous challenge, it was on image resolution, so the task is more or less the same. The biggest difference is that in this case we are dealing with video frames, and therefore we can potentially explore temporal information. So we can use future video frames and previous video frames to predict a super resolved current frame. So this is like an optional stuff. You can use this, or you can even go for the standard single image upsampling approach, which was actually done by the majority of teams. So if you are using a simple image upscaling approach, then this task is basically equivalent to image super resolution. So, and in this competition, the participants had to develop models for 4x video super resolution, and the models had to demonstrate real-time performance on mobile NPUs. And additionally, in this competition, we took into account energy efficiency of the design solutions. Here, the participants used REDS dataset containing video frames of HD resolution sampled at 24 frames per second. And in general, in this dataset, there were 240 videos for training, and the rest of the videos were used for testing and validation. All submissions were evaluated based on PSNS SAM scores and runtime and energy consumption results on the MediaTek Dimensity 9000 SoC. So the models were executed on Dimensity's 5th generation APU and were performing upscaling of images to HD resolution directly on this NPU. And the final score was proportional to PSNR. The final score of each submission was proposed to its PSNR score and inversely proposed to its power consumption. Same as before, the participants could use a benchmark for optimizing their models locally, and also they were able to upload the IT-Flight models to a remote server and get the runtime and power efficiency results, power consumption results on the target Dimensity 9000 NPU. This slide demonstrates the final results obtained in this challenge. So again, the first thing that should be mentioned is that all solutions are extremely fast. There was only one requirement, that they should demonstrate real-time performance, which means that they should upsample videos at 30 frames per second. All teams succeed with this. Moreover, the majority of teams demonstrated a rate and the speed of over 300 FPS. So in this case, they significantly surpassed this hard threshold. And almost all of them also demonstrated quite good power consumption results. So in case of the first two teams, the resultant solutions required less than 0.1 watt for processing 30 frames. And yeah, so the first solution was the most efficient, the most power efficient one. And overall, it can demonstrate quite good, quite good numerical results, and at the same time good runtime results and energy efficiency. In some sense, the best trade-off between numerical visual and runtime and power consumption results was demonstrated by team Gamedia group. So in this case, we can see that its PSNR score and the SAM score is quite high, and despite of this, it demonstrates over 300 FPS in the Dimensity NPU. And yeah, its power consumption is a bit higher, but if like you don't need an extremely low power consumption, then this solution might also be interesting. And as a takeaway message from this slide, I should mention that all top solutions, they were based on single image upscaling strategy. So they were not exploring this temporal dependency, this additional temporal information. And in some sense, this is quite intuitive, because if you are going for this temporal information, then you are going into models with extra connections, with recurrent connections, and this increases the runtime and power consumption heavily. Because in general, you can assume that power consumption is, at some sense, proportional to the runtime. So you're getting larger runtime, you're getting larger power consumption. And with recurrent models, yes, you can potentially get somewhat better results. For instance, this model was a recurrent model. Basically, Steam Super Dash, they just used the provided baseline, which was a recurrent neural network. And yes, this solution can demonstrate the high FPS and SSAM score, but yeah, its runtime is quite huge, and the corresponding power consumption is also large. So if you are really interested in getting as small runtime and energy consumption as possible, then single image upscaling is still the best option for video super resolution. And let's look at the top submissions in this challenge. The challenge winner is team NVIDIA SR. And it proposed an extremely lightweight architecture that consisted of 3 convolutional layers, 1 Prelo activation, and 1 pixel shuffler. And as always, with this model, the hardest stuff is to train it, and even to make sure that the model converges to the results that you want. And to achieve this, Arthos proposed the following trick. First, they changed the number of output channel in this last convolution from 48 to 12. And then they trained the model to perform 2 times image super resolution, which is a much simpler task. And in this case, there are no problems, because the model can easily learn how to perform 2 times image upsampling. After that, they took the weights, the obtained weights, and just repeated them 4 times in the last convolutional layer. Since this layer is followed by pixel shuffle lock, this operation is equivalent to changing the model to do 4 times image upsampling, where 2 times image upsampling is performed by image super resolution, and additional 2 times image upsampling is performed by repeating the output values of repeating the resulting output values twice. And, well, not twice, actually, 4 times. Yeah, in this case, with this simple modification, you're basically getting a baseline model that already performs 4 times image upsampling, and there are no more problems with fine-tuning this model, because it will definitely converge to something that you want. So it won't be the case that the model got stuck and it doesn't know how to deal with this large upsampling factor. In this case, it already does very basic, well, in some sense, yeah, quite basic upsampling, but it's enough to continue training the model and get nice results in the end. And the entire architecture was trained to minimize L1 loss function, and then it was further fine-tuned with L2 loss. The second challenge winner is Team ZX VIP. And here we can, well, the model is based on ECB block. And here we can see our beloved structural reparametrization technique. So same as in the previous top solutions from image super resolution challenge, here the authors used ECB block that consisted of a large number of different convolutional layers, and the authors additionally used Sobel and Laplacian filters. And during the training phase, all these convolutional layers, they exist separately, and they learn quite an extensive set of filters that help to improve visual and numerical results. And during the inference phase, they are fused into a single 3x3 convolutional layer. And yeah, in this case, you're getting plain convolutional model that is extremely efficient. So, and this helped this team to achieve quite good PS analysis M scores. And yeah, the model was trained with Chebanea loss function and then fine-tuned with L2 loss. And the third solution that should be mentioned is the one from GANmedia group. So in this case, the guys basically took last year's top solution from Image Super Resolution Challenge. So this is ABPN that was already mentioned in the previous presentation, and just slightly optimized it. They added an extra skip connection. They replaced summation op with concatenation and 1x1 convolution. And in this case, they got slightly better numerical results and front-end results. And this was enough to get the best fidelity scores in this competition, well, second best fidelity scores in this competition, while still being able to achieve very good runtime and relatively good power consumption scores. And the model was just trained with the standard mean average, mean absolute error loss function. So the description of this and the rest of the solutions is provided in the challenge paper. Yeah, those of you who would decide to participate in the next mobile AI super resolution challenges, and not only super resolution challenges, should probably remember the structural reparameterization trick, because as you can see, this trick helped the majority of teams to get good results. And yeah, all the rest, all remaining important information can be found in the challenge report. So, any questions? Okay, so if there are no questions, then we are moving to the next presentations.
Okay, thank you, Andrei. So the next presentation.
My name is Winnie Ann. Today I'd like to share a paper sliding window recurrent network for efficient video super resolution. Video super resolution, VSR, is the task of restoring high-resolution frames from a sequence of low-resolution inputs, different from single-image super resolution. VSR can utilize interframes temporal information to reconstruct results with more details. However, only a few VSR approaches can be applied to real-world mobile devices due to the computational resources and runtime limitations. In this paper, we propose a sliding window-based recurrent network, SWRN, which can be real-time inference while still achieving superior performance. This figure illustrates the video sequence from the first frame to 60th frame. The top row is the low-resolution frames and the middle row shows the bicubically upsampled frames. Our method is illustrated in the bottom row. Note that the same part of different frames could have different sharpness and details, which enables us aggregate neighboring frames to recover an HR image with rich details. We propose a lighter-weight video super resolution network, known as SWRN, which can be easily deployed on mobile devices and perform VSR in real time. To make the SWRN more efficient while preserving high performance, we propose the sliding window strategy to utilize neighboring frames information to reconstruct rich details. A bidirectional hidden state is incorporated to currently store and update temporal information, which could be very useful to aggregate long-range dependencies to improve the VSR performance. This is the overview architecture of the proposed sliding window recurrent network. The core idea of our method is to grasp and aggregate complementary information from neighboring frames to improve the performance of video reconstruction. The forward and backward hidden states are recurrently updated and concatenated with neighboring two frames to provide extra information to reconstruct HR images. Our model is trained on a high-quality 720p REDS dataset, which is widely used in recent VSR researches. The REDS dataset contains 240 video clips for training, 30 video clips for validation, and 30 video clips for testing. Each clip has 100 consecutive frames. All low-resolution videos are produced by bicubic downsampling with a scale factor of 4. We compare SWRN with FSR-CNN and mobile RRN. The inference times and quantitative results are reported in Table 1. SWRN is more compatible with the mobile TF-Lite GPU delegate accelerator and has lower latency than FSR-CNN. Moreover, we also conduct an ablation study to analyze the impact of the main components of the proposed SWRN framework, sliding window strategy and hidden states, as shown in Table 2. In addition, we also provide the analysis of the impact of the number of channels in Table 3. This is the visual comparison of the video sequence 002 from the first frame to 60th frame. One can see that video sequences produced by our method are much sharper and clear, and are visually pleasant. The result demonstrates our method satisfies the realistic runtime requirement while preserving a high PSNR performance. Thank you.
We have time for one question. If no question, we move on to the next talk.
Hello everyone. Today I am going to talk about EESRnet, a network energy efficient superposition. I will explain how the following three aspects. First is the research significance. It is urgent to design a lightweight super-resolution network with high performance, low latency, and low power consumption. Next, I will describe our proposed method. First, we propose an energy-efficient super-resolution method that can effectively balance the performance and energy consumption of the network. Second, we implement a video super-resolution network based on hidden feed alignment, which can be easily deployed on mobile devices. Finally, based on extensive experiments, we design a simple energy-efficient super-resolution network with structural downsizing of EESRnet. Now, I will present the details. Inspired by ADPN, we use 2D convolution to build our EESRnet. The entire architecture is shown in the figure. It mainly consists of 3x3 convolution operations. The shape of the feature maps remains unchanged before the depth to space layer. The key difference between video super-resolution methods and image super-resolution methods is the temporal information between the frames. Inspired by RRN, we add temporal information to EESRnet, named TEESRnet, as shown in the picture above. It proceeds in a single loop fashion while exploiting hidden features and accumulate temporal information of video sequences. In the Mobile AI 2022 challenge, we submitted a simple version of the EESRnet. It only contains 3 convolution layers. The first convolution layer is a 3x3 convolution with 16 output channels, while the last 2 have 48 output channels. In short, the SEESRnet is an energy-efficient network which fully benefits from its simple network structure. In addition, the full INT8 quantization further reduces its power consumption. Finally, we come to the results. As shown in the branch region in the figure, our proposed TEESRnet can reconstruct more details, and the EESRnet as well as TEESRnet can generate results similar to mobile RRM while ensuring low energy consumption. Our method achieves a nice place among all the 13 teams in the Mobile ARN 2022 real-time video super-resolution challenge. As shown in Table 1, EESRnet has the same amount of parameters with ADPN, but can reduce latency by 1.57 milliseconds. As shown in Table 2, adding temporal information to the network results in a 0.24 decibel increase in PSNR compared to EESRnet. This proves that adding temporal information can effectively improve the performance of the network. On the other hand, compared with mobile RRN, we remove a large number of residue modules and use the more powerful EESRnet as a backbone, which improves the performance by 1.19 decibel. As shown in Table 3, DCEnet brings a performance improvement of 0.18 decibel and a latency reduction of 1.33 milliseconds. As shown in Table 4, the REST block and SE-REST block can improve performance by 0.14 decibel and 0.2 decibel compared with the conf block, while they also increase of latency by 1.68 milliseconds and 2.50 milliseconds respectively. Table 5 lists the experimental results on the different architecture settings of EESRNet. Based on the scoring criteria of the competition, we finally choose the last line in Table 5 as the parameter setting of SEESRNet. The above is all the content of my paper. Thanks for listening. If you have any questions, please email me.
Okay, so this was the presentation. Move on to the next one.
Hello, I'm Ying Qian Wang from National University of Teaching Technology. In this presentation, I'll briefly review our work on light field angular superresolution. Light field angular data, also called as light field reconstruction or field difference, aims at reconstructing a discrete sample light field from a partially sampled one. To achieve accurate angular data, it is important and challenging operate the complementary information of the view, especially with dealing with large disparities shown in the right figure. In this paper, we propose a method for light field angular data via the correspondence field reconstruction. Here are the main contributions of this work. Note that our method can well incorporate the light field structure required at handle large disparities. Inspired by parallel excitation mechanism in theory that we try to modify the parallel excitation for light field angular data. This figure shows the correlation among different fields and their corresponding maps. According to the light field geometry, the slopes of oriented lines in EPI reflect the disparities among different fields, and the same object in different fields corresponds to lines with the vertical shifts. Motivated by the above observation, we can reconstruct the correspondence map of five by shifting the line in the correspondence map of corner as shown in the figure. Similarly, we can further generate the correspondence map of internal view by shifting the correspondence map of side view, and finally reconstruct the dense correspondence field. We developed a network to achieve angular SAR based on dense correspondence field reconstruction. Specifically, by using the dense correspondence field, the internal views can be synthesized by performing a simple batch arithmetic multiplication, such as the one used in the parallel excitation mechanism. Note that to achieve a higher reconstruction accuracy, both views and features are projected to the partial position based on the correspondence field. Finally, a light field with higher angular resolution is reconstructed. Here are the quantitative results produced by different methods. Our method can achieve comparable performance with SOTA method on lateral datasets and achieve superior performance on HCI datasets with larger disparities. Here are the visual results produced by different methods. By visualizing the reconstruction error, we can observe that our method achieves higher reconstruction quality as compared to SOTA method. Finally, we visualize the horizontal and vertical correspondence maps of extractive patches. In this case, the disparities between input views are about 20 pixels. For the correspondence map between input views, the values represent the degree of similarity of correspondence points. In this figure, we can clearly see that reliable correspondence can be built by our method. That's all. Thank you.
Okay, we have time for one question. Okay, if no question, let's move on.
Hello, this is Mingyong Cao from Tsinghua University. I'd like to present our work at AIM 2022 towards real-world video deep learning by exploring the neural formation process, which tries to tackle the real-world video deep learning problem on the data side. Video deep learning is a fundamental task that removes the blur artifacts through effective spatial temporal modeling. Although many methods have achieved highly competitive results on multiple datasets, they still can hardly remove blurs in the real-world blurry videos. As shown in the figure, the models trained on existing synthetic datasets cannot remove the blurs in the capture of blurry video. An direct way to tackle the real-world video blurring problem is to collect real data pairs. Yet the collecting process requires specifically designed imaging devices and suffers from misalignment problems easily. Therefore, developing a realistic blur synthesis pipeline is significant for us to construct large-scale datasets to tackle the challenging real-world blurring problems. To do so, we first revisited the formation processes of real-world and existing synthetic blurs to figure out possible reasons of the performance gap. And the comparison is shown in the left figure. We have found some potential reasons shown in the right table to attribute to the gap between real-world and synthetic blurs, including the formation space, imaging noise, ISV, and so on. More detailed analysis can be found in our paper. Therefore, by considering these factors, we propose a novel realistic blur synthesis pipeline to generate realistic blur sharp pairs for model training. First, we collect an ultra-high frame rate raw video dataset. The high frame rate can help us synthesize more continuous blurs shown in the figure. Compared to existing datasets, the blurs synthesized by our high frame rate videos are much natural. Meanwhile, these raw clear videos can help the community construct their specific blur datasets. Next, based on the blur formation process, we propose a novel blur synthesis pipeline to generate close to real blurs. Firstly, we should set the video parameters of the synthesized blurry video as close to the real-world blurry video as possible. Secondly, the blurs are synthesized in raw space by averaging several consecutive sharp frames, and further added the reduced noise during the averaging process. And then, the blurry raw frames are rendered into RGB frames with the same ISP of the real-world blurry videos. Let's see some deblurring results of DVR model. Obviously, the model trained on existing synthetic datasets cannot remove the blurs in this real capture scenario. Compared to these datasets, thanks to the realistic blurs generated from the proposed pipeline and the dataset, we can see our pipeline can help the model remove the blurs and restore the sharp text. One example can be found in our paper and supplementary material. We will release the project at GitHub. Thanks for listening.
Okay, we have time for a question. So, if no question, then let's move on to the invited talk, the fifth invited talk of the day. So we have Dr. Bo Zhu from Meta Reality Labs with us, and he will talk about practical considerations for one-device denoising. Bo, are you ready?
Yes. Can you see me?
Yes.
Okay. I'm going to share my screen real quick.
Perfect.
Does that work? Okay, great. All right.
So
well, thank you, Radu. Okay, awesome. Thank you, Radu, for organizing this workshop and providing me the opportunity to speak here. I want to say just up front, I'm relatively new to this community. Academically, my wheelhouse is in medical imaging, in particular with MRI image reconstruction and developing deep learning-based approaches there. But a few years ago, my startup, which was based on this in medical imaging research, pivoted to computational photography. And we ended up developing some real-time video denoising products that were commercially deployed on smartphone OEMs. So today in this talk, I wanted to focus on some practical issues related to on-device denoising that we've encountered both at the startup and even more so now at Meta, where much of our team is now. And I wanted to give a quick shout out. One of our team members, Haitao Yang, has been really critical and driving many of these efforts and ideas that we'll be presenting. So to start off with, I don't need to tell anyone here that smartphones and wearables have small image sensors. For example, going from a full frame DSLR sensor to a smartphone sensor cuts your sensor size by around 20x, which reduces inherent SNR by about 26 dB. But for those unfamiliar with AR glasses, it may be surprising to know how much even smaller the AR glasses sensors typically are. It's going to further cut down your photon capturing area by around 9 or 10x, resulting in additional 19 dB SNR drop. So this means we have very noisy raw images to work with, and therefore good video denoising is critical to improve these frames, both for consumer photo and video image quality, as well as downstream computer vision tasks. To set the frame for the rest of this talk, I really wanted to focus on the fact that, of course, very efficient models are going to be critical for both single frame or burst or video denoising, and especially for real-time enhancement in AR and MR settings. So one of the things that we have to be cognizant of is we can't perform frame-based pipelining. So you can't take pre-processing and then, let's say, a neural network, denoising, and then some post-processing at different frames that are pipelined. That's going to produce unacceptable end-to-end latency. So, for example, if we're talking about 30 or 60 FPS, that's tens, maybe close to 100 milliseconds in delay end-to-end if we go with that approach. So at the end of the day, for example, if you go, we have a 60 FPS setting, that means we only have around 16 milliseconds for all of these stages that I talked about, including the ISP, which can be very very time consuming. We had to do this often on 2 cameras for left and right, and at a high resolution if we're doing, let's say, raw denoising. And all of this on a very low power SoC. So at the end of the day, we might only have a few milliseconds for the model to do this high resolution denoising. And of course, we do. One last thing is, and for MR applications, we're further constrained by comfort and nausea of the user due to real world versus perceived mismatch, and it's very sensitive to that. Anyway, so we have to do all this within a very limited latency, and of course we do have in-house silicon efforts and custom hardware accelerator architectures to help with this on the hardware front. And we do a lot of hardware and software co-development, but we really have to think about the efficiency of the AI model from the ground up, and prune away as much as possible to allow the network to do the pure task of denoising, going from X plus epsilon to X, and really nothing else. And that starts with how we think about the training data. By now there's a pretty established understanding that using realistic but synthetically generated noise is the way to go for supervised denoising training. But I really wanted to look a bit deeper into why synthetic noise is conceptually advantageous, particularly for efficient models. So, when we think about the synthetic noise paradigm, one of the first things that comes to mind is that we can rapidly produce an unlimited data set size for any sensor, right? So there's no need to capture hundreds or thousands of different scenes. Depending on how many sensors you're doing this and how many ISO and exposure levels, this would need to be repeated many times, within each scene, right? And so there's a practical issue there that is just very time consuming and resource consuming. But even if you had the time and the resources to go out and do all this, there are still additional issues if you want to work on, real world data set capture. So the first thing, and I think a lot of us have maybe worked in this, dealt with, is the fact that for real data collection, using, for example, a long exposure ground truth, really you want to be perfectly aligned with the input and the output, the long exposure and the short exposure, if that's the way that you're going about producing this data set. And that requires really zero motion of the subject in the background, and also zero ego motion, which means zero camera motion, and that's more easier to control. The subject motion is a lot harder to control. And during this long exposure, it has to be no motion. That would cause not only input and output misregistration if you're sequentially capturing this, right? But also there will be blur, of course, during the long exposure, and that's a confound that you don't want to have in your data set. This is very challenging with outdoor scenes, especially with natural grass and leaves and other things moving around in the wind, and scenes with people or animals. So indoor lab settings, maybe that's a little bit easier to do, but once you're out in the real world and you want to get a lot of data set variety, that's going to be starts to get pretty hard. And this misregistration can it can be potentially be alleviated with optical flow and alignment, let's say, but that depends on, first of all, the quality of those algorithms. Just adds a lot of complexity into this into this pipeline, right? And so at the end of the day, if we don't take account of these confounds, then the model will have to learn things like registering the frames, or at least being robust to non-registered frames, and you don't want that extra task complexity for the model to have to take care of. Another way that one might think about doing this instead of long exposure versus short exposure is, let's say, changing the lighting conditions, right? Just simply, let's say, if you're in an environment where you can control the lighting condition, then you can go low lux and high lux, but that would vary the scene illumination non-uniformly. So now, if you go with that approach, the neural network denoiser is handling more than just the pure denoising problem. And the fact that if you're doing this over many hundreds or thousands of frames, and you're not doing the exact sort of lighting change increase, that would push the function approximation problem from a one-to-one to a one-to-many, since there would be multiple ground truths for each pixel and for each pixel or each image pair, right? And so there are multiple ground truths that are possible within that framework, and that's really challenging for a small network to have to deal with. And this would still suffer from the previous misregistration issues that we talked about. We can think about, let's say, a neutral density filter that can potentially solve this illumination uniformity issue, right? But practically that can introduce reflections if it's not perfectly installed. And it's going to be a real hassle mechanically inserting and removing this neutral density filter mechanically. The process will likely introduce camera motion or vibrations, and again, that would cause misregistration between the input and the output. And finally, one can imagine maybe using electronically controlled neutral density filters. Those would also have the additional advantage of doing multiple darkening factors, right? But these electronically controlled NDFs, most likely will use LCDs, and that's been demonstrated to introduce chromatic aberration and fringing artifacts into the scene. And again, this is yet another confound that you don't want to have the neural network to have to deal with. And finally, one can think about perhaps using a camera that's aimed at a TV or a projector that's displaying synthetic scenes, right? So you're going to have this pseudo-synthetic setup where you're using the camera and the real camera capture with the real noise profiles from the camera, but you're able to, let's say, synthetically put in the scene, and so that might help with the whole not going to thousands of different physical locations problem. But the problem is that when we're looking at these TV or projector blade scenes, these are discrete pixels, and not only is it going to introduce moire artifacts, but the resolution of the image sensors that we're dealing with typically are much larger than a 4K or an 8K resolution, right, from your TV or projector, and that means that you're going to have blurry details, and so it's really not an ideal type of situation to be in. And the other thing is that for low light scenes that we often care the most about during denoising, right? The black level of the TV or the projector is not zero. And so this, even the state-of-the-art OLED screens have black levels of around 0.2 nit, or that converts to around 0.6 lux. And we often care about scenes that are lower than that. So yet again, this is a potential. These are issues that we have to deal with. If you don't use synthetic noise training. And thus far, I've primarily been talking about in the single frame, photo capture setting. For video, it becomes even worse, right? So we have all the same real world data collection issues that we talk about from the images that applies to video, but also the fact that low light and ground truth data can't be captured sequentially, right? We have real world motion that is unrepeatable, unless of course you're using that TV and projector setup, which had those issues that we discussed, right? But in real world environments, you're gonna have to capture synchronously or simultaneously, right? And even then, we have to assume, let's say, a neutral density filter type of setup, because we can't, for example, do simultaneous lighting conditions. We can't do long exposures, right? I mean, that's just going to be impossible with, real world frame rates of 33 milliseconds that you're stuck with when you're doing video capture. And so even this is quite limited to just the NDF sort of situation. And in that case, it requires highly synchronized captures where the exposures for each frame start at the same exact time at the sub-millisecond level. And so there are just additional complications there of synchronizing the two captures. And then, even if you, solve for all of those things, then there's misregistration between the two cameras that need to be corrected, right? With, let's say, optical flow and alignment, you have occlusion problems. I mean, it's just not going to be an ideal setup. And so this is all a very kind of roundabout way of really emphasizing the importance of synthetic noise training, right? All these issues can be avoided with a synthetic data set pipeline, which really ends up, at the end, they simulates the scene as if you just taken it with a larger sensor. And so, the typical pipeline, as we very often know now, is we do a noise characterization of the sensor. We apply this model to a ground truth, which has been unprocessed, right? So if you're taking like sRGB images, we unprocess that to your linear raw domain, take care of things like color correction matrices and white balance, so on and so forth, and then apply some additional pre-processing, which we'll be discussing about, to make the problem even simpler. And then, of course, we do the training, after that with the supervised data set. So, I want to talk a little bit about the data collection process of the sensor noise model. Just there are practical issues with this. We need to get the noise versus signal curve, or essentially the photon transfer curve. And the conventional way to do this PTC characterization of the image sensors is to use something, like flat field uniform light sources, whether we're talking about flat field illuminators or integrating spheres. These can be very expensive, going from, the thousands or tens of thousands of dollars often. And, even with these expensive equipment, there's some practical issues. So for example, there's lens vignetting, right? So you capture the data with your camera module, and you'll get this, with almost all lenses, you get this lens vignetting and shading, which causes this non-uniform response. And it's a non-trivial issue that must be corrected, right? Because we are spatially computing these noise characteristics. Of course, it's certainly possible to do this, but it just adds an additional, part to this that you had to get perfectly correct. Typically with integrating spheres, we're talking about 95%, uniformity, right? And that's just of the light field itself. You have to then correct and get that same uniformity, in a post-process lens corrected, lens shading corrected way to really get the full precision of this method. And, depending on how you're sweeping through this PTC curve, it's often by changing exposure time, but noise characteristics are often exposure time dependent. And so in order to have really accurate noise characteristics, we really want to do this for a single exposure time across the dynamic range of the sensor. And so we actually need to change the illumination instead. And that leads to another issue, which is that for low light scenes, right, when we really want to capture this, the lowest DN values and how the noise corresponds there, the illuminating sphere needs to be very stable and have very fine low lux resolution, but many integrating spheres are unable to produce stable illumination below 25 lux. And so these are all practical issues that we need to deal with when we're using these integrating spheres or some, other forms of flat field illuminators. And of course, the last thing is, depending on the budget, the equipment expense is non-trivial. So, one of the ways that we can avoid a lot of these issues and have a very cheap setup and collect, the SNR curve data, for denoising purposes, is something like this, where you set up an LED flashlight such that the entire dynamic range of the sensor for a given exposure and gain is collected within the single field of view. And you can rapidly collect, let's say, 1,000 raw images or so. Depending on the setup, it may only take 30 seconds or a few minutes. The noise characteristics are computed temporally with respect to pixel-wise intensity instead of spatially with uniform illumination level, right? This is basically how you get the statistics now, and you could basically take an ensemble, statistics, over all these, and you have very, very high resolution, right, in terms of the pixel intensities here, because you have a very natural roll off, from the saturation point down to the black level. And, again, all within the same scene. You have megapixels and megapixels to work with here. And most samples are at low intensities near the black level, where the accuracy of SNR characterization is most important for low light denoising applications. And, couple things to take care of. I mean, so the LED light source must be stable in both intensity and mechanical positioning. Stability is usually not an issue, and in terms of the LED stability, but mechanical positioning, you really want to make sure you have less than a pixel shift or so over the raw capture session, which can be very short because, again, we're just taking, a single, rapid burst of, let's say, hundreds or 1,000 raw images. The assumption here, of course, is that the noise is pixel-wise independent, but we can correct FPN beforehand, and the dynamic streak noise can be characterized separately. These are sort of separate issues here, right? I think really assuming that you have pixel-wise independent noise, this can be a very good way of characterizing your sensor noise. Now, a variation of this technique was also described very well in Wang et al.'s paper in ECCV in 2020. In that case, they use essentially a paper, right, to do this intensity variation going from dark to bright. The issue there is that the contrast ratio of paper is typically 100 to 1, which would require multiple captures at different base lux. And then the reason is because the dynamic range of a sensor that you care about is typically 1,000 or 4,000, right? 10-bit or versus 12-bit sensors. And so we would take a little bit more time, and then you'd have to might have problems with registration between the different captures. And so an angled LED light that was described previously in a completely dark room, we can achieve the entire dynamic range from less than 0.1 lux to around 1,000 lux within a single field of view, within a single session. So next I want to talk about the pre-processing stage, and running low on time here, so I'm just going to kind of quickly run through some thoughts there. There are a lot of things that we can do to prepare the data to make the denoising problem simple. I want to just focus on one of them, which is the variance stabilizing transform, which is a pretty common technique. But as we know, we can convert a noise versus signal curve with a typical profile like this, kind of a square root based sort of standard deviation curve like that, into a constant standard deviation or variance over signal intensity like this. One of the most common ways to do this is with the Anscombe transform. There are other methods as well, but just to show here that and the analytical inverse, as well as the exact unbiased inverse during post processing that you need to do. And the reason why this is important is because first, it reduces the problem to a single variance additive white Gaussian noise denoising problem, right? But also it's a good approximation for gamma correction. We're operating in the raw domain, which is linear, and that doesn't correspond to more perceptually relevant domain, which is logarithmic as per Weber-Fechner law. And so, this variance stabilizing transform would be typically on the, providing a power of about 0.45, which is actually a good approximation for gamma correction, which is around 0.45. And this gamma correction is one of the ways that we get into this more perceptually relevant domain. And this means that your loss is going to be more perceptually relevant instead of being in the linear domain during training. And it also enables denoising of the entire dynamic range of the sensor by doing this nonlinear compression. And that's particularly important for effectively representing the raw input, which can be 10 or 12 bits, right? As well as the intermediate features within the, within your network when you're in an 8-bit quantized domain. So as a, just kind of simple illustration here, if we have just a linear 8-bit quantization on a 10-bit raw, then what we see here is that we have we're basically taking in and kind of compressing away all these really important values in the low light pixel intensities, right, and just mapping them to to these discrete 0, 1, 2, 3, 4 values. If we do variance stabilizing transform, again, not only does that simplify the problem, but then it also allows us to distribute the bits in the low intensity values where distribute them well and accurately represent them well in the low light areas where it's most important. Oops, sorry, I think I accidentally, okay, here we go. Okay. And just a quick kind of demonstration of this in a very low light scene on a very simple, small convolutional network. We see here that, without a variance stabilizing transform, especially when you quantize it, you get all these nasty artifacts, especially here. Yes.
We don't see what you are showing there.
Oh, I see. Okay, let me, can I,
Share
let me reshare the screen then. Okay. Can you see it now?
Yeah.
Okay. Sorry about that. Disconnected the monitor accidentally. So in this very low light scene here, again, without VST, then we have just a lot of these chroma noise artifacts that come into play, and a lot of the features here, are kind of blurred away, right? But they're preserved really well, in the VST version, and there's very, very little difference between the quantized versus standard floating precision, with VST on. So the last thing I wanted to discuss, again, starting to run low on time here, very quickly, is if you're in the this is more on the product side, where there are some camera embedded devices that may not have the compute available to run neural network inference, right? And so to enable this type of raw AI denoising that we've been talking about, the raw captures in these sort of settings would require a wireless transfer to enable to a capable compute platform. So for example, a cloud server, or let's say a local smartphone. And one of the problems there would be that the raw compression is kind of necessary, because transmitting a very large uncompressed high bitrate raw would excessively drain the battery, and also introduce long latencies. And so in this sort of case, we would be want to do something like where on the capture device, you would do the capture and then the compression, and then on the more capable engine, we would do the decompression and then the denoising on that. And one of the things to keep in mind is that we really can't do things like neural compression, because again, in this case, we're assuming that we have limited compute available. And so at this time, I'm really unable, unfortunately, to go into many of the details, but to give a sense of what we can do to achieve this, what we have on the left here is the same network architecture and everything, and it's denoised with JPEG compression, let's say a 7:1 ratio, but with a enhanced raw compression. We're able to achieve not only a better compression ratio, but much higher image quality. So sorry to go over on time here, but thank you for listening, and available to answer some questions.
Okay, thank you very much. So do we have questions? So if you have questions, just unmute yourself and ask directly, or you can just write in the chat and go with the respond. Okay, while we are waiting for your questions, let me ask a couple. So what is better, standard buyer or quad buyer for denoising?
Yeah, I think it. Yeah, that's a very good question. Quad Bayer, you can do binning, right, to increase your SNR, especially if it's charge domain binning. I think for video cases, that's definitely the way to go, especially because people expect lower resolution, so you can bin and get the higher SNR right off the bat. If you want a quad Bayer, for stills, that starts to get into more challenging domains, because now you have to demosaic, right, at the original high resolution. Then that becomes like a AI demosaicing problem, and we can do, of course, very well with that. But yeah, I would say, generally speaking, we would prefer quad Bayer if possible, if we're talking primarily about video.
Okay, another question. What is better to work with, a single shot or a multiple shot? in a different way of saying, with a burst mode or not?
Yeah, I mean, if you can take care of the motion with with burst, I think that would generally be better, right? And I think that's really the main issue is how compute heavy is your motion estimation and compensation on device. But yeah, if you can take care of that really well, then being able to capture more light over those frames, that allows your neural network to do less, right? With that and higher SNR coming in. Yeah, so that would be ideal.
Okay, another question. Your talk was quite generic and was not targeting like a specific hardware or camera. Okay, so could you give some examples? For example, if we are targeting something like Oculus or some other product from Meta, okay, in the end, what is the philosophy here? To do most of the compute directly on the as close as possible to the sensor on the device, or to like you mentioned here, to do some compression and eventually afterwards to do some operation?
Yeah, I mean, for real world, real time, not real world, for real time applications where it's, let's say, mixed reality, right? I mean, I can't go into all the details, but one can imagine that the latency really becomes a really important issue, and so it's going to be that's a problem you would have to deal with if you're doing a offload sort of scenario, right? Like even the compression, the compression itself, even forget transmission, right? Just even the compression, is a time factor there. So it's just even from a sort of conceptual perspective, the offload is a lot more of a sensical operation when you're not in a real time setting, right, where the latency is a little bit more unconstrained.
We have a question from Yildi. Yildi, if you want, you can just unmute yourself and ask, or I could just read your question. So, have you also considered fixed pattern noise for generating synthetic images, or only photon shot noise?
Yeah. So, I mean, so we can, let's say, we can synthesize fixed pattern noise in there. Ideally, you want to take care of the fixed pattern noise at the source, if possible, because first of all, it's really depends on the product we're talking about and the exact configuration of the hardware, right? But it's usually solvable. A lot of these you can get to pixel independent noise, if the sensor is, the register settings are done correctly and you don't have power supply issues. It's usually that's where you want to solve the problem. But yes, if you're forced into a position where you have to take care of FPN, then we would have to synthesize that, right, and put that into the training data.
Okay. Do we have some other questions?
Yes, Radu here. So
yes,
thank you so much for your presentation, Bu. Yeah, really interesting. I hope that we have the slides soon at the AIM website to have a look later. So my question is, what I understand from your presentation, most of the processing, let's say the heavy processing is done in the raw domain. And looks like, you really take care of the raw images, and then after that, you just process them with an ISP. So in terms of workload and processing, how much is done in the raw domain and how much is done in the sRGB domain? If you can share some insights.
Yeah, well, so just talking at a high level, the denoising problem is more tractable, and it's a simpler problem in the raw domain because you don't have intermediate ISP modules messing up the noise characteristics, right? Depending on how much, pre-processing has been done, a lot of the noise may have been destroyed, right, in the process, and so that's either irrecoverable or that's yet or you're in a regime now where you have to have the network learn how to recover that, right? And that just again makes the network do more things. That being said, one can imagine well, yeah, so I'll kind of keep it there. I think to address the second part of your question about let's say kind of splitting up the workloads, right, between let's say ISP denoise, raw denoising and some sort of post-process ISP denoising at some point downstream. Yeah, I mean, one can imagine ways that could be beneficial, but it really depends on the details of for example, do you even have a software ISP in the chain to do this, or where in the where that ISP is located, let's say. But yeah, I mean, kind of combining raw denoising and sRGB denoising, there can be definitely some benefits there. Yeah.
Okay. So
thank
you, Bo. And if there are no other questions right away now, keep in mind that always you could send a question by email to Bo, and definitely he will be happy to provide you some response. Thank you very much, and we will move to the next presentation. This is the challenge on super resolution of compressed image and video. So Ren?
Yes. Okay. Hello everyone. I am Ren Yang from ETH Zurich. So our challenge is on super resolution and of compressed image and video. So the background is that nowadays there are increasing amount of videos transmitted over the internet. However, the bandwidth of the internet is limited, and the storage on our device is also limited. So in this case, that video compression plays an important role for significantly reduce the bitrate and facilitate the transmission of videos over the internet. But video compression will lead to the quality loss in the compressed video. So it is necessary to study on the quality enhancement of compressed video. And moreover, if we want to recover TV series which has been captured like 10 or 20 years ago, then it is not only with the poor quality because of the compression, but also it is usually with a low resolution. So in this challenge, we focus on the super resolution of the compressed video, which means that we aim at both the super resolution and the quality enhancement of the compressed video at low resolution. And our challenge has two tracks. So the first track is for the super resolution of compressed image, and the second track is for the super resolution of compressed video. For track one, we generate the test samples by first downsampling the images with the factor of 4 by the bicubic algorithm. And then we compress the downsampled image by JPEG with the quality factor of 10. And our target is to recover the high resolution image. And we will rank the performance by the performance of PSNR. And in the second track, we also first downsample the video with the factor of 4 and compress the video by the HEVC codec, by the official HEVC test model HM16.20 with the low delay P configuration at the QP of 37. And for the first track, we use the DIV2K dataset, which has 800 images for training and 100 images for validation and 100 images for test. And for track 2, we use the proposed third version LDV dataset. Okay, so I will first introduce the proposed dataset. It's the third version of the LDV dataset, which contains 365 videos, which includes the videos from the second version and plus 30 videos proposed in this challenge. So the videos in our LDV dataset are collected from YouTube. And to ensure the high quality, we only collected videos with a 4K resolution and without obvious compression artifacts. And all source videos used in our datasets have the license of Creative Commons attribution license. And to remove the compression artifacts of the collected videos, we downscale the videos by the factor of 4. And we also crop them to ensure that the width and the height of each video are the multiples of 8, because this is the requirement of the HEVC codec. And we also follow the standard datasets of JCTVC to convert the videos to the format of YUV420. And in our dataset, we have the categories. We have 10 categories of scenes that include animals, cities, the close-up videos, the fashion videos, the human, indoor, park, scenery, sports, and vehicle, and also with different kinds of motion and the large range of frame rates and etc. We will introduce the diversity in the next page. And in the track 2, and we use the original, the second version of LDV dataset as for training. And we also collect 30 more videos, including 15 videos for validation and 15 videos for test. And this figure shows the 10 categories of our videos. So we can see that from the content aspect, we have a very good diversity. And also, we also take care of the diversities on the motion, frame rate, and some other camera configurations. For example, we have 80% of videos with a relatively slow motion and 20% of videos with a very fast motion. And our frame rate also ranges from 24 to 60. And we have around 30% of videos are captured by the handheld cameras. So it has some slight shaky features, slight shaky in the captured videos. And the others, around 70% videos are captured by the steady camera. And we also have some videos with a dark light. And this page shows the result of track 1. So track 1 is for the super resolution of JPEG compressed image. And we can see that the top ranked teams improves the quality upon the simple bicubic upscaling by around 1.4 dB. And we have set our CodeLab server to be active. And so if you have some new methods, you can also test your performance on our CodeLab server to compare with this participated teams. And we can also see from this table that the top ranked teams usually consume high computational complexity. For example, the winner for the winner team, it takes like 2 minutes to process one image. And the most teams also use the very good performed GPU. And this table shows the test and the training details of each team. And we can see from this table that that the Flickr 2K is the most popular extra training data used in these teams. and also one team used ImageNet. And all these data sets are public. And so one data set called Flickr2KL, which is generated by the BSR teams themselves. So we have also make their data set available on our homepage. So this ensures the reproducibility of these methods. We briefly introduced the methods proposed by the first two teams. The winner team is the UVE team, who designed a two-stage method. So the first stage aims at removing the JPEG artifacts, and so they use the convolutional neural networks based on the Swing V2, which contains some transformer layers. And the second stage aims at the super resolution, and they use the residual dense block net for the 4 times the super resolution. And the second place team is the BSR team, whose method is based on the HAT method, which is originally proposed for super resolution. What they proposed is to use a multi-patches training scheme. That means that when they train the HAT framework, they use not only the current patch, but also the neighboring patches, which has a similar contents with the current patch. And they observe the performance improvement on our task. And for the third place team and other 2 teams, the authors will present their paper after my presentation. And for the track 2, there are only 2 teams participated in our challenge. So the first ranked team is the Noya Terminal CV team from Huawei. We also compare its performance with our entire winner. And we can see from this table that they have around 1 dB improvement upon the entire winner. And actually, they have also attended our entire workshop several months ago. And in the entire workshop, in the entire challenge, their performance is comparable with the winner. And then in our AIM challenge, they have a significant improvement over their previous methods. And for both their entire and AIM methods, they use the same framework. That is, the first do an initial super resolution on the original patch, and then they select some similar patches in the feature domain, and then after they collected the similar patches and they use all these patches to help the current patch for the super resolution and the removal of JPEG of HEVC artifacts. And so the improvements from their entire methods to their AIM method is mainly on the architecture of the framework. That is, they used a more complicated architecture at the cost of a higher, more heavy computational complexity. For example, in their AIM, in the method for the AIM challenge, their model consumes 21 days using 8 V100 GPUs for training. And they also collected a very large training data set, which contains 90,000 videos from YouTube. So this makes their significant improvements upon the entire method, and then become the winner of the AIM challenge. Okay, and so this page collects our report. So if you think that the methods proposed in our challenge is useful for your research, please cite our paper. And we will also release our proposed data set. And we will also update the challenge home week in homepage in like 1 week. And you can pay attention to our homepage and the data set if you are interested in it. Okay, and thank you very much, and congratulations to the winners.
Thank you, Ren. Do we have any question? Okay, so if there are no questions, then thank you again, Ren, and let's go for the next talk. One of the methods in this challenge.
Hello, everyone. I'd like to introduce our paper, CIDBNet, and our team is CATIA LCVG. Compressed image super resolution is very useful in data transmission. On one hand, image compression technique can save bandwidth, but leads to undesirable artifacts. On the other hand, downsampling can reduce computation costs, but further degrade image quality. Therefore, the core issue is how to reduce compression artifacts and retain high-frequency details for super resolution. To solve this problem, we propose a consecutively interactive dual-branch network. The overall architecture is here. Given a compressed or low-resolution image, 3 stages are applied. In the second stage, each feature mixing block contains a 2-branch unit, that is, convolution group and a transformer group, and an adaptive cross-branch fusion module to aggregate the 2-branch features. Transformer group aims to utilize long-range pixel interactions. It adopts the same structure of HAT, which uses several hybrid attention blocks and an overlapping cross-attention block. Based on HAT, we integrate the gated DCON feed-forward network into attention blocks to enhance them. GDFN uses a depth-wise convolution to leverage local information and a gating scheme to control information flow. Convolution group aims to extract useful local features. It consists of several NAFNet blocks. NAFNet block includes simple gates and simplified channel attention without any nonlinear activation function. In order to effectively develop features and global representations, we propose an adaptive cross-branch fusion module, referred to as ACFM. Specifically, given local feature XC and global feature XT, the cross-attention features FT2C and FC2D are computed respectively. 2-branch features are enhanced by adding attentive features. Then, an adaptive map is calculated based on image contents and serves as weights to fuse 2-branch features. Next, let's see the experimental results. In Table 1, we gradually modify the baseline model HAT and compare their differences. The second column represents a single-branch convolutional model. The third column is the baseline transformer model. Results show the effectiveness of GDFN, ACFM, and the dual-branch structure. We also explore the effects of ImageNet training in Table 2. ImageNet training significantly improves the PSNR. However, fine-tuning ImageNet pre-trained model causes a slight performance drop. Based on this observation, we only use ImageNet for training as a challenge. We compare our method with 3 cascading and 3 state-of-the-art resolution methods. Cascading methods apply artifacts removal and the super resolution algorithm step by step. Our method has the highest PSNR. In particular, it surpasses HATL, which has twice the depth of HAT. And from visual comparisons, we can observe that the results of our method have less excessive blurry artifacts and preserve sharper edges. Finally, we give some conclusions. CIDBNet aims to couple local features with global representations to enhance feature learning. And we introduce ACFM, which enhances 2-branch features across attention scheme and adaptively fuses them. Experiments show the superiority of our method. That's all. Thank you.
Okay, we have time for one question. If no question, then we move to the next talk.
Hello, everyone. This is Li Bingchen from University of Science and Technology of China. Here I present our work, Hierarchical Swing Transformer for Compressed Image Super Resolution. We joined AIM 2022 Compressed Image Super Resolution Challenge and take the 5th place. In this paper, we focus on artifacts removal of highly compressed and downsampled images. Most previous works only focus on compression artifacts removal or image super resolution tasks. Few of them jointly consider these two distortions together. As shown in picture, the hybrid distortion becomes more severe than compression artifacts or downsampled distortion alone. Considering these, we propose the hierarchical swing transformer network to jointly capture the hierarchical feature representations and enhances the distorted images. Considering that hierarchical network architecture has the advantage of strong representation ability, and swing transformer can effectively capture global and local information of image, we combine these two parts together to form our HIST. Our network is combined of 4 parts. Firstly, hierarchical feature extraction module. Previous works have revealed that extracting hierarchical features at different scales from images and processing them in a divide and compare manner can provide the network a strong representation ability, and thus can deal with more severe and complex image degradation. In details, the input image is gradually passed through 3 different convolutions to extract the hierarchical representations with 3 scales, that is, the original size, the half size, and the quarter size features. Secondly, feature enhancement module. As the hybrid distortion is difficult to remove, we adopt transformer-based architecture rather than previous CNN-based architecture, because swing transformer can model long-range dependency enabled by the shifted window mechanism. Thirdly, fusion module. After enhance the features of different scales, we will integrate them together with the fusion module, which aims to bring the contextual information from low scale to high scale. We use a pixel shuffle layer to upsample the feature map and concatenate it with the feature map of high scale together and to pass through a convolution layer. Finally, HR reconstruction module. This module aims to produce the final result. This process is realized by several convolution and pixel shuffle layers. In this table, we show quantitative comparison for compressed image super resolution on 5 benchmark datasets. The results are tested on 4 times super resolution with different compression qualities. Extensive experiments show that our HIST outperforms other methods on compressed image super resolution tasks. As shown in figure, compared with other methods, our HIST can generate super resolved images with fewer artifacts. Moreover, HIST performs better in rich texture areas, resulting in pleasant perceptual quality. All these benefit from a hierarchical network structure, which captures features at different scales and enhances the network's representation ability. To further explore the advantage of introducing a hierarchical network structure, we set network branches from 1 to 3 and observe their performance on 4 times super resolution tasks. As shown in table, with the increase of branches, the parameters of network grows quickly, while the performance only brings a little increase. Therefore, trade-off between performance and overall complexity, we choose a 3 branches HIST in our work. If you are interested in our work, more details can be found in our paper. Thank you for your lesson.
Okay, we have time for 1 question. So if no questions, then let's move on to the next talk. We have the Swing to SR and Beijing Choi.
Yeah, sure.
Will give the talk.
Hi, everybody.
I'm Eugene Che from Megastudy Edu, and I'm going to present our work, SWIN2SR, SWIN-V2 transformer for compressed image resolution and restoration. Our code and trained models and online demo are available on our project webpage. As Lanyan already told, compression plays an important role on the efficient transmission and storage of images and videos through band-limited systems, such as streaming services, virtual reality, cloud storage, or for images. However, compression leads to artifact and the loss of the original information, which may severely degrade the visual quality of the imaging. For this reason, quality enhancement and restoration of compressed image has become a popular research topic. Recently, SWIN-IR achieved the state-of-the-art in image restoration task. It shows out of performance on this area and very well structured. SWIN-IR used SWIN transformer layer and proposed the residual SWIN transformer block. Our work, SWIN2SR, is focused on compressed super resolution task and changing SWIN transformer V1 block to SWIN transformer V2 block. The main change from SWIN transformer V1 block to SWIN transformer V2 block are three features. First, a residual post-normalization replacing the previous pre-normalization. Second, a scaled cosine attention replacing the original dot product attention. A third, a log-spaced continuous relative position bias approach replacing the previous parameterized approach. In the original paper of SWIN transformer V2 shows that first and second features make it easier for the model to scale up capacity, so we can train larger model more stably. And third features make the model to be transformed more effectively across window resolution. In some tasks, our SWIN2SR model achieved the same result as a SWIN-IR, yet training 33% less iteration, especially lightweight super resolution. In compressed super resolution task and our work, the input is JPG compressed quality 10 and 4 times downsampled from ground truth. In this work, we used 3 losses called the auxiliary loss, L1 loss, and high frequency loss. Auxiliary losses minimize the L1 distance between the downsampled prediction Y hat and the downsampled reference Y PNG images. And high frequency loss, we extract the high frequency information from the high resolution images and formulate it as shown in the slide, where HF denotes the high frequency information of the image. To obtain this, we convolved a simple 5 versus 5 corner B as a Gaussian blur operation. This approach we denote as a SWIN2SRCI, an end-to-end model for JPG artifact removal and super resolution. The experimental results are shown in the slide. We experiment in classical SR X2, X4, and lightweight SR X2, and real-world SR Extra. More detail is in our paper. And we show our demos in here. This demo is implemented by Hugging Face and Guardio. The code is fully open sourced on GitHub, and if you want to know more about our project, feel free to check our project page and paper or contact us. In the end, thanks for the organizer to host this interesting and amazing challenge. Thank you.
Okay, thank you. We have time for one question.
Well, I have a question. So you have designed some high frequency loss and aux loss, right? So how much improvement for this two losses by adding these 2 losses?
I'm not pretty sure, but in the 000 over there is a 2 decimal, so there's a change in there. Maybe 0.1 or 2, 3 point. I guess.
Okay, in comparison with only use the L1 loss.
Yes, right, in PSNR.
Okay, thank you.
Okay, so if no other questions, then thank you. And let's move on to the last invited talk of the day. We have Professor Gordon Wettstein that will join soon. Meanwhile, he asked for me to play his recording, and he will be here to take the questions at the end of the presentation.
Hi, I'm Gordon Wettstein, Associate Professor of Electrical Engineering and Computer Science at Stanford University, and I'd like to tell you a little bit more about emerging neural scene representation, rendering, and generation approaches that will shape the metaverse of the future. So some of you may be familiar with emerging neural radiance field techniques. So these are ideas where we take photographs of real scenes like the ones you see here, and then we train a neural network to represent the 3D scene, and we can render novel views from the scene. This has really sparked a revolution in computer vision and computer graphics because we now go towards neural network-based representations of these different scenes to represent them. This is not only enabling computer vision and computer graphics, but also in robotics, autonomous driving, and importantly, in metaverse applications in VR and AR. Let me tell you a little bit more about the generation aspect here. Here's a few examples of our recent work that we called efficient, geometry-aware, 3D generative adversarial networks. So the idea is that we don't just represent a single scene using a neural network, but we use this as to generalize across many different scenes of the same type. So if you think about one phase can be represented by one neural network, and many phases could be represented by their own neural networks. But what we would like to do is understand what this distribution of functions will actually look like so that we can sample new types of these functions and generate people that don't really exist in the real world, and we can render them from multiple different perspectives to generate new 3D assets of people, cats, or other types of objects. So this is the idea behind 3D generative adversarial networks. Like any neural network, a 3D GAN has to be trained on some kind of a training data. And there are basically two choices today. The first choice would be to work with recorded data. So some people have built specific studio rigs where we have many, many different cameras, and we bring people in and we have these shower caps, and we capture these people from many different perspectives at the same time. We can use conventional computer graphics and computer vision methods to reconstruct the shape of these people, but they're sort of limited because it's expensive to build these setups, and it's difficult to get lots of different people going through this. So for example, this is a data set that I'm showing you on the left. It only has about 500 people, but they all come with high resolution photos from multiple different perspectives and ground truth depth maps. So a data set like that may be good to train a 3D GAN, but it's sort of limiting in the type of identities, in the type of people that it shows, and also in the detail that it has, because it doesn't even show hair. On the other hand, we have synthetic data that we can use to generate many different people, almost an infinite amount. For example, this data set from Microsoft that has more than 100,000 different people in it. They can be rendered from different perspectives. We have ground truth depth maps. We have labels, semantic labels. We know exactly which pixel contains what type of object. And we have a great diversity of in the scene. The problem with synthetic data, though, is that it's not real. So we can easily spot that this is close to photorealistic, but not quite photorealistic. So why can't we use existing single view data sets like FFHQ to train 3D GANs? Well, the challenge is, first of all, that we only have a single photo of each person and that these are totally uncurated examples. We just have these different photos of different people and they have no multi-view supervision, they have no labels, we don't even know what the camera pose was. And there are also lots of biases in these data sets in that people who look at a camera typically smile, whereas people who don't know that there's a camera, they don't smile. So there's a smile bias, for example, towards where the camera view is. And you need to really understand these data sets in order to be able to work with them. Now, it is possible to use unstructured single view data sets to train 3D GANs, which I'll hope to convince you in the next couple of minutes. Before we dive into 3D GANs, let's talk about 2D GANs. 2D GAN is a neural network architecture that consists of a generator and a discriminator. The generator will take random noises input and will generate a 2D image. This image is then fed into the discriminator along with a massive training data set of real images, and the discriminator will learn to tell if the generated image is real or fake. If you train the generator and discriminator together for long enough, they are able to generate photorealistic looking images that are indistinguishable from the training data. Now, that is great in 2D, but for metaverse applications and beyond, we want to generate 3D assets. So in this context, how do we generate a 3D scene that doesn't exist in reality and then make sure that this is photorealistic? Well, the first thing we need to do is set up a discriminator architecture that tells us whether the scene is real or fake. And simply extending 3D existing generator and discriminator architectures to 3D doesn't work because it's typically so memory inefficient that it's impossible to train such a network. So instead, what we can do is we can generate a 3D scene, and I'll tell you in a second how we actually generate it, then render it from multiple different camera perspectives, as you can see here, and then feed each of these 2D images into an existing 2D discriminator to tell us whether these images are real or fake. And so the benefit of doing this is that you can use existing 2D image discriminators that are well explored and computationally efficient to make sure that just any view that you could potentially render from your generated 3D scenes are photorealistic. So now, how do you generate a scene? Part of the challenge is that it's very computationally expensive to train a GAN. Training a GAN takes maybe a week of time on many expensive GPUs. So this is a lot of different computational resources at work. And it's very difficult to tune the hyperparameters to get this to work. So we need to be very computationally efficient to do that. The computational efficiency is almost the key element to training a GAN, at least a 3D GAN. So we came up with a really simple way to represent 3D scenes that is particularly well suited for 3D GANs, in particular the generator architecture. Instead of representing the 3D scene as point clouds or volume of features, we represent it as a set of 3 planes that we call the triplane representation. These are axis aligned with the XY, YZ, and XZ axes, and they contain features. You can now query any position in 3D space XYZ by projecting that 3D position onto each of the different planes and doing a lookup there of the 2D feature that lives on this plane. We then aggregate these 3 features using some aggregation function, such as a sum. That would be the simplest, but you could also use products or mixtures of products and sums. There are different choices here. We're just going to stick with the sum for now because it's the easiest. And then we feed the aggregated 3D feature into a small neural network that is very computationally efficient to be evaluated, and that's also memory efficient. So this neural network translates the 3D feature that is very abstract into a density and a color that can be interpreted by neural rendering algorithm, volume rendering, for example, and that can then render a 2D image from this. The nice thing about this triplane representation is that it's very memory efficient. If you scale up the resolution of this 3D scene, the memory required to store features on these 3 planes scales quadratically rather than cubically, which it would be for voxel representation. Turns out that it's easy to generalize across different scenes with this triplane representation. And importantly, this representation is backwards compatible with existing 2D generator architectures like StyleGAN. And I'll show you what that means in practice. Now you may think, hey, representing a 3D scene with just 3 planes doesn't really give you the same capacity or fidelity as NeRF or other types of representations that you've seen recently. Well, let me try to convince you otherwise. This is a scene that we optimize with a reference NeRF implementation on the left and with our triplane implementation representation on the right. And what you can see is that our triplane representation is not only 8 times faster to optimize, but it also captures all the detail. For example, the text in this scene very well. Now, I have to say that the triplane representation out of the box does not contain view-dependent effects. You modify it to do that, but in this case it doesn't. So you get a lot more specularities on the NeRF representation. Okay, so now I showed you triplane representation. I hope that I convinced you that it has enough capacity to represent a 3D scene at high fidelity. And we are just going to use standard volume rendering to render 2D images from this. In order to build a 3D GAN, there's other parts that we also need. For example, we need a generator. Luckily, we can build on existing 2D generator architectures such as StyleGAN 2. I don't want to go too much into detail, but these are convolutional neural networks that turn random noise into 2D images. Instead of generating the image directly, we generate the features on the 3 planes and then just rearrange them into 3D. As I mentioned before, we can also use existing 2D discriminators at the end because we just feed the rendered images from these 3D representations into these discriminators, and they will tell us whether they're real or not, and they're ideally trained such that any rendered image looks real. There's a couple of other components, like a super resolution module. We're actually still computationally limited to rendering images at a resolution of 128 by 128. So the super resolution module helps us go from that raw rendering resolution to the final desired resolution in a multi-view consistent way. We also use pose conditioning of the generator and the discriminator, but these are maybe implementation details that you can put up in the paper. So as I mentioned, a standard discriminator takes a random sample image from the data set of images that we know to be real, for example, here the left one, and it takes a generated image from our generator and it compares them to tell you if it's real or fake. We modified this idea a little bit for our framework by doing the same thing at multiple different resolutions. So we are taking the original data set and comparing it to both the final synthesized output of the super resolution module, but also to the raw rendering resolution at a lower resolution to a blurred version of the real image. So this dual discrimination architecture is what makes sure that our super result images are multi-view consistent. And here you can see an example of a generated person. I'll just show you some results now. You saw it earlier at the raw neural rendering resolution. Here we have the super resolution module applied, and you can see that we get a lot of detail out of this super resolution module. Like the hair, the eyebrows, the eyes, and other parts that really make up a photorealistic person. Here's another example of a person that doesn't exist in the real world. This is a totally randomly generated person, but looks perfectly real. We can move the camera around. The nice thing is also that our model learns to, represent the scene or these types of faces using their geometry. We never trained it to learn the geometry correctly. It just does it automatically to be able to render these people in a multi-view consistent fashion. So the network's never trained with ground truth depth or any multi-view supervision. It just learns to do it by itself. The same idea applies to other object classes like cats, cars. We showed a few others in the paper. Here I'm just going to show you a cat. And you can see that the geometry is also represented at a reasonably fine detail. But these rendered cats look pretty much photorealistic. And all they're trained on is random collections of single view images of people's cats. Here are a couple of existing works. Giraffe is state-of-the-art method on the upper left. It generates high quality images, but they're not multi-view consistent. PyGAN was our own work from about a year ago that was very multi-view consistent, but the quality was still sort of limited. There are other approaches too, but I'd say EG3D has made a big step forward to generating photorealistic 3D content. So just comparing PyGAN, that was our own work a year ago, to EG3D on the bottom, we get a lot more detail. We get the frame rate is higher. So we're going from 1 frame per second to 35 frames per second. So we can render this 35 times faster. And this is so important for just training the scan to get the quality you want. FID score, lower is better, is very low. It's almost as good as 2D generative models. So we're getting close to getting the same quality that we've known from 2D generative models. This is really one of the prime examples. Choppy. Just start the slide again. Appreciate it. Okay. So this is something you can't do with any existing traditional computer graphics or computer vision model. What we're doing here is we have these latent codes for each person. So each person is really represented by just a few numbers of random noise, and we're interpolating these latent codes. And what you can see is that this GAN that we trained can now interpolate between these people as well, and the shapes representing them. Sorry, I'm having trouble here. But this is it's not an image-based interpolation or anything. We're just interpolating these latent codes. Okay. As I mentioned, all this works in real time. Here's a preview of generated cats and people, where we just move the mouse to move the perspective and change some attributes. We're interpolating in the latent code also. We're just changing the camera perspective. So this makes it directly applicable for metaverse applications, and it makes the training just so much more efficient that we can actually get this quality that I showed. Once we have a trained GAN, we can now do what we call a GAN inversion, where we take a single photograph of a person on the left, and we start with a randomly initialized EG3D code on the right, and we can now optimize this code to match the single image. So what that means is we can fit our 3D GAN to a photo of a person and render that same photo from multiple different perspectives. So the pre-trained GAN is very efficient also for photo editing, manipulation, or other tasks beyond just unconditionally generating people. So for example, here we took a photograph of Abraham Lincoln and we generated a 3D representation of it. So this is interesting because now we can start thinking about photo editing and other tasks. For example, you had a single image. Can you animate this image? Can you change other attributes of it? So other GAN inversion work has shown how to edit attributes such as age, facial hair, glasses, gender, or other attributes from 2D images. But wouldn't it be great if we could take a video, capture the facial movements of this target video, and then retarget that onto our source image as well? And using 3D GAN inversion, we can do that, which you can see here. These are first results of a single source image on the upper left being edited in the attributes and then being reanimated. We can also get the shapes of all these edited figures. Again, this person doesn't know anything about Adam Driver. It's the first time that it's seeing the single source image, and it also doesn't know anything about Obama. We can just combine these in a really interesting way to start working on some editing tasks. Now, in the metaverse, we think about human bodies as much as we do about faces, but generating 3D human bodies is a little bit more challenging. One of the problems is that faces are sort of always well aligned. There's just some facial expressions that change, and the identity, obviously. But for human bodies, working with photographs of human bodies is challenging because they're in all different types of poses. They have lots of different accessories. They have their arms left and right, up and down. It's very difficult to find a good aligned way to represent them. So it's a little bit more challenging to work with. We've started to work in that space, and I got some initial results in a work that we call generative neural articulated radiance fields, or GNARF. And here the idea is again to map a latent code Z, latent random code Z, through a neural network into a person in a canonical pose. And so we can generate the person, and then we can deform this person in a way to animate them in arbitrary ways that you can see on the right. These are just some dance moves from totally different data sets, and we're now cycling through the identity on the left and then move these people. So these are all synthetically generated. On the upper left, you can see the driving mesh. The rest of these are just different identities that we generated, and we can now animate as well. The quality isn't quite as good, I would say, as for the faces yet, but this is work in progress, and already beats the state of the art that you can see on the upper right by quite a large margin. So we are working towards digital people that we can generate, reanimate. They can populate the metaverse, digitize ourselves, help edit photographs, videos of us. Yeah, with this, I'd like to thank you for your attention. My lab is the computational imaging lab. We actually work on a number of different topics beyond neural rendering. We also work on AR, VR displays, computational cameras and displays, and leveraging AI to develop new imaging and display systems in general. So with this, I'd like to thank the co-authors of the EG3D paper that I mentioned for most of this talk, and also the other folks in my group who contributed to this line of work. Thank you.
Okay, so this was the talk. Thank you very much, Professor Gordon Wechstein. So if you have questions, please unmute yourself and let us know, or you can just drop a question in the chat. Okay, so yes,
yes,
Marcus?
Radu. Wait 1 second. Okay. Yeah, so thank you so much for your presentation, Professor. So I'm wondering, for these new generative models, I don't know the details about the CVPR paper that you mentioned, but exactly not how you evaluate them, but how do you believe that you should evaluate those models? Because let's say art-wise, or like let's say 2D models, like before we heard Professor Oma about stable diffusion, and now this 3D generative model. Do you think that FID and these sort of metrics are a bit out of date, or how do you think that we should evaluate this beyond, qualitative samples?
Yeah, that's a great question. FID is certainly a great starting point, first of all, because of legacy reasons, like you want to be able to compare the quality of your images to, or the, FID score. What does it really measure? I mean, it measures how the distribution of images, 2D images generated by your model matches the training distribution, right? And if you have access to the training distribution, then that's a great metric. For foundation models, that's not always the case, right? Like, we don't know what ImageGen was trained on. Nobody has access to that data. So, evaluating FID score isn't necessarily possible. You have access to the model that was trained on the data, but you don't really have access to the data itself. So, in that context, FID may be not the right metric. For simple 3D GAN models like this, or I call it simple, but trained on simple data and open data sets like FFHQ, I think that's easily possible, and it's the standard way. Now, FID combines multiple different aspects. It combines the image fidelity, so you think about it, the visual quality, but also the diversity. So it may be useful to disentangle the two, because some methods are maybe look good, but maybe they're not very diverse. Or people play all sorts of tricks to trade off between these two. Like the truncation trick is well known. You trade diversity for quality, and things look good. People have been looking at precision recall. There was a paper on, trying to disentangle the two and measure one with precision, the other with recall. I mean, that's a useful thing to do. But none of these metrics also measure 3D multi-view consistency. So this is a big topic in 3D generation. It's like, how multi-view consistent are these images actually? Each image can look great, But if they're not multi-view consistent, then it's not a real 3D GAN. So measuring multi-view consistency is important. So we've been doing this in a couple of different ways, and it's not straightforward. But typically, you can, for faces and bodies at least, you have certain landmarks that exist. And what you can do is you can look at any one generated image, maybe find 64 landmarks, either in the face or in the body. You can find the joints that you know. You can reproject them using the depth that you know, for example, because you also generated the depth into different images, and you can compare these reprojected landmarks, for example. That's I think a good way, or at least a starting point for evaluating 3D multi-view consistency. But it's only true for the face or for the body, for the joints. Like the real difficult part is really the hair, for example, or other fine details. So now we don't have landmarks for hair. So then, you could use a call map reconstruction on the multi-view images of a single scene and just show the point cloud and see how scattered it is, but it's also not a really good quantitative way to do it. We also don't have a good way to evaluate the depth map, for example. I mean, it's not supervised, so you don't have ground truth again, and the resolution and quality of the depth maps among many different methods is vastly different. So you're absolutely right. I think rethinking these metrics for 3D generative methods in general, and especially so for emerging diffusion models, is a really important topic. And I don't have all the answers, but yeah, great question.
Thank you for your honest answer. Yeah, I completely agree that, let's say artistic-wise, the results are amazing, but there are like 40 papers, well, maybe 100 papers every month about neural rendering, and all of them have kind of the same kind of metrics and the same good-looking images. So there is no like a well-established benchmark of we should evaluate these and compare methods in this way.
Yeah, I mean, the thing is for these standard neural rendering methods that operate on a single scene, like I call them overfitting methods, so NeRF, or other scenes where you have one or multiple images of the same scene, you're trying to represent that scene, and you do novel view synthesis. Now, that's pretty straightforward. You just take a data set of images, for example, synthetic images, you leave out some and you use them for testing. So, you can make up your own test and training set if you want, and you can use standard image metrics like PSNR, SSIM, LPIPs, that kind of stuff. But I think for these generative models, it becomes a lot more tricky. But yeah, standardized tests is a good thing, even for NeRFs, right? But I think, a couple of recent methods have used these ShapeNet objects and have pretty, like PixelNeRF and a couple other methods, you all use the same ShapeNet class, but they're so simple that it's like almost like MNIST. It's getting too simple, right? So I think metrics is very important and not non-straightforward topic.
Okay, thank you so much.
Okay, another question.
Hello, Professor. Thanks for the talk. What is the intuition behind projecting images onto a triplane structure and then aggregating them back?
Okay, I'm not sure if I understood the question, but why not take the images, project them onto the triplane, and then work from there? Is that the question?
No. What was the intuition behind doing this three-plane projection?
Oh, the three-plane projection. Oh, yeah. So we were working on this for a while, and the only reason why we worked on this was to make it simple and fast. And the title, Efficient 3D GANs, I mean, it sort of suggests that, but the big insight that Eric, the student who was leading this project, made was that, when we worked on PyGAN and some other 3D generative models, is that it's just too slow. And the quality of a GAN is by a large extent defined by how many times you can iterate over the training set. Whatever fancy things you're doing in your model almost don't matter. The first thing that matters is how many epochs can you train, right? And you're going to be limited by the time to the deadline. So, for us, it was always like, okay, we're going to build models that can train on a cluster, but no more than 1 week. If we have to train it for longer than a week, it becomes sort of infeasible. That's like an arbitrary standard, right? And we were lucky because we had access to the NVIDIA cluster because Eric was doing an internship at NVIDIA, and it was this collaboration. So it's challenging for academic groups to do that. I mean, we have a big server in the lab also, but many students want to use it. So it's a dilemma that goes beyond this specific project. But our goal was to find the most efficient way to render something And it didn't have to be super perfect for overfitting scenarios necessarily. It just had to be fast. And, it had to be fast and ideally also backward compatible with these 2D generators. So it was really Eric who came up with this idea of coming up with this triplane representation. I mean, in retrospect, you can think of it as a rank 1 approximation of the volume, right? It depends on the aggregation function, but what's a rank 1 volume? You can represent it by the outer product of 3 planes. So then you have 3 planes and you have a multiplication as the aggregation function. Now, we tested multiplications too, and found that a simple sum of all the features actually works better and more robustly.
Thank you.
But you can think about it as a rank 1 thing. But you're free to change the aggregation function.
Thank you.
Okay, some other questions? So while you are thinking about other questions, I have also one. So okay, let's wait a little. So if you have questions, please just unmute yourself and let us know, or just write in the chat, and Professor Weinstein will respond. Okay. Okay.
Okay.
So
Well, thank you.
I have one question. The question here is how important is actually the depth information? Because I'm seeing that the results are quite good in what you are showing, but actually the depth image that is there is quite rough.
Yeah.
It's not very detailed and so on.
Yeah. So I would say if you want something that's multi-view consistent, the depth is important. Now the question is, how important is it, and how much detail do you have to have in there? So without a good depth, like Giraffe is a great method, it generates very nice looking images, but the depth is crap. And with that, you lose the ability to really do anything multi-view consistent. Now, even with this clever triplane representation for our method, it's still slow. So we still have to operate at a lower resolution for generating the raw volume. And so the detail of the depth map is limited by that. We have a super resolution module on top that gives you really the high resolution at the end. Sorry, I have a 3-year-old who also wants to be entertained at the same time. So the detail is limited simply again by the trade-off between computational complexity and multi-view consistency. There are also ambiguities in there because we don't have depth to supervise with. For example, the eyes in the data set FFHQ. Everybody on every photo looks at the camera, no matter where. So there's a bias in the data set in that camera position and gaze direction are entangled. It's very difficult to unentangle that. And the easiest way for the network to learn that is by having this hollow eye illusion, where it actually learns the eyes to be not convex, but concave, and puts a texture on the back. It looks correct from all perspectives, as if the person gazes at the camera from anywhere. So it's not the correct geometry, but it's the easiest way for the GAN to explain this phenomenon. So, and similarly, you have other biases like that, and it's really difficult to get hair because everybody has different hair. Remember, we only see every person only once, right? Like we never have multi-view supervision. So there's a little bit of there is a little bit of aliasing when you go through the different views, and that's basically multi-view inconsistency introduced by the super resolution network. Now, the thing is, a few follow-up papers already came out, coming up with, I would say, more efficient discriminator architectures. So rather than taking the whole image in, they work on patches. For example, Peter Wonka had a paper on that a couple months ago, and they're more efficient. And they were able to actually train the whole network at a much higher resolution for the depth. So that helps and looks a lot better already all of a sudden, without really improving the scores overall. But that's interesting. Then we didn't do any regularization or anything on the shapes. So we didn't do anything. So you can probably come up with 100 different ways of slightly regularizing this. But again, it gets challenging to test all of these methods because it takes so long to train the GAN. Well, now that the model is out, people can, and the code too, everybody can do it themselves and try it. But yeah, it's not straightforward. And it's a big topic of research. Like, that's the holy grail, getting like high quality shapes, ideally that are animatable and exportable into like legacy formats like meshes and textured meshes. I mean, that would be ideal, because then you can train this 3D GAN, use the volume rendering for that, but then convert it back to assets that people can use in their existing pipelines already and reanimate and so on. So I think these are some of the big challenges moving forward.
Okay, we have time for one extra question. So Pedram Dindari, maybe you want to just unmute yourself and ask the question. Pedram? Okay, if not, I can just read in the chat. Yeah, Pedram?
Yeah, I'm here.
Okay.
Okay.
So what?
So my question was that how can a generative model, which is only built from 2D convolutions and trained on 2D convolutions, maybe pre-trained or not, but how can we make 3D representations out of it by just simply splitting its output to 3 planes? They are not really, I didn't notice or didn't catch it, but they are not temporal or spatial consistency between those things. They are outputs of some convolution layers. How can that happen?
Okay, so excellent question. So I've gotten this question a lot, actually. It's a really good question. It's like, if everything is 2D, how is it possible that, and there's no multi-view supervision, how is it possible that you get something that's 3D multi-view consistent, right? So the answer has twofold. The first is, there is a physical bottleneck that uses a physical 3D rendering step as part of the network. So the generator is 2D, it generates 3 planes that are treated as multiple different features of the same 2D output. And then these 3 planes are arranged in 3D, and then there's a 3D rendering step on top, this volume rendering, the same that NeRF does. And that it basically, this physical module forces the generator, the 2D generator, to learn something that makes sense after the 3D rendering step. So that's number one. So there is a 3D module in there, and that's really the rendering. And that interprets whatever's output as a 3D volume. So the generator is forced by piping the output, the features of the 2D generator through this 3D bottleneck. It has to learn something that makes sense in 3D. So that's number one. But the other nuance to this question is, the training data is only 2D. We never see a single person from multiple different angles. We only have single view observations of any one identity. And so this is where the adversarial loss function that GANs are trained with is important, because it doesn't do a per pixel loss or anything like that. It's trying to match distributions. And so the distribution of the training data is basically, it doesn't come for free. You actually need to know what the camera pose distribution of the training data is. So, for FFHQ, it's a data set of 70,000 people's faces. You basically know that most people look at the camera. So it's kind of like a Gaussian distribution where most cameras look at the face from front on, and then there's some standard deviation, going to the sides and going to the top and bottom. So we can model that. That's like the black magic of getting this pose distribution in the first place. And we list that in the paper, so you can reproduce it. Once you have that pose distribution, you can sample images using that pose distribution from the model that you're training, and then you're trying to match the images, but there's never a per pixel loss. It's really this distribution matching loss. But the pose distribution is a key. Like, if you don't have that, or if it's not good, then your model is only going to be as good as your approximation of this pose distribution. So hopefully that gave a little bit of insight into why we can train a 2D model to get something 3D multi-view consistent. Yeah, and the adversarial loss also ensures that any one sample from all these different directions looks like a face, right? Like it's never just trained on one view here and one view there. On average, it's trained over all the distribution of views. So it's only frontal views. It's never, you can't render it from the back. There's nothing there because no images in the training set see the face or the head from the back. But from anywhere from from the front, it will always look like a face, because that's what the adversarial loss says, is like make anything that's generated look like a face. In the 3D module, make sure that, you know, there's no view inconsistency. It has to be at least close to multi-view consistent. And with these two constraints, it's enough to use a 2D model, or mostly 2D model, to train this 3D gap.
Okay.
Okay, so the second principle that you told is on behalf of the discriminator network, if I get it correctly.
Yes. It's just this is a characterization of all GANs, basically. You know, when you train a GAN and you sample any point in the latent space, they will all look like images that came from the target distribution. Whether it's MNIST, you can sample anywhere in the latent space, and you get an image that looks like a number. Or in this case, you can sample anywhere in the latent space, but also anywhere in the camera space. You can think about it as that. So this is a property of probabilistic models, really, and with that also generative models. So you know, variational autoencoders have that property. GANs have that property. Diffusion models should have that property also. So you know, all these types of models have that property. Others don't. So feed-forward networks don't have that.
Okay.
Okay, yeah, thank you. Thank you very much.
Okay, so this was probably the last question for Gordon, at least here. If you have more questions, I think Gordon really is more than happy to answer if you send them by email. Okay, Gordon, thank you very much for your crazy good talk and works. Okay.
Thanks for having me.
Okay, and now let's move to the last part of our workshop, and we have a challenge report, Instagram filter removal challenge, and Furkan is here, and we'll discuss about this after the presentation. The presentation, I will play it myself. Okay, here it is.
Hello everyone, I am Furkan Kınlı from Özyeğin University. Now I'm going to present about AIM 2022 challenge on Instagram filter removal. This challenge is jointly organized by my colleagues Sami Menteş and Barış Özcan, my supervisor Professor Furkan Kıraç from Özyeğin University, and Professor Ravi Timofti from University of Würzburg. Before going into the details about the challenge, let's review the main motivation behind removing Instagram filters from the images. Understanding the content of social media images is a crucial task for the industrial applications in different domains like retail, fashion, and e-commerce. The images shared on social media generally contain visual filters applied, where these filters lead to different consecutive transformations on top of the image, or inject varied combinations of distractive factors like noise or blurring. Therefore, we can say that the filtered images are the challenging subjects for the recent deep learning strategies, especially for CNN-based architectures. CNNs are not robust to these transformations or distractive factors, and their performance negatively affected for the downstream vision tasks. At this point, we can define that the main goal of Instagram filter removal is to produce realistic and pleasant images in which the impact of the filters applied is mitigated while preserving the original content within. Jointly with the AIM workshop, we propose an AIM challenge on Instagram filter removal. The task of recovering this set of Instagram filtered images to their original versions with high fidelity. With the help of this challenge, we would like to increase the attention on this research topic that may help the industrial applications that primarily target social media images. In this challenge, we have used the IFFI dataset, which is introduced to our prior work, and has 500 and 100 instances of original images and their filtered versions as the training and validation sets respectively. There are 8,500 training and 1,700 validation images in total. For the final evaluation phase, we have shared another 100 instances of images with 11 filters which are available at the annotation time. And we use them as the private test set. The filter types are picked for the private test set and named as Amaro, Clarendon, Gingham, Hi-Fi, Hudson, Lo-Fi, Mayfair, Nashville, Perpetua, Valencia, and X-Pro 2. We have collected all samples in high resolution and have provided low resolution and high resolution versions to the participants. The final evaluation has been done on low resolution images. Also, the participants were allowed to use extra data in their training process. Considering Instagram filter removal is an image-to-image translation problem, we have measured the performance of the submissions by the common fidelity metrics in the literature, which are peak signal to noise ratio PSNR and the structural similarity SSIM. The participants have uploaded the outputs that they have obtained to CodaLab, and all evaluation process has been done on the CodaLab servers. However, we have shared the evaluation script on the challenge webpage. In the evaluation phase, we have ranked the submitted solutions by the average PSNR value on the private test set. Lastly, we did not employ any user study in the evaluation process of this challenge. Challenge has lasted 3 months. The participant had 2 months for developing their algorithms to achieve the best rank in this challenge. After the submissions were completed, we have validated the leaderboard by double-checking the scores by the output sent in the submission files. We have 114 registered participants to the challenge during the development phase. At the final evaluation stage, 9 teams have submitted the valid results, codes, executables, and the fact sheets. Let's review the approach used for attacking Instagram filter removal problem. The participants have used different architectures and strategies for solving this problem. Top solutions follow different deep learning strategies. For example, the first team in the rankings has employed U-shaped transformers-based architecture with test time augmentation strategy. The team in the second rank has proposed a novel defiltering module in a simple CNN-based encoder-decoder architecture. The third team has used a 2-stage learning approach, where the first stage is responsible for processing the low-resolution input, and the second stage refines the output by using residual groups and different attention modules. If you want to look at through the other strategies employed in this challenge, please refer to our challenge report, and links will be given at the end of the presentation. Now let's take a look at the challenge results. Here are the overall results of Instagram filter removal challenge. Team 5 Win has achieved the PSNR value of 34.7 dB with a runtime of 0.91 seconds. Cassia LCVG team has placed to the second rank with their PSNR value of 34.48 dB with a runtime of 0.43 seconds. Team MiAlgo has took the third place in this challenge with the PSNR value of 34.47 dB with a runtime of 0.41 seconds. Here is the visual comparison of the top solutions. All top solutions have achieved to produce visually plausible, unfiltered images with less artifact and closer color palette as in the original version of the images. If we look closer, we can see that the winner solution has the ability to preserve the main color distribution of the original image better than the other participants. Similarly, we have another example that shows the minimal color differences between the winner solution and the others. Nevertheless, all top solutions have shown a very good performance on the regions where the colors are substantially changed, especially for the shallow and brighter areas. Team 5 Win, Yi Zhuo, Jitao Wang, Xiaolan Zhang from Xidian University proposed the UTF-8 method to restore the image after filtering. UTF-8 refers to U-shaped transformer for filter removal. This figure illustrates the main architecture of the UTF-8. They mainly consider the filter as an alternative to the noise. So they approach the problem as the noise. They have employed the test-time augmentation-based U-former model to enhance the generalization capability of their model. The CASIA LCVG team is the runner-up in this challenge. Team members are Yu Zhu, Chenghua Li, Chong Lang, and Jian Cheng from Chinese Academy of Sciences, Micro, and IRIA. This team have proposed a simple encoder-decoder network for Instagram filter removal task. Their proposed architecture, namely the filter net, consists of basic unit defilter block, which contains DV convolutional layers with different kernel sizes. And they fuse the features extracted by these different convolutional layers by using both spatial and channel attention. According to their findings, the data augmentation plays an important role for training of this model, especially mix-up strategy, and it improves the performance of their approach by 2D. To summarize, we have organized AIM 2022 challenge on Instagram filter removal to improve the ability to understand the images shared on social media. At the final evaluation stage, 9 teams have competed, and qualitatively and quantitatively state-of-the-art performances have been achieved by the top-ranked solutions in this challenge. Team 5Win is the winner of this challenge with the PSNR value of 34.7 dB, with the runtime of 0.91 seconds on PyTorch framework. Also, there are still rooms for improvement in this task. We are further planning to focus on the ability to remove all filter types, even if it does not annotate it. And also we can focus on building more accurate but less complex architectures, which means more efficient solutions for the real-time deployments. Let me conclude this presentation by giving thanks to our sponsors. The AIM 2022 workshop and the challenges are supported by these organizations. Thank you. This is the end of this presentation. Thank you for listening. Here are the links for my personal webpage, the workshop webpage, and the archive version of the challenge report.
Okay, so this was the challenge report presentation. If you have questions, please unmute yourself, let us know. Furkan is here. Yes, Andrei? Andrei,
Yeah,
maybe...
I can also ask it by mic if you can hear me well. I missed the information at the start of the presentation. Does the dataset include more filter applied on top of each other or just one filter? And if yes, does the order matter?
Actually, only one filter applied for a single image, and we have more than one copy for each instance. For training data set, we have 16 different filters applied, but only one filter for one instance. And at the end, we have 17 images for one single instance at all.
Okay, great. Thanks.
You're welcome. Thank you.
Okay, any other question? Okay, if not, because we are quite a bit behind the schedule. Thank you, Furkan, and let's move on with 2 other talks. One on instance filter removal as well. So here is the presentation. I think that the authors are here and they will be able to take the questions at the end of the presentation.
Hello, this is Unha Yo, and you're watching a summary of our paper CAIR for Fast and Lightweight Multi-Scale Color Attention Network for Instagram Filter Removal, presented at AIM Workshop ECCV 2022. Here's an example of an image of some apples and the same image with a filter. When training a deep learning model with the pure image, the model learns to classify the image as apple. But this model could predict the same image but with filter as orange, which is a wrong answer. Therefore, reverting a filtered image to its original image is necessary for various computer vision tasks before training or testing. Kinley et al. Proposed an Instagram filtered fashionable image dataset, which is a set of high-resolution fashionable images with 16 different Instagram filters. This figure shows an example of filtered images in the dataset. This slide shows the results of existing Instagram filter removal methods. IFRNet shows strength in PSNR, and CIFR shows a high SIM value. These two methods use an adversarial training strategy for autoencoder-like architectures, which is exceedingly complex and time-consuming. In the figure on the right, these two models remove filters quite well. Still, the restoration is insufficient in terms of color. NAFNet is one of the state-of-the-art image restoration methods. It shows better results than two methods mentioned previously. The visual results also show that result of NAFNet is more similar to the original than result of the two. Our proposed network CARE is excellent in terms of both PSNR and SIM. Also, CARE-M has fewer parameters and less operations than the existing methods. Visually, CARE shows the most similar restoration result to its original. Let me explain how we achieved this. We use NAFNet as our baseline to take advantage of its simplicity and low complexity. NAFNet adopts UNet architecture and consists of simple baseline blocks called NAF blocks. Please refer to reference number 4 for more details. This is the basic version of our proposed network CARE, which takes single input image. The main difference with NAFNet is that CARE-S has a color attention module, which takes an input image and outputs a color attention map. The color attention module is on the next slide. Here is the CARE multi-scale input version. The input image IF is downscaled by a factor of 2 as going down to the lower level, and each color attention module takes the input of its level and image from the upper level, then extracts color attentive features. The color attention module is described on the right side. It consists of Gaussian blur with a standard deviation of 12. This drone blurring operation ensures that only the color information can be extracted from the input image IFK-1. The structure, content, and fine texture come from the lower level image IFK, and some other convolution layers are used to get rich informations. To improve performance, we use an ensemble learning strategy. The ensemble network learns to combine the two results from CARE-S and CARE-M. This result is denoted as CARE asterisk. CARE is much faster and has fewer parameters than the previous Instagram filter removal methods, while obtaining more accurate results. We have summarized quantitative results of several methods on the IFFI dataset. CARE-S and CARE-M outperform IFRNet and CIFR in all metrics by large margins. CARE-M also shows better performance than NAFNet with fewer operations. CARE asterisk achieved the best PSNR and SIM among compared methods. CARE, which has the strength of the color attention module, successfully removed filters and restored color information.
Okay, so this was the talk. Do you have questions? If not, we are moving to the last, but not the least important talk of the workshop. So we have the unsupervised scene sketch to photosynthesis. The authors, I think some of them are here. So should I play the?
Oh, I can present if.
Okay, so then I will stop my sharing and please share your screen.
Thank you. So hi everyone, we present unsupervised scene sketch to photosynthesis. So the task we are looking at is, we want to synthesize a realistic image from this scene sketch. So it could be complicated because this scene, it can have complicated structures, or it can contain, multiple objects, like there will be pines, there will be like mountains, the ground and sky, right? And then here's, the expected result. You want to synthesize a realistic photo from the sketch. So this task is a little bit challenging because sketch is colorless, there's no texture. So it's a really ill-posed problem. So what we have is we ask to have a style reference. It kind of provides how the mountain texture should look like, what the sky should look like. And then the synthesized photo, in a way, it's really kind of copy paste the texture and color from the reference. Right? You can see how the color matches for the sky and how the lighting is similar for this mountain. And then on the other hand, this shape should match even with the sketch, the semantics should match. Another application we do is the sketch-based scene edit. So if you give a photo to the system, it generates a synthesized sketch. And then, say I don't like this blanket, or I want to add a new furniture like a lamp, I can just add a few strokes or remove a few strokes. And then we can synthesize the edit photo from it. It's easier than, use Photoshop or other algorithm to edit because you just need to change a few strokes. And of course, based on the system, you can also synthesize like a photo with new style, but it's like a similar content as your sketch. So existing work is really influenced by this sketchy scene paper, where they generate this scene sketch by just combining this object of a sketch with the reference of like a cartoon image. The thing is they try to break them into object synthesize and then combine them together. So like this paper, what they do is when you have a scene sketch, they first do a segmentation or detection to get out each object out. And then for each object, they try to synthesize object level sketch. And then finally, they combine them together to get a new image. The result is not that good because there could be like error when you are doing detection or segmentation. Another thing is, when you are combining the synthesized object to the background, there could also be artifacts. So really we ask if we can directly learn from images. So here is basically what we are doing. We directly, want to give a scene sketch, want to generate this, the holistic photo. And the takeaway is the holistic scene structure need to be preserved rather than broken into pieces for this task. So how do we do this? We are using a standardization module, to learn directly from photos, because really there's like a no paired, like a scene sketch to photo data set. We use edge detection to convert, this kind of training images, which is like widely available, just natural images with edge detection to get the edge. So this kind of mimic their this kind of like sketch. And then for inference, what we do is we also do edge detection to convert the sketch to edge. So it becomes like a realistic, it becomes more similar as a training. And then also decrease, the variety in the inference phase, because, you could have different individual drawing styles for the sketch. And then when we have the standardized input, we put to like a photosynthesis system, like take a sketch and a reference photo in and generate a realistic photo. So how we train the generation part? So first, how it's auto encoding, because this is like unsupervised training due to no pair data. So we need to first learn this kind of decomposed representation of a content and style. So each image will be encoded to content and style representations, and then decoded to like the whole like a reconstruct image. And this is guaranteed by the StyleGAN 2. And another thing we have is we also generate a corresponding edge. So make sure the content of this two image map as additional loss. Another thing, when we finish the auto encoding, and what we have is fine-tuning the network. Basically, we get the content representation from the sketch and then style representation from the reference photo, and then combine them together to decode the synthesized image. And we use GAN loss to improve the realisticness. Also, we ask the style and the content representation to be matching for this kind of like a triplet data set. So here are some results showing on generating from the room sketch with a sketch and reference. Also some results from the church. This is some result on the mountains. One thing we have is the style interpolation. Basically on the left, we can have a style representation from the winter image. On the right, we have that from summer. And then by linear combining, winter style and the summer style, we can gradually, move one image from winter to summer. And similarly, we can do the same thing for afternoon to dusk. Here's some result for the scene editing. Basically, you could have an initial like a drawing of several strokes for a scene, and then you can gradually basically just add on different objects, and then finally you can generate like a room as what you want, like a different design or different furniture. So how do we evaluate the system? We do a perceptual study. Basically ask if this generated photo can really fool people. So in the questionnaire, we have multiple questions asking people, if it's left or right, which is the real photo. So one is the real photo, another actually is from the generated system. If you do a random guess, it's 50%. And then what we have for mountain, is around 49%, which is means like people really hard to distinguish. But definitely, for indoor scene and church, when there's more complex structure, it'll be like a worse result. And yeah, we also have questions on style and content matching. And yeah, that's all. If you're interested, you can take a look for our, more results or code. And I'm happy to take any question.
Okay, thank you. Are there any questions? If not, I have one. Okay, so Peter, you are showing there, okay, at least that example, nice example, where you are just modifying the sketch and you are gradually adding objects. Okay, but that sketch and also the objects are pretty much like good quality sketches.
Yeah.
Okay, and the result is pretty much following quite closely the edges and is adding some extra textural content. Now, the question here is actually from the point of view of just amateur and so on, if actually you could turn some hand-drawn sketches that are just noisy and so on, and in the process, you are just creating something that is photorealistic and is fixing also the kind of sketch. You just imagine that I'm just drawing, I don't know, some stylized object, okay, and that object is just picked and something meaningful is there.
Yes. I think for now, this system really I think this is more like a hand drawn, right? Like this kind of like a lamp. You can see the quality is not that good, but when you're removing something like the blanket, it's probably better. But yeah, I would say for now, because really we are generating from the whole image to another photo. So for indoor scene, it could be a little bit hard due to the complication of different furniture. Yeah, but anyway, another thing I think what we do is we just so like this kind of synthesized sketch as a edge map, we can get something from another image and then we can copy paste the strokes from there. So it gives much better result. But if you draw by yourself, it depends on the quality. Yes. It could be worse. Yeah, but it's something we are trying to working on for sure. But thank you for the question.
Thank you for the nice talk. Okay, so this concludes also the workshop. Thank you very much, all of you that you succeeded and you stayed till the end of the workshop. I want to thank my co-organizers again. My thanks are going to the PC members of the workshop, to the sponsors, and all the people that supported our workshop and the success of this workshop. So thank you all, and I hope to see you in person here at the European Conference on Computer Vision in Tel Aviv, if you are attending, or at the next Computer Vision venue. So this being said, thank you all, and have a nice evening or day or night. Bye. Thank you.